Section 16 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Esther. The Elements of Geology by William Harmon Norton. Section 16, Chapter 10. Earthquakes. Any sudden movement of the rocks of the crust, as when they tear apart, when a fissure is formed or extended, or slip from time to time along a growing fault, produces a jar called an earthquake, which spreads in all directions from the place of disturbance. The Charleston Earthquake. On the evening of August 31, 1886, the city of Charleston, South Carolina, was shaken by one of the greatest earthquakes which has occurred in the United States. A slight tremor which rattled the windows was followed a few seconds later by a roar as of subterranean thunder, as the main shock passed beneath the city. Houses swayed to and fro, and their heaving floors overturned furniture and threw persons off their feet as, dizzy and nauseated, they rushed to the doors for safety. In 60 seconds a number of houses were completely wrecked, 14,000 chimneys were toppled over, and in all the city scarcely a building was left without serious injury. In the vicinity of Charleston railways were twisted and trains derailed. Fissures opened in the loose superficial deposits, and in places spouted water mingled with sand from shallow underlying aquifers. The point of origin or focus of the earthquake was inferred from subsequent investigations to be a rent in the rocks about 12 miles beneath the surface. From the centre of greatest disturbance, which lay above the focus, a few miles northwest of the city, the surface shock travelled outward in every direction, with decreasing effects, at the rate of nearly 200 miles per minute. It was felt from Boston to Cuba, and from eastern Iowa to the Bermudas, over a circular area whose diameter was 1,000 miles. An earthquake is transmitted from the focus through the elastic rocks of the crust, as a wave or series of waves, of compression and rarefaction, much as a sound wave is transmitted through the elastic medium of the air. Each earth particle vibrates with exceeding swiftness, but over a very short path. The swing of a particle in firm rock seldom exceeds 1/10 of an inch in ordinary earthquakes, and when it reaches 1/2 of an inch and an inch, the movement becomes dangerous and destructive. The velocity of earthquake waves, like that of all elastic waves, varies with the temperature and elasticity of the medium. In the deep, hot, elastic rocks they speed faster than in the cold and broken rocks near the surface. The deeper the point of origin, and the more violent the initial shock, the faster and farther do the vibrations run. Great earthquakes, caused by some sudden displacement or some violent rending of the rocks, shake the entire planet. Their waves run through the body of the earth at the rate of about 350 miles a minute, and more slowly round its circumference, registering their arrival at opposite sides of the globe on the exceedingly delicate instruments of modern earthquake observatories. Geological effects. Even great earthquakes seldom produce geological effects of much importance. Landslides may be shaken down from the sides of mountains and hills, and cracks may be opened in the surface deposits of plains, but the transient shiver which may overturn cities and destroy thousands of human lives runs through the crust and leaves it much the same as before. Earthquakes attending great displacements. Great earthquakes frequently attend the displacement of large masses of the rocks of the crust. In 1822 the coast of Chile was suddenly raised 3 or 4 feet, and the rise was 5 or 6 feet a mile inland. In 1835 the same region was again upheaved from 2 to 10 feet. In each instance a destructive earthquake was felt for 1,000 miles along the coast. The great California earthquake of 1906. A sudden dislocation occurred in 1906 along an ancient fault plain which extends for 300 miles through western California. The vertical displacement did not exceed 4 feet, while the horizontal shifting reached a maximum of 20 feet. Fences, rows of trees, and roads which crossed the fault were broken and offset. The latitude and longitude of all points over thousands of square miles were changed. On each side of the fault the earth blocks moved in opposite directions, the block on the east moving southward, and that on the west moving northward, and to twice the distance. East and west of the fault the movements lessened with increasing distance from it. This sudden slip set up an earthquake lasting 65 seconds, followed by minor shocks recurring for many days. In places the jar shook down the waste on steep hillsides, snapped off or uprooted trees, and rocked houses from their foundations or threw down their walls or chimneys. The water mains of San Francisco were broken, and the city was thus left defenseless against a conflagration which destroyed $500,000,000 worth of property. The destructive effects varied with the nature of the ground. Buildings on firm rock suffered least, while those on deep alluvium were severely shaken by the undulations, like water waves, into which the loose material was thrown. Well braced steel structures, even of the largest size, were earthquake proof, and buildings of other materials, when honestly built and intelligently designed to withstand earthquake shocks, usually suffered little injury. The length of the intervals between severe earthquakes in Western California shows that a great dislocation so relieves the stresses of the adjacent earth blocks that scores of years may elapse before the stresses again accumulate and cause another dislocation. Perhaps the most violent earthquake which ever visited the United States attended the depression, in 1812, of a region 75 miles long and 30 miles wide, near New Madrid, Missouri. Much of the area was converted into swamps, and some into shallow lakes, while a region 20 miles in diameter was bulged up athwart the channel of the Mississippi. Slight quakes are still felt in this region from time to time, showing that the strains to which the dislocation was due have not yet been fully relieved. Earthquakes originating beneath the sea. Many earthquakes originate beneath the sea, and in a number of examples they seem to have been accompanied, as soundings indicate, by local subsidences of the ocean bottom. There have been instances where the displacement has been sufficient to set the entire Pacific Ocean pulsating for many hours. In mid-ocean the wave thus produced has a height of only a few feet, while it may be 200 miles in width. On shores near the point of origin, destructive waves 2 or 3 score feet in height roll in, and on coasts thousands of miles distant the expiring undulations may still be able to record themselves on tidal gauges. Distribution of earthquakes. Every half hour some considerable area of the earth's surface is sensibly shaken by an earthquake. But earthquakes are by no means uniformly distributed over the globe. As we might infer from what we know as to their causes, earthquakes are most frequent in regions now undergoing deformation. Such are young rising mountain ranges, fault lines where readjustments recur from time to time, and the slopes of suboceanic depressions whose steepness suggests that subsidence may there be in progress. Earthquakes, often of extreme severity, frequently visit the lofty and young ranges of the Andes, while they are little known in the subdued old mountains of Brazil. The Highlands of Scotland are crossed by a deep and singularly straight depression called the Great Glen, which has been excavated along a very ancient line of dislocation. The earthquakes which occur from time to time in this region, such as the Inverness earthquake in 1891, are referred to slight slips along this fault plane. In Japan, earthquakes are very frequent. More than 1,000 are recorded every year, and 29 world-shaking earthquakes occurred in the 3 years ending with 1901. They originate, for the most part, well down on the eastern flank of the earth fold, whose summit is the mountainous crest of the islands, and which plunges steeply beneath the sea to the abyss of the Tuscarora Deep. Minor causes of earthquakes. Since any concussion within the crust sets up an earth jar, there are several minor causes of earthquakes, such as volcanic explosions and even the collapse of the roofs of caves. The earthquakes which attend the eruption of volcanoes are local, even in the case of the most violent volcanic paroxysms known. When the top of a volcano has been blown to fragments, the accompanying earth shock has sometimes not been felt more than 25 miles away. Depth of focus. The focus of the Charleston earthquake, estimated at about 12 miles below the surface, was exceptionally deep. Volcanic earthquakes are particularly shallow, and probably no earthquakes known have started at a greater depth than 15 or 20 miles. This distance is so slight compared with the earth's radius that we may say that earthquakes are but skin deep. Should you expect the velocity of an earthquake to be greater in a peneplain or in a river delta? After an earthquake, piles on which buildings rested were found driven into the ground and chimneys crushed at base. From what direction did the shock come? Chimneys standing on the south walls of houses toppled over on the roof. Should you infer that the shock in this case came from the north or south? How should you expect a shock from the east to affect pictures hanging on the east and the west walls of a room? How the pictures hanging on the north and the south walls? In parts of the country, as in southwestern Wisconsin, slender erosion pillars or monuments are common. What inference could you draw as to the occurrence in such regions of severe earthquakes in the recent past? End of section 16.
Section 17 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, July 2010. The Elements of Geology by William Harmon Norton. Chapter 11. Volcanoes. Connected with movements of the earth's crust which take place so slowly that they can be inferred only from their effects is one of the most rapid and impressive of all geological processes, the extrusion of molten rock from beneath the surface of the earth, giving rise to all the various phenomena of volcanoes. In a volcano, molten rock from a deep region below, which we may call its reservoir, ascends through a pipe or fissure to the surface. The materials erupted may be spread over vast areas, or, as is commonly the case, may accumulate about the opening, forming a conical pile known as the volcanic cone. It is to this cone that popular usage refers the word volcano, but the cone is simply a conspicuous part of the volcanic mechanism whose still more important parts, the reservoir and the pipe, are hidden from view. Volcanic eruptions are of two types: effusive eruptions, in which molten rock wells up from below and flows forth in streams of lava, a comprehensive term applied to all kinds of rock emitted from volcanoes in a molten state; and explosive eruptions, in which the rock is blown out in fragments, great and small, by the expansive force of steam. Eruptions of the effusive type. The Hawaiian volcanoes. The Hawaiian Islands are all volcanic in origin, and have a linear arrangement characteristic of many volcanic groups in all parts of the world. They are strung along a northwest-southeast line, their volcanoes standing in two parallel rows, as if reared along two adjacent lines of fracture or folding. In the northwestern islands, the volcanoes have long been extinct and are worn low by erosion. In the southeastern island, Hawaii, 3 volcanoes are still active and in process of building. Of these, Mauna Loa, the monarch of volcanoes, with a girth of 200 miles and a height of nearly 14,000 feet above sea level, is a lava dome the slope of whose sides does not average more than 5 degrees. On the summit is an elliptical basin 10 miles in circumference and several hundred feet deep. Concentric cracks surround the rim, and from time to time the basin is enlarged as great slices are detached from the vertical walls and engulfed. Such a volcanic basin, formed by the insinking of the top of the cone, is called a caldera. On the flanks of Mauna Loa, 4,000 feet above sea level, lies the caldera of Kilauea, an independent volcano whose dome has been joined to the larger mountain by the gradual growth of the two. In each caldera the floor, which to the eye is a plain of black lava, is the congealed surface of a column of molten rock. At times of an eruption lakes of boiling lava appear which may be compared to air holes in a frozen river. Great waves surge up, lifting tons of the fiery liquid a score of feet in air, to fall back with a mighty plunge and roar; and occasionally the lava rises several hundred feet in fountains of dazzling brightness. The lava lakes may flood the floor of the basin, but in historic times have never been known to fill it and overflow the rim. Instead, the heavy column of lava breaks way through the sides of the mountain and discharges in streams, which flow down the mountain slopes for a distance sometimes of as much as 35 miles. With the drawing off of the lava, the column in the duct of the volcano lowers, and the floor of the caldera wholly or in part subsides. A black and streaming abyss marks the place of the lava lakes. After a time the lava rises in the duct, the floor is floated higher, and the boiling lakes reappear. The eruptions of the Hawaiian volcanoes are thus of the effusive type. The column of lava rises, breaks through the side of the mountain, and discharges in lava streams. There are no explosions, and usually no earthquakes, or very slight ones, accompany the eruptions. The lava in the calderas boils because of escaping steam, but the vapor emitted is comparatively little, and seldom hangs above the summits in heavy clouds. We see here in its simplest form the most impressive and important fact in all volcanic action. Molten rock has been driven upward to the surface from some deep-lying source. Lava flows. As lava issues from the side of a volcano or overflows from the summit, it flows away in a glowing stream resembling molten iron drawn white hot from an iron furnace. The surface of the stream soon cools and blackens, and the hard crust of non-conducting rock may grow thick and firm enough to form a tunnel, within which the fluid lava may flow far before it loses its heat to any marked degree. Such tunnels may at last be left as caves by the draining away of the lava, and are sometimes several miles in length. Pahoehoe and Aa. When the crust of highly fluid lava remains unbroken after its first freezing, it presents a smooth, hummocky, and ropey surface known by the Hawaiian term Pahoehoe. On the other hand, the crust of a viscid flow may be broken and splintered as it is dragged along by the slowly moving mass beneath. The stream then appears as a field of stones, clanking and grinding on, with here and there from some chink a dull red glow or a wisp of steam. It sets to a surface called Aa of broken, sharp-edged blocks, which is often both difficult and dangerous to traverse. Fissure eruptions. Some of the largest and most important outflows of lava have not been connected with volcanic cones, but have been discharged from fissures, flooding the country far and wide with molten rock. Sheet after sheet of molten rock has been successively outpoured, and there have been built up, layer upon layer, plateaus of lava thousands of feet in thickness and many thousands of square miles in area. Iceland. This island plateau has been rent from time to time by fissures from which floods of lava have outpoured. In some instances the lava discharges along the whole length of the fissure, but more often only at certain points upon it. The Laki fissure, 20 miles long, was in eruption in 1783 for 7 months. The inundation of fluid rock which poured from it is the largest of historic record, reaching a distance of 47 miles and covering 220 square miles to an average depth of 100 feet. At the present time the fissure is traced by a line of several hundred insignificant mounds of fragmental materials, which mark where the lava issued. The distance to which the fissure eruptions of Iceland flow on slopes extremely gentle is noteworthy. One such stream is 90 miles in length, and another 70 miles long has a slope of little more than 1/2 a degree. Where lava is emitted at one point and flows to a less distance, there is gradually built up a dome of the shape of an inverted saucer with an immense base but comparatively low. Many lava domes have been discovered in Iceland, although from their exceedingly gentle slopes, often but 2 or 3 degrees, they long escaped the notice of explorers. The entire plateau of Iceland, a region as large as Ohio, is composed of volcanic products, for the most part of successive sheets of lava whose total thickness falls little short of 2 miles. The lava sheets exposed to view were outpoured in open air, and not beneath the sea, for peat bogs and old forest grounds are interbedded with them, and the fossil plants of these vegetable deposits prove that the plateau has long been building and is very ancient. On the steep sea cliffs of the island, where its structure is exhibited, the sheets of lava are seen to be cut with many dikes, fissures which have been filled by molten rock, and there is little doubt that it was through these fissures that the lava outwelled in successive flows, which spread far and wide over the country and gradually reared the enormous pile of the plateau. Eruptions of the explosive type. In the majority of volcanoes, the lava which rises in the pipe is at least in part blown into fragments with violent eruptions and shot into the air together with vast quantities of water vapor and various gases. The finer particles into which the lava is exploded are called volcanic dust or volcanic ashes, and are often carried long distances by the wind before they settle to the earth. The coarser fragments fall about the vent and there accumulate in a steep, conical, volcanic mountain. As successive explosions keep open the throat of the pipe, there remains on the summit a cup-shaped depression called the crater. Stromboli. To study the nature of these explosions we may visit Stromboli, a low volcano built chiefly of fragmental materials, which rises from the sea off the north coast of Sicily and is in constant though moderate action. Over the summit hangs a cloud of vapor which strikingly resembles the column of smoke puffed from the smokestack of a locomotive, in that it consists of globular masses, each the product of a distinct explosion. At night the cloud of vapor is lighted with a red glow at intervals of a few minutes, like the glow on the trail of smoke behind the locomotive when from time to time the fire box is opened. Because of this intermittent light flashing thousands of feet above the sea, Stromboli has been given the name of the lighthouse of the Mediterranean. Looking down into the crater of the volcano, one sees a viscid lava slowly seething. The agitation gradually increases. A great bubble forms. It bursts with an explosion which causes the walls of the crater to quiver with a miniature earthquake, and an outrush of steam carries the fragments of the bubble aloft for 1,000 feet, to fall into the crater or on the mountain side about it. With the explosion the cooled and darkened crust of the lava is removed, and the light of the incandescent liquid beneath is reflected from the cloud of vapor which overhangs the cone. At Stromboli we learn the lesson that the explosive force in volcanoes is that of steam. The lava in the pipe is permeated with it much as is a thick boiling porridge. The steam in boiling porridge is unable to escape freely, and gathers into bubbles, which in breaking spurt out drops of the pasty substance. In the same way, the explosion of great bubbles of steam in the viscid lava shoots clots and fragments of it into the air. Krakatoa. The most violent eruption of history, that of Krakatoa, a small volcanic island in the strait between Sumatra and Java, occurred in the last week of August, 1883. Continuous explosions shot a column of steam and ashes 17 miles in the air. A black cloud, beneath which was midnight darkness, and from which fell a rain of ashes and stones, overspread the surrounding region to a distance of 150 miles. Launched on the currents of the upper air, the dust was swiftly carried westward to long distances. 3 days after the eruption it fell on the deck of a ship 1,600 miles away, and in 13 days the finest impalpable powder from the volcano had floated around the globe. For many months the dust hung over Europe and America as a faint lofty haze illuminated at sunrise and sunset with brilliant crimson. In countries nearer the eruption, as in India and Africa, the haze for some time was so thick that it colored sun and moon with blue, green, and copper-red tints, and encircled them with coronas. At a distance of even 1,000 miles, the detonations of the eruption sounded like the booming of heavy guns a few miles away. In one direction they were audible for a distance as great as that from San Francisco to Cleveland. The entire atmosphere was thrown into undulations, under which all barometers rose and fell, as the air waves thrice encircled the earth. The shock of the explosions raised sea waves which swept round the adjacent shores at a height of more than 50 feet, and which were perceptible half way around the globe. At the close of the eruption, it was found that half the mountain had been blown away, and that where the central part of the island had been, the sea was 1,000 feet deep. Martinique and St. Vincent. In 1902, two dormant volcanoes in the West Indies, Mount Pelee in Martinique and Soufriere in St. Vincent, broke into eruption simultaneously. No lava was emitted, but there were blown into the air great quantities of ashes, which mantled the adjacent parts of the islands with a pall as of gray snow. In early stages of the eruption, lakes which occupied old craters were discharged and swept down the ash-covered mountain valleys in torrents of boiling mud. On several occasions there was shot from the crater of each volcano a thick and heavy cloud of incandescent ashes and steam, which rushed down the mountainside like an avalanche, red with glowing stones and scintillating with lightning flashes. Forests and buildings in its path were leveled as by a tornado. Wood was charred and set on fire by the incandescent fragments. All vegetation was destroyed, and to breathe the steam and hot suffocating dust of the cloud was death to every living creature. On the morning of the 8th of May, 1902, the first of these peculiar avalanches from Mount Pelee fell on the city of St. Pierre, and instantly destroyed the lives of its 30,000 inhabitants. The eruptions of many volcanoes partake of both the effusive and the explosive types. The molten rock in the pipe is in part blown into the air with explosions of steam, and in part is discharged in streams of lava over the lip of the crater and from fissures in the sides of the cone. Such are the eruptions of Vesuvius, one of which is illustrated in Figure 219. Submarine eruptions. The many volcanic islands of the ocean and the coral islands resting on submerged volcanic peaks prove that eruptions have often taken place upon the ocean floor and have there built up enormous piles of volcanic fragments and lava. The Hawaiian volcanoes rise from a depth of 18,000 feet of water and lift their heads to about 30,000 feet above the ocean bed. Christmas Island, see page 194, built wholly beneath the ocean, is a coral-capped volcanic peak, whose total height, as measured from the bottom of the sea, is more than 15,000 feet. Deep sea soundings have revealed the presence of numerous peaks which fail to reach sea level, and which no doubt are submarine volcanoes. A number of volcanoes on the land were submarine in their early stages, as, for example, the vast pile of Etna, the celebrated Sicilian volcano, which rests on stratified volcanic fragments containing marine shells now uplifted from the sea. Submarine outflows of lava and deposits of volcanic fragments become covered with sediments during the long intervals between eruptions. Such volcanic deposits are said to be contemporaneous, because they are formed during the same period as the strata among which they are embedded. Contemporaneous lava sheets may be expected to bake the surface of the stratum on which they rest, while the sediments deposited upon them are unaltered by their heat. They are among the most prominent records of volcanic action, far outlasting the greatest volcanic mountains built in open air. From upraised submarine volcanoes, such as Christmas Island, it is learned that lava flows which are poured out upon the bottom of the sea do not differ materially, either in composition or texture, from those of the land. Volcanic products. Vast amounts of steam are, as we have seen, emitted from volcanoes, and comparatively small quantities of other vapors, such as various acid and sulphurous gases. The rocks erupted from volcanoes differ widely in chemical composition and in texture. Acidic and basic lavas. Two classes of volcanic rocks may be distinguished: those containing a large proportion of silica, silicic acid, silicon dioxide, and therefore called acidic, and those containing less silica and a larger proportion of the bases, lime, magnesia, soda, etc., and therefore called basic. The acidic lavas, of which rhyolite and thrakite are examples, are comparatively light in color and weight and are difficult to melt. The basic lavas, of which basalt is a type, are dark and heavy and melt at a lower temperature. Scoria and pumice. The texture of volcanic rocks depends in part on the degree to which they were distended by the steam which permeated them when in a molten state. They harden into compact rock where the steam cannot expand. Where the steam is released from pressure, as on the surface of a lava stream, it forms bubbles, steam blebs, of various sizes, which give the hardened rock a cellular structure. Figure 220. In this way are formed the rough slags and clinkers called scoria, which are found on the surface of flows, and which are also thrown out as clots of lava in explosive eruptions. On the surface of the seething lava in the throat of the volcano there gathers a rock foam which, when hurled into the air, is cooled and falls as pumice, a spongy gray rock so light that it floats on water. Amygdules. The steam blebs of lava flows are often drawn out from a spherical to an elliptical form resembling that of an almond, and after the rock has cooled, these cavities are gradually filled with minerals deposited from solution by underground water. From their shape, such casts are called amygdules, Greek, amygdalon, and almond. Amygdules are commonly composed of silica. Lavas contain both silica and the alkalines, potash and soda, and after dissolving the alkalis, percolating water is able to take silica also into solution. Most agates are banded amygdules in which the silica has been laid in varicolored concentric layers. Glassy and stony lavas. Volcanic rocks differ in texture according to the rate at which they have solidified. When rapidly cooled, as on the surface of a lava flow, molten rock chills to a glass, because the minerals of which it is composed have not had time to separate themselves from the fused mixture and form crystals. Under slow cooling, as in the interior of the flow it becomes a stony mass composed of crystals set in a glassy paste. In thin slices of volcanic glass one may see under the microscope the beginnings of crystal growth in filaments and needles and feathery forms, which are the rudiments of the crystals of various minerals. Spherulites, which also mark the first changes of glassy lavas toward a stony condition, are little balls within the rock, varying from microscopic size to several inches in diameter, and made up of radiating fibers. Perlitic structure, common among glassy lavas, consists of microscopic curving and interlacing cracks, due to contraction. Flow lines are exhibited by volcanic rocks both to the naked eye and under the microscope. Steam blebs, together with crystals and their embryonic forms, are left arranged in lines and streaks by the currents of the flowing lava as it stiffened into rock. Porphyritic structure. Rocks whose ground mass has scattered through it large conspicuous crystals are said to be porphyritic, and it is especially among volcanic rocks that this structure occurs. The ground mass of porphyries either may be glassy, or may consist in part of a felt of miniature crystals. In either case, it represents the consolidation of the rock after its outpouring upon the surface. On the other hand, the large crystals of porphyry have slowly formed deep below the ground at an earlier date. Columnar structure. Just as wet starch contracts on drying to prismatic forms, so lava often contracts on cooling to a mass of close-set, prismatic, and commonly six-sided columns, which stand at right angles to the cooling surface. The upper portion of a flow, on rapid cooling from the surface exposed to the air, may contract to a confused mass of small and irregular prisms, while the remainder forms large and beautifully regular columns, which have grown upward by slow cooling from beneath. Fragmental materials. Rocks weighing many tons are often thrown from a volcano at the beginning of an outburst by the breaking up of solidified floor of the crater, and during the process of an eruption large blocks may be torn from the throat of the volcano by the outrush of steam. But the most important fragmental materials are those derived from the lava itself. As lava rises in the pipe, the steam which permeates it is released from pressure and explodes, hurling the lava into the air in fragments of all sizes. Large pieces of scoria, lapilli, fragments the size of a pea or walnut, volcanic sand, and volcanic ashes. The latter resemble in appearance the ashes of wood or coal, but they are not in any sense like them, a residue after combustion. Volcanic ashes are produced in several ways. Lava rising in the volcanic duct is exploded into fine dust by the steam which permeates it. Glassy lava, hurled into the air and cooled suddenly, is brought into a state of high strain and tension, and, like Prince Rupert's drops, flies to pieces at the least provocation. The clash of rising and falling projectiles also produces some dust, a fair sample of which may be made by grating together 2 pieces of pumice. Beds of volcanic ash occur widely among recent deposits in the western United States. In Nebraska, ash beds are found in 20 counties and are often as white as powdered pumice. The beds grow thicker and coarser toward the southwestern part of the state, where their thickness sometimes reaches 50 feet. In what direction would you look for the now extinct volcano whose explosive eruptions are thus recorded? Tuff. This is a convenient term designating any rock composed of volcanic fragments. Coarse tufts of angular fragments are called volcanic breccia, and when the fragments have been rounded and sorted by water, the rock is termed a volcanic conglomerate. Even when deposited in the open air, as on the slopes of a volcano, tuffs may be rudely bedded and their fragments more or less rounded, and unless marine shells, or the remains of land plants and animals, are found as fossils in them, there is often considerable difficulty in telling whether they were laid in water or in air. In either case, they soon become consolidated. Chemical deposits from percolating waters fill the interstices, and the bed of loose fragments is cemented to hard rock. The materials of which tuffs are composed are easily recognized as volcanic in their origin. The fragments are more or less cellular, according to the degree to which they were distended with steam when in a molten state, and even in the finest dust one may see the glass or the crystals of lava from which it was derived. Tuffs often contain volcanic bombs, balls of lava which took shape while whirling in the air, and solidified before falling to the ground. Ancient volcanic rocks. It is in these materials and structures which we have described that volcanoes leave some of their most enduring records. Even the volcanic rocks of the earliest geological ages, uplifted after long burial beneath the sea, and exposed to view by deep erosion, are recognized and their history read despite many changes which they may have undergone. A sheet of ancient lava may be distinguished by its composition from the sediments among which it is embedded. The direction of its flow lines may be noted. The cellular and slaggy surface where the pasty lava was distended by escaping steam is recognized by the amygdules which now fill the ancient steam blebs. In a pile of successive sheets of lava, each flow may be distinguished and its thickness measured, for the surface of each sheet is glassy and scoriaceous, while beneath its upper portions the lava of each flow is more dense and stony. The length of time which elapsed before a sheet was buried beneath the materials of succeeding eruptions may be told by the amount of weathering which it has undergone, the depth of ancient soil, now baked to solid rock, upon it, and the erosion which it had suffered in the interval. If the flow occurred from some submarine volcano, we may recognize the fact by the sea-laid sediments which cover it, filling the cracks and crevices of its upper surface, and containing pieces of lava washed from it in their basal layers. Long buried glassy lavas devitrify, or pass into a stony condition, under the unceasing action of underground waters. but their flow lines and perlitic and spherulitic structures remain to tell of their original state. Ancient tuffs are known by the fragmental character of their volcanic material, even though they have been altered to firm rock. Some remains of land animals and plants may be found embedded, to tell that the beds were laid in open air, while the remains of marine organisms would prove as surely that the tuffs were deposited in the sea. In these ways, ancient volcanoes have been recognized near Boston, in southeastern Pennsylvania, about Lake Superior, and in other regions of the United States. The life history of a volcano. The invasion of a region by volcanic forces is attended by movements of the crust heralded by earthquakes. A fissure or a pipe is opened and the building of the cone or the spreading of wide lava sheets is begun. Volcanic cones. The shape of a volcanic cone depends chiefly on the materials erupted. Cones made of fragments may have sides as steep as the angle of repose, which in the case of coarse scoria is sometimes as high as 30 or 40 degrees. At the base of the mountain the finer materials erupted are spread in more gentle slopes, and are also washed forward by rains and streams. The normal profile is thus a symmetric cone with a flaring base. Cones built of lava vary in form according to the liquidity of the lava. Domes of gentle slope, as those of Hawaii, for example, are formed of basalt, which flows to long distances before it congeals. When superheated and emitted from many vents, the easily melted lava builds great plateaus, such as that of Iceland. On the other hand, lavas less fusible, or poured out at a lower temperature, stiffen when they have flowed but a short distance, and accumulate in a steep cone. Trachyte has been extruded in a state so viscid that it has formed steep-sided domes like that of Sarcoe. Most volcanoes are built, like Vesuvius, both of lava flows and of tuffs, and sections show that the structure of the cone consists of outward dipping, alternating layers of lava, scoria, and ashes. From time to time the cone is rent by the violence of explosions, and by the weight of the column of lava in the pipe. The fissures are filled with lava, and some discharge on the sides of the mountain, building parasitic cones, while all form dikes, which strengthen the pile with ribs of hard rock and make it more difficult to rend. Great catastrophes are recorded in the shape of some volcanoes, which consist of a circular rim, perhaps miles in diameter, inclosing a vast crater or a caldera within which small cones may rise. We may infer that at some time the top of the mountain has been blown off, or has collapsed and has been engulfed because some reservoir beneath had been emptied by long continued eruptions. The cone building stage may be said to continue until eruptions of lava and fragmental materials cease altogether. Sooner or later the volcanic forces shift or die away, and no further eruptions add to the pile or replace its losses by erosion during periods of repose. Gases, however, are still emitted, and, as sulfur vapors are conspicuous among them, Such vents are called solfataras. Mount Hood, in Oregon, is an example of a volcano sunk to this stage. From a steaming rift on its side there rise sulphurous fumes which, half a mile down the wind, will tarnish a silver coin. Geysers and hot springs. The hot springs of volcanic regions are among the last vestiges of volcanic heat. Periodically eruptive boiling springs are termed geysers. In each of the geyser regions of the earth, the Yellowstone National Park, Iceland, and New Zealand, the groundwater of the locality is supposed to be heated by ancient lavas that, because of the poor conductivity of the rock, still remain hot beneath the surface. Old Faithful, one of the many geysers of the Yellowstone National Park, plays a fountain of boiling water 100 feet in air, while clouds of vapor from the escaping steam ascend to several times that height. The eruptions take place at intervals from 70 to 90 minutes. In repose, the geyser is a quiet pool, occupying a crater-like depression in a conical mound some 12 feet high. The conduit of the spring is too irregular to be sounded. The mound is composed of porous silica deposited by the waters of the geyser. Geysers erupt at intervals instead of continuously boiling, because their long, narrow, and often tortuous conduits do not permit a free circulation of the water. After an eruption the tube is refilled, and the water again gradually becomes heated. Deep in the tube, where it is in contact with hot lavas, the water sooner or later reaches the boiling point, and bursting into steam, shoots the water above it high in the air. Carbonated springs. After all the other signs of life have gone, the ancient volcano may emit carbon dioxide as its dying breath. The springs of the region may long be charged with carbon dioxide, or carbonated, and when they rise through limestone may be expected to deposit large quantities of travertine. We should remember, however, that many carbonated springs and many hot springs are wholly independent of volcanoes. The destruction of the cone. As soon as the volcanic cone ceases to grow by eruptions, the agents of erosion begin to wear it down, and the length of time that has elapsed since the period of active growth may be roughly measured by the degree to which the cone has been dissected. We infer that Mount Shasta, whose conical shape is still preserved despite the gullies 1,000 feet deep which trench its sides, is younger than Mount Hood, which erosive agencies have carved to a pyramidal form. The pile of materials accumulated about a volcanic vent, no matter how vast in bulk, is at last swept entirely away. The cone of the volcano, active or extinct, is not as old as the earth counts time. Volcanoes are short-lived geological phenomena. Crandall Volcano. This name is given to a dissected ancient volcano in the Yellowstone National Park, which once, it is estimated, reared its head thousands of feet above the surrounding country, and greatly exceeded in bulk either Mount Shasta or Mount Etna. Not a line of the original mountain remains. All has been swept away by erosion, except some 4,000 feet of the base of the pile. This basal wreck now appears as a rugged region about 30 miles in diameter, trenched by deep valleys and cut into sharp peaks and precipitous ridges. In the center of the area is found the nucleus (N, Fig. 237), a mass of coarsely crystalline rock that congealed deep in the old volcanic pipe. From it there radiate in all directions, like the spokes of a wheel, long dikes whose rock grows rapidly finer of grain as it leaves the vicinity of the once heated core. The remainder of the base of the ancient mountain is made of rudely bedded tuffs and volcanic breccia, with occasional flows of lava, some of the fragments of the breccia measuring as much as 20 feet in diameter. On the sides of cañons the breccia is carved by rain erosion to fantastic pinnacles. At different levels in the midst of these beds of tuff and lava are many old forest grounds. The stumps and trunks of the trees, now turned to stone, still in many cases stand upright, where once they grew on the slopes of the mountain as it was building. Figure 238. The great size and age of some of these trees indicate the lapse of time between the eruption whose lavas or tuffs weathered to the soil on which they grew, and the subsequent eruption which buried them beneath showers of stones and ashes. Near the edge of the area lies Death Gulch, in which carbon dioxide is given off in such quantities that in quiet weather it accumulates in a heavy layer along the ground and suffocates the animals which may enter it. End of section 17. Section 18 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, July 2010. The Elements of Geology by William Harmon Norton. Chapter 12. Underground Structures of Igneous Origin. It is because long-continued erosion lays bare the innermost anatomy of an extinct volcano, and even sweeps away the entire pile with much of the underlying strata, thus leaving the very roots of the volcano open to view, that we are able to study underground volcanic structures. With these we include, for convenience, intrusions of molten rock, which have been driven upward into the crust, but which may not have succeeded in breaking way to the surface and establishing a volcano. All these structures are built of rock forced when in a fluid or pasty state into some cavity which it has found or made, and we may classify them therefore according to the shape of the molds in which the molten rock has congealed, as 1. Dikes, 2. Volcanic necks, 3. Intrusive sheets, and 4. Intrusive masses. Dikes. The sheet of once molten rock with which a fissure has been filled is known as a dike. Dikes are formed when volcanic cones are rent by explosions, or by the weight of the lava column in the duct, and on the dissection of the pile they appear as radiating vertical ribs cutting across the layers of lava and tuff of which the cone is built. In regions undergoing deformation, rocks lying deep below the ground are often broken, and the fissures are filled with molten rock from beneath, which finds no outlet to the surface. Such dikes are common in areas of the most ancient rocks, which have been brought to light by long erosion. In exceptional cases, dikes may reach the length of 50 or 100 miles. They vary in width from a fraction of a foot to even as much as 300 feet. Dikes are commonly more fine of grain on the sides than in the center, and may have a glassy and cracked surface where they meet the inclosing rock. Can you account for this on any principle which you have learned? Volcanic necks. The pipe of a volcano rises from far below the base of the cone, from the deep reservoir from which its eruptions are supplied. When the volcano has become extinct, this great tube remains filled with hardened lava. It forms a cylindrical core of solid rock, except for some distance below the ancient crater, where it may contain a mass of fragments which had fallen back into the chimney after being hurled into the air. As the mountain is worn down, this central column, known as the volcanic neck, is left standing as a conical hill. Figure 240. Even when every other trace of the volcano has been swept away, erosion will not have passed below this great stalk on which the volcano was born as a fiery flower whose site it remains to mark. In volcanic regions of deep denudation, volcanic necks rise solitary and abrupt from the surrounding country as dome-shaped hills. They are marked features in the landscape in parts of Scotland and in the St. Lawrence Valley about Montreal. Figure 241. Intrusive sheets. Sheets of igneous rocks are sometimes found interleaved with sedimentary strata, especially in regions where the rocks have been deformed and have suffered from volcanic action. In some instances such a sheet is seen to be contemporaneous (page 248). In other instances the sheet must be intrusive. The overlying stratum, as well as that beneath, has been affected by the heat of the once molten rock. We infer that the igneous rock when in a molten state was forced between the strata much as a card may be pushed between the leaves of a closed book. The liquid wedged its way between the layers, lifting those above to make room for itself. The source of the intrusive sheet may often be traced to some dike, known therefore as the feeding dike, or to some mass of igneous rock. Intrusive sheets may extend a score and more of miles, and, like the longest surface flows, the most extensive sheets consist of the more fusible and fluid lavas, those of the basic class, of which basalt is an example. Intrusive sheets are usually harder than the strata in which they lie, and are therefore often left in relief after long denudation of the region. Figure 315. On the west bank of the Hudson there extends from New York Bay north for 30 miles a bold cliff several hundred feet high, the Palisades of the Hudson. It is the outcropping edge of a sheet of ancient igneous rock which rests on stratified sandstones and is overlain by strata of the same series. Sandstones and lava sheet together dip gently to the west, and the latter disappears from view 2 miles back from the river. It is an interesting question whether the Palisades sheet is contemporaneous or intrusive. Was it outpoured on the sandstones beneath it when they formed the floor to the sea, and covered forthwith by the sediments of the strata above, or was it intruded among these beds at a later date? The latter is the case, for the overlying stratum is intensely baked along the zone of contact. At the west edge of the sheet is found the dike in which the lava rose to force its way far and wide between the strata. Electric Peak, one of the prominent mountains of the Yellowstone National Park, is carved out of a mass of strata into which many sheets of molten rock have been intruded. The western summit consists of such a sheet several hundred feet thick. Studying the section of Figure 244, what inference do you draw as to the source of these intrusive sheets? Intrusive masses. Bosses. This name is generally applied to huge irregular masses of coarsely crystalline igneous rock lying in the midst of other formations. Bosses vary greatly in size and may reach scores of miles in extent. Seldom are there any evidences found that bosses ever had connection with the surface. On the other hand, it is often proved that they have been driven, or have melted their way, upward into the formations in which they lie, for they give off dikes and intrusive sheets, and have profoundly altered the rocks about them by their heat. The texture of the rock of bosses proves that consolidation proceeded slowly and at great depths, and it is only because of vast denudation that they are now exposed to view. Bosses are commonly harder than the rocks about them, and stand up, therefore, as rounded hills and mountainous ridges, long after the surrounding country has worn to a low plain. The base of bosses is indefinite or undetermined, and in this respect they differ from laccoliths. Some bosses have broken and faulted the overlying beds, some have forced the rocks aside and melted them away. The Spanish peaks of southeastern Colorado were formed by the upthrust of immense masses of igneous rock, bulging and breaking the overlying strata. On one side of the mountains the throw of the fault is nearly a mile, and fragments of deep-lying beds were dragged upwards by the rising masses. The adjacent rocks were altered by the heat to a distance of several thousand feet. No evidence appears that the molten rock ever reached the surface, and if volcanic eruptions ever took place, either in lava flows or fragmental materials, all traces of them have been effaced. The rock of the intrusive masses is coarsely crystalline, and no doubt solidified slowly under the pressure of vast thicknesses of overlying rock, now mostly removed by erosion. A magnificent system of dikes radiates from the peaks to a distance of 15 miles, some now being left by long erosion as walls 100 feet in height. Figure 239. Intrusive sheets fed by the dikes penetrate the surrounding strata, and their edges are cut by cañons as much as 25 miles from the mountain. In these strata are valuable beds of lignite, an imperfect coal, which the heat of dikes and sheets has changed to coke. Laccoliths. The laccolith (Greek lakos, cistern, lithos, stone) is a variety of intrusive masses in which molten rock has spread between the strata, and, lifting the strata above it to a dome-shaped form, has collected beneath them in a lens-shaped body with a flat base. The Henry Mountains, a small group of detached peaks in southern Utah, rise from a plateau of horizontal rocks. Some of the peaks are carved wholly in separate dome-like uplifts of the strata of the plateau. In others, as Mount Hillers, the largest of the group, there is exposed on the summit a core of igneous rock from which the sedimentary rocks of the flanks dip steeply outward in all directions. In still others, erosion has stripped off the covering strata and has laid bare the core to its base, and its shape is here seen to be that of a plano-convex lens or a baker's bun, its flat base resting on the undisturbed bedded rocks beneath. The structure of Mount Hillers is shown in Figure 248. The nucleus of igneous rock is 4 miles in diameter and more than a mile in depth. Regional intrusions. These vast bodies of igneous rock, which may reach hundreds of miles in diameter, differ little from bosses except in their immense bulk. Like bosses, regional intrusions give off dikes and sheets and greatly change the rocks about them by their heat. They are now exposed to view only because of the profound denudation which has removed the upheaved dome of rocks beneath which they slowly cooled. Such intrusions are accompanied, whether as a cause or as effect is still hardly known, by deformations, and their masses of igneous rock are thus found as the core of many great mountain ranges. The granitic masses of which the Bitter Root Mountains and the Sierra Nevadas have been largely carved are each more than 300 miles in length. Immense regional intrusions, the cores of once lofty mountain ranges, are found upon the Laurentian peneplain. Physiographic effects of intrusive masses. We have already seen examples of the topographic effects of intrusive masses in Mount Hillers, the Spanish peaks, and in the great mountain ranges mentioned in the paragraph on regional intrusions, although in the latter instances these effects are entangled with the effects of other processes. Masses of igneous rock cannot be intruded within the crust without an accompanying deformation on a scale corresponding to the bulk of the intruded mass. The overlying strata are arched into hills or mountains, or, if the molten material is of great extent, the strata may conceivably be floated upward to the height of a plateau. We may suppose that the transference of molten matter from one region to another may be among the causes of slow subsidences and elevations. Intrusions give rise to fissures, dikes, and intrusive sheets, and these dislocations cannot fail to produce earthquakes. Where intrusive masses open communication with the surface, volcanoes are established, or fissure eruptions occur such as those of Iceland. The intrusive rocks. The igneous rocks are divided into two general classes, the volcanic or eruptive rocks, which have been outpoured in open air or on the floor of the sea, and the intrusive rocks, which have been intruded within the rocks of the crust and have solidified below their surface. These two classes are alike in chemical composition and may be divided into acidic and basic groups. In texture, The intrusive rocks differ from the volcanic rocks because of the different conditions under which they have solidified. They cooled far more slowly beneath the cover of the rocks into which they were pressed than is permitted to lava flows in open air. Their constituent materials had ample opportunity to sort themselves and crystallize from the fluid mixture, and none of that mixture was left to congeal as a glassy paste. They consolidated also under pressure. They are never scoriaceous, for the steam with which they were charged was not allowed to expand and distend them with steam blebs. In the rocks of the larger intrusive masses one may see with a powerful microscope exceedingly minute cavities, to be counted by many millions to the cubic inch, in which the gaseous water which the mass contained was held imprisoned under the immense pressure of the overlying rocks. Naturally, these characteristics are best developed in the intrusives which cooled most slowly, i.e. in the deepest seated and largest masses, while in those which cooled more rapidly, as in dikes and sheets, we find gradations approaching the texture of surface flows. Varieties of the intrusive rocks. We will now describe a few of the varieties of rocks of deep-seated intrusions. All are even-grained, consisting of a mass of crystalline grains formed during one continuous stage of solidification, and no porphyritic crystals appear as in lavas. Granite, as we have learned already, is composed of three minerals, quartz, feldspar, and mica. According to the color of the feldspar the rock may be red or pink or gray. Hornblende, a black or dark green material, an iron magnesian silicate, about as hard as feldspar, is sometimes found as a fourth constituent, and the rock is then known as hornblendic granite. Granite is an acidic rock corresponding to rhyolite in chemical composition. We may believe that the same molten mass which supplies this acidic lava in surface flows solidifies as granite, deep below the ground in the volcanic reservoir. Syenite, composed of feldspar and mica, has consolidated from a less siliceous mixture than has granite. Diorite, still less siliceous, is composed of hornblende and feldspar, the latter mineral being of different variety from the feldspar of granite and syenite. Gabbro, a typical basic rock, corresponds to basalt in chemical composition. It is a dark, heavy, coarsely crystalline aggregate of feldspar and augite, a dark mineral allied to hornblende. It often contains magnetite, the magnetic black oxide of iron, and olivine, a greenish magnesian silicate. In the northern states all these types, and many others also of vast number of varieties of intrusive rocks, can be found among the rocks of the drift brought from the areas of igneous rock in Canada and the states of our northern border. Summary. The records of geology prove that since the earliest of their annals tremendous forces have been active in the earth. In all the past, under pressures inconceivably great, molten rock has been driven upward into the rocks of the crust. It has squeezed into fissures forming dikes. It has burrowed among the strata as intrusive sheets. It has melted the rocks away or lifted the overlying strata, filling the chambers which it has made with intrusive masses. During all geological ages, molten rock has found way to the surface, and volcanoes have darkened the sky with clouds of ashes and poured streams of glowing lava down their sides. The older strata, the strata which have been most deeply buried, and especially those which have suffered most from folding and from fracture, show the largest amount of igneous intrusions. The molten rock which has been driven from the earth's interior to within the crust or to the surface during geologic time must be reckoned in millions of cubic miles. The interior condition of the earth and causes of volcanism and deformation. The problems of volcanoes and of deformation are so closely connected with that of the earth's interior that we may consider them together. Few of these problems are solved, and we may only state some known facts and the probable conclusions which may be drawn as inferences from them. The interior of the earth is hot. Volcanoes prove that in many parts of the earth there exist within reach of the surface regions of such intense heat that the rock is in a molten condition. Deep wells and mines show everywhere an increase in temperature below the surface shell, affected by the heat of summer and the cold of winter. A shell in temperate latitudes 60 or 70 feet thick. Thus in a boring more than a mile deep at Schlotterbach, Germany, the earth grows warmer at the rate of 1° Fahrenheit for every 67 feet as we descend. Taking the average rate of increase at 1° for every 60 feet of descent, and assuming that this rate, observed at the moderate distances open to observation, continues to at least 35 miles, the temperature at that depth must be more than 3,000 degrees, a temperature at which all ordinary rocks would melt at the earth's surface. The rate of increase in temperature probably lessens as we go downwards, and it may not be appreciable below a few hundred miles. But there is no reason to doubt that the interior of the earth is intensely hot. Below a depth of 1 or 2 score miles, we may imagine the rocks everywhere glowing with heat. Although the heat of the interior is great enough to melt all rocks at atmospheric pressure, it does not follow that the interior is fluid. Pressure raises the fusing point of rocks, and the weight of the crust may keep the interior in what may be called a solid state, although so hot as to be a liquid or a gas were the pressure to be removed. The interior of the earth is rigid and heavy. The earth behaves as a globe more rigid than glass under the attractions of the sun and moon. It is not deformed by these stresses as is the ocean in the tides, proving that it is not a fluid ball covered with a yielding crust a few miles thick. Earthquakes pass through the earth faster than they would were it of solid steel. Hence the rocks of the interior are highly elastic, being brought by pressure to a compact, continuous condition unbroken by the cracks and vesicles of surface rocks. The interior of the earth is rigid. The common rocks of the crust are about 2½ times heavier than water, while the earth as a whole weighs 5 6/10 times as much as a globe of water the same size. The interior is therefore much more heavy than the crust. This may be caused in part by compression of the interior under the enormous weight of the crust, and in part, also, by an assortment of material, the heavier substances, such as the heavy metals, having gravitated towards the center. Between the crust, which is solid because it is cool, and the interior, which is hot enough to melt were it not for the pressure which keeps it dense and rigid, there may be an intermediate zone in which heat and pressure are so evenly balanced that here rock liquefies whenever and wherever the pressure upon it may be relieved by movements of the crust. It is perhaps from such a subcrustal layer that the lava of volcanoes is supplied. The causes of volcanic action. It is now generally believed that the heat of volcanoes is that of the earth's interior. Other causes, such as friction and crushing in, the making of mountains, and the chemical reactions between oxidizing agents of the crust and the unoxidized interior, have been suggested, but to most geologists they seem inadequate. There is much difference of opinion as to the force which causes molten rock to rise to the surface in the ducts of volcanoes. Steam is so evidently concerned in explosive eruptions that many believe that lava is driven upward by the expansive force of the steam with which it is charged, much as a viscid liquid rises and boils over in a test tube or kettle. But in quiet eruptions, and still more in the eruption of intrusive sheets and masses, there is little if any evidence that steam is the driving force. It is therefore believed by many geologists that it is pressure due to crustal movements and internal stresses which squeezes molten rock from below into fissures and ducts in the crust. It is held by some that where considerable water is supplied to the rising column of lava, as from the groundwater of the surrounding region, and where the lava is viscid so that steam does not readily escape, the eruption is of the explosive type. When these conditions do not obtain, the lava outwells quietly, as in the Hawaiian volcanoes. It is held by others not only that volcanoes are due to the outflow of the earth's deep-seated heat, but also that the steam and other emitted gases are for the most part native to the earth's interior, and never have had place in the circulation of atmospheric and ground waters. Volcanic action and deformation. Volcanoes do not occur on wide plains or among ancient mountains. On the other hand, where movements of the earth's crust are in progress in the uplift of high plateaus, and still more in mountain making, molten rock may reach the surface, or may be driven upward toward it, forming great intrusive masses. Thus extensive lava flows accompanied the upheaval of the block mountains of western North America and the uplift of the Colorado Plateau. A line of recent volcanoes may be traced along the system of rift valleys which extends from the Jordan and Dead Sea through eastern Africa to Lake Nyassa. The volcanoes of the Andes show how conspicuous volcanic action may be in young rising ranges. Folded mountains often show a core of igneous rock, which by long erosion has come to form the axis and the highest peaks of the range, as if the molten rock had been squeezed up under the rising upfolds. As we decipher the records of the rocks in historical geology, we shall see more fully how, in all the past, volcanic action has characterized these periods of great crustal movements, and how it has been absent when and where the earth's crust has remained comparatively at rest. The causes of deformation. As the earth's interior, or nucleus, is highly heated, it must be constantly though slowly losing its heat by conduction through the crust and into space. And since the nucleus is cooling, it must also be contracting. The nucleus has contracted also because of the extrusion of molten matter, the loss of constituent gases given off in volcanic eruptions, and, still more important, the compression and consolidation of its material under gravity. As the nucleus contracts, it tends to draw away from the cooled solid crust, and the latter settles, adapting itself to the shrinking nucleus much as the skin of a withering apple wrinkles down upon the shrunken fruit. The unsupported weight of the spherical crust develops enormous tangential pressures similar to the stresses of an arch or dome, and when these lateral thrusts accumulate beyond the power of resistance, the solid rock is warped and folded and broken. Since the planet attained its present mass, it has thus been lessening in volume. Notwithstanding local and relative upheavals, the earth's surface on the whole has drawn nearer and nearer to the center. The portions of the lithosphere which have been carried down the farthest have received the waters of the oceans, while those portions which have been carried down the least have emerged as continents. Although it serves our convenience to refer the movements of the crust to the sea level as datum plane, it is understood that this level is by no means fixed. Changes in the ocean basins increase or reduce their capacity, and thus lower or raise the level of the sea. But since these basins are connected, the effect of any change upon the water level is so distributed that it is far less noticeable than a corresponding change would be upon the land. End of section 18.
Section 19 of the Element of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Elements of Geology by William Harmon Norton. Chapter 13. Metamorphism and Mineral Veins. Under the action of internal agencies, rocks of all kinds may be rendered harder, more firmly cemented, and more crystalline. These processes are known as metamorphism, and the rocks affected, whether originally sedimentary or igneous, are called metamorphic rocks. We may contrast with metamorphism the action of external agencies in weathering, which render rocks less coherent by dissolving their soluble parts and breaking down their crystalline grains. Contact metamorphism. Rocks beneath a lava flow or in contact with igneous intrusions are found to be metamorphosed to various degrees by the heat of the cooling mass. The adjacent strata may be changed only in color, hardness, and texture. Thus, next to a dike, bituminous coal may be baked to coke or anthracite, and chalk and limestone to crystalline marble. Sandstone may be converted into quartzite, and shale into argillite, a compact, massive clay rock. New minerals may also be developed. In sedimentary rocks there may be produced crystals of mica and of garnet, a mineral as hard as quartz, commonly occurring in red, 12-sided crystals. Where the changes are most profound, rocks may be wholly made over in structure and mineral composition. In contact metamorphism, thin sheets of molten rock produce less effect than thicker ones. The strongest heat effects are naturally caused by bosses and regional intrusions, and the zone of change about them may be several miles in width. In these changes, heated waters and vapors from the masses of igneous rocks undoubtedly played a very important part. Which will be more strongly altered, the rocks about a closed dike in which lava began to cool as soon as it filled the fissure, or the rocks about a dike which opened on the surface and through which the molten rock flowed for some time? Taking into consideration the part played by heated waters, which will produce the most far-reaching metamorphism, dikes which cut across the bedding planes or intrusive sheets which are thrust between the strata. Taking into consideration the part played by heated waters, which will produce the most far-reaching metamorphism, dikes which cut across the bedding planes or intrusive sheets which are thrust between the strata. Regional metamorphism. Metamorphic rocks occur widespread in many regions, often hundreds of square miles in area, where such extensive changes cannot be accounted for by igneous intrusions. Such are the dissected cores of lofty mountains, as the Alps, and the worn-down bases of ancient ranges, as in New England, large areas in the Piedmont belt, and in the Laurentian peneplain. In these regions the rocks have yielded to immense pressure. They have been folded, crumpled, and mashed, and even their minute grains, as one may see with a microscope, have often been puckered, broken, and crushed to powder. It is to these mechanical movements and strains which the rocks have suffered in every part that we may attribute their metamorphism, and the degree to which they have been changed is in direct proportion to the degree which they have been deformed and mashed. Other factors, however, have played important parts. Rock crushing develops heat, and allows a freer circulation of heated waters and vapors. Thus chemical reactions are greatly quickened. Minerals are dissolved and redeposited in new positions, or their chemical constituents may recombine in new minerals. Entirely changing the nature of the rock is when, for example, feldspar recrystallizes as quartz and mica. Early stages of metamorphism are seen in slate. Pressure has hardened the marine muds, the arkose, or the volcanic ash from which slates are derived, and has caused them to cleave by the rearrangement of their particles. Under somewhat greater pressure, slate becomes phyllite, a clay slate whose cleavage surfaces are lustrous with flat-lying mica flakes. The same pressure which has caused the rock to cleave has set free some of its mineral constituents along the cleavage planes to crystallize there as mica. Foliation. Under still stronger pressure, the whole structure of the rock is altered. The minerals of which it is composed, and the new minerals which develop by heat and pressure, arrange themselves along planes of cleavage, or shear and rudely parallel leaves, or folia. Of this structure, called foliation, we may distinguish two types, a coarser feldspathic type, and a fine type in which other minerals than feldspar predominate. Gneiss is the general name under which are comprised coarsely foliated rocks banded with irregular layers of feldspar and other minerals. The gneisses appear to be due in many cases to the crushing and shearing of deep-seated igneous rocks such as granite and gabbro. The crystalline schists, representing the finer types of foliation, consist of thin parallel crystalline leaves, which are often remarkably crumpled. These folia can be distinguished from the laminate of sedimentary rocks by their lenticular form and lack of continuity, and especially by the fact that they consist of platy, crystalline grains, and not of particles rounded by wear. Mica schist, the most common of schists, and in fact of all metamorphic rocks, is composed of mica and quartz and alternating wavy folia. All gradations between it and phyllite may be traced, and in many cases we may prove it due to metamorphism of slates and shales. It is widespread in New England and along the eastern side of the Appalachians. Talc schist consists of quartz and talc, a light-colored magnesian mineral of greasy feel, and so soft that it can be scratched with a thumbnail. Hornblende schist, resulting in many cases from the foliation of basic igneous rocks, is made of the folia of hornblende alternating with bands of quartz and feldspar. Hornblende schist is common over large areas in the Lake Superior region. Quartz schist is produced from quartzite by the development of fine folia mica along planes of shear. All gradations may be found between it and unfoliated quartzite on the one hand and mica schist on the other. Under the resistless pressure of crustal movements, almost any rocks, sandstones, shales, lavas of all kinds, granites, diorites, and gabbros may be metamorphosed into schists by crushing and shearing. Limestones, however, are metamorphosed by pressure into marble, the grains of carbonate of lime recrystallizing freely to interlocking crystals of calcite. These few examples must suffice of the great class of metamorphic rocks. As we have seen, they owe their origin to the alteration of both of the other classes of rocks, the sedimentary and igneous, by heat and pressure, assisted usually by the presence of water. The fact of change is seen in their hardness, arid cementation, their more or less complete recrystallization, and their foliation. But the change is often so complete that no trace of their original structure and mineral composition remains to tell whether the rocks from which they were derived were sedimentary or igneous, or to what variety of either of these classes they belonged. In many cases, however, the early history of a metamorphic rock can be deciphered. Fossils not wholly obliterated may prove it originally water-laid. Schists may contain rolled-out pebbles, showing their derivation from a conglomerate. Dikes of igneous rocks may be followed into a region where they have been foliated by pressure. The most thoroughly metamorphosed rocks may sometimes be traced out into unaltered sedimentary or igneous rocks, or among them may be found patches of little change where their history may be read. Metamorphism is most common among rocks of the earlier geological ages, and most rare among rocks of recent formation. No doubt it is now in progress where deep-buried sediments are invaded by heat either from intrusive igneous masses or from the Earth's interior, or are suffering slow deformation under thrust of mountain-making forces. Suggest how rocks in process of metamorphism may sometimes be exposed to view. Why do metamorphic rocks appear on the surface today? Mineral veins. In regions of folded and broken rocks, fissures are frequently found to be filled with sheets of crystalline minerals deposited from solution by underground water, and fissures thus filled are known as mineral veins. Much of the importance of mineral veins is due to the fact that they are often metalliferous, carrying valuable native metals and metallic ores disseminated in fine particles, in strings, and sometimes in large masses in the midst of valueless non-metallic minerals, which make up what is known as the vein stone. The most common vein stones are quartz and calcite, fluorite, calcium fluoride, a mineral harder than calcite and crystallizing in cubes of various colors, and barite, barium sulfate, a heavy white mineral, are abundant in many veins. The gold-bearing quartz veins of California traverse the metamorphic slates of the Sierra Nevada mountains. Below the zone of solution, page 45, these veins consist of a vein stone of quartz mingled with pyrite, page 13, the latter containing threads and grains of native gold. But to the depth of about 50 feet from the surface, the pyrite of the vein has been dissolved, leaving a rusty cellular quartz with grains of insoluble gold scattered through it. The placer deposits of California and other regions are gold-bearing deposits of gravel and sand in riverbeds. The heavy gold is apt to be found mostly near or upon the solid rock, and its grains, like those of the sand, are always rounded. How the gold came in the placers we may leave to the pupil to suggest. Copper is found in a number of ores, and also in the native metal. Below the zone of surface changes, the ore of a copper vein is often a double sulfide of iron and copper called chalcopyrite. A mineral softer than pyrite, it can easily be scratched with a knife, and deeper yellow in color. For several score of feet below the ground, the vein may consist of rusty quartz, from which the metallic ores have been dissolved. But at the base of the zone of solution, we may find exceedingly rich deposits of copper ores, copper sulfides, red and black copper oxides, and green and blue copper carbonates, which have clearly been brought down in solution from the leached upper portion of the vein. Origin of mineral veins. Both vein stones and ores have been deposited slowly from solution in water, much as crystals of salt are deposited on the sides of a jar of saturated brine. In our study of underground water, we learned that it is everywhere circulating through the permeable rocks of the crust, descending to profound depths under the action of gravity and again driven to the surface by hydrostatic pressure. Now fissures, wherever they occur, form the trunk channels of the underground circulation. Water descends from the surface along these rifts. It moves laterally from either side to the fissure plane, just as groundwater seeps through the surrounding rocks from every direction to a well, and it ascends through these natural waterways as in an artesian well, whenever they intersect an aquifer in which water is under hydrostatic pressure. The waters which deposit vein stones and ores are commonly hot, and in many cases they have derived their heat from intrusions of igneous rocks still uncooled within the crust. The solvent power of the water is thus greatly increased, and it takes up into solution various substances from the igneous and sedimentary rocks which it traverses. For various reasons, these substances stances are deposited in the vein as ores and vein stones. On rising through the fissure, the water cools and loses pressure, and its capacity to hold minerals in solution is therefore lessened. Besides, as different currents meet in the fissure, some ascending, some descending, and some coming in from the sides, the chemical reaction of these various weak solutions upon one another and upon the walls of the vein precipitates the minerals of vein stuffs and ores. As an illustration of the method of vein deposits, we may cite the case of a wooden box pipe used in the Comstock mines, Nevada, to carry the hot water of the mine from one level to another, which in 10 years was lined with calcium carbonate more than a half-inch thick. The Steamboat Springs, Nevada, furnish examples of mineral veins in process of formation. The steaming water rises through fissures in volcanic rocks and is now depositing in the rifts a vein stone of quartz, with metallic ores of iron, mercury, lead, and other metals. Reconcentration. Near the base of the zone of solution, veins are often stored with exceptionally large and valuable ore deposits. This local enrichment of the vein is due to the reconcentration of the metalliferous ores. As the surface of the land is slowly lowered by weathering and running water, the zone of solution is lowered at an equal rate and encroaches constantly on the zone of cementation. The minerals of veins are therefore constantly being dissolved along their upper portions and carried down the fissures by groundwater to lower levels, where they are redeposited. Many of the richest ore deposits are thus due to successive concentrations. The ores were leached originally from the rocks to a large extent by laterally seeping waters. They were concentrated in the ore deposits of the vein chiefly by ascending currents. They have been reconcentrating by descending waters in the way just mentioned. The origin source of the metals. It is to the igneous rocks that we may look for the origin source of the metals of veins. Lavas contain minute percentages of various metallic compounds, and no doubt this was the case also with the igneous rocks which formed the original earth crust. By the erosion of the igneous rocks, the metals have been distributed among sedimentary strata, and even the sea has taken into solution an appreciable amount of gold and other metals, but in this widely diffuse condition they are wholly useless to man. The concentration which has made them available is due to the interaction of many agencies. Earth movements fracturing deeply the rocks of the crust, the intrusion of heated masses, the circulation of underground waters have all cooperated in the concentration of the metals of mineral veins. While fissure veins are the most important mineral veins, the latter term is applied also to any water which has been filled with similar deposits from solution. Thus insoluble rocks, such as limestones, joints enlarged by percolating water, are sometimes filled with metalliferous deposits, as, for example, the lead and zinc deposits of the upper Mississippi Valley. Even a porous aquifer may be made the seat of mineral deposits, as in the case of some copper-bearing and silver-bearing sandstones of New Mexico. End of section 19, recorded by Andrew Nelson, Atlanta, Georgia.
Section 20 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Elements of Geology by William Harmon Norton. Part 3. Historical Geology. Chapter 14. The Geological Record. What a formation records. We have already learned that each individual body of stratified rock, or formation, constitutes a record of the time when it was laid. The structure and the character of the sediments of each formation tell whether the area was land or sea at the time when they were spread, and if the former, whether the land was river plain or lake bed, or was covered with wind-blown sands, or by the deposits of an ice sheet. If the sediments are marine, we may know also whether they were laid in shoal water near the shore, or in deeper water out at sea, and whether during a period of emergence, or during a period of subsidence, when the sea transgressed the land. By the same means, each formation records the stage in the cycle of erosion of the land mass from which its sediments were derived. An unconformity between two marine formations records the fact that between the periods when they were deposited in the sea, the area emerged as land and suffered erosion. The attitude and structure of the strata tell also of the foldings and fractures, the deformation and metamorphism which they have suffered, and the igneous rocks associated with them as lava flows and igneous intrusions add other details to the story. Each formation is thus a separate local chapter in the geological history of the earth, and its strata are its leaves. It contains an authentic record of the physical conditions, the geography, of the time and place when and where its sediments were laid. Past cycles of erosion. These chapters in the history of the planet are very numerous, although much of the record has been destroyed in various ways. A succession of different formations is usually seen in any considerable section of the crust, such as a deep canyon or where the edges of upturned strata are exposed to view on the flanks of mountain ranges, and in any extensive area, such as a state of the Union or a province of Canada, the number of formations outcropping on the surface is large. It is thus learned that our present continent is made up for the most part of old continental deltas. Some, recently emerged as the strata of young coastal plains, are the records of recent cycles of erosion, while others were deposited in the early history of the earth, and in many instances have been crumpled into mountains, which afterwards were leveled to their bases and lowered beneath the sea to receive a cover of later sediments before they were again uplifted to form land. The cycle of erosion now in progress and recorded in the layers of the stratified rock being spread beneath the sea in continental deltas has therefore been preceded by many similar cycles. Again and again movements of the crust have brought to an end one cycle, sometimes when only well under way, and sometimes when drawing toward its close, and have begun another. Again and again they have added to the land areas which before were sea, with all their deposition records of earlier cycles, or have lowered areas of land beneath the sea to receive new sediments. The age of the earth. The thickness of the stratified rocks now exposed upon the eroded surface of the continents is very great. In the Appalachian region the strata are 7 or 8 miles thick, and still greater thicknesses have been measured in several other mountain ranges. The aggregate thickness of all the formations of the stratified rocks of the earth's crust, giving to each formation its maximum thickness wherever found, amounts to not less than 40 miles. Knowing how slowly sediments accumulate upon the sea floor, we must believe that the successive cycles which the earth has seen stretch back into a past almost inconceivably remote, and measure tens of millions and perhaps even hundreds of millions of years. How the formations are correlated and the geological record made up. Arranged in the order of their succession, the formations of the earth's crust would constitute a connected record in which the geological history of the planet may be read, and therefore known as the geological record. But to arrange the formations in their natural order is not an easy task. A complete set of the volumes of the record is to be found in no single region. Their leaves and chapters are scattered over the land surface of the globe. In one area certain chapters may be found, though perhaps with many missing leaves, and with intervening chapters wanting, and these absent parts perhaps can be supplied only after long search through many other regions. Adjacent strata in any region are arranged according to the law of superposition. That is, any stratum is younger than that on which it was deposited, just as in a pile of paper, any sheet was laid later than that on which it rests. Where rocks have been disturbed, their original attitude must be determined before the law can be applied. Nor can the law of superposition be used in identifying and comparing the strata of different regions, where the formations cannot be traced continuously from one region to the other. The formations of different regions are arranged in their true order by the law of included organisms, that is, formations, however widely separated, which contain a similar assemblage of fossils, are equivalent and belong to the same division of geological time. The correlation of formations by means of fossils may be explained by the formations now being deposited about the North Atlantic. Lithologically, they are extremely various. On the continental shelf of North America, limestones of different kinds are forming off Florida, and sandstones and shales from Georgia northward. Separated from them by the deep Atlantic oozes are other sedimentary deposits now accumulating along the west coast of Europe. If now all these offshore formations were raised to open air, how could they be correlated? Surely not by lithological likeness, for in this respect they would be quite diverse. All would be similar, however, in the fossils which they contain. Some fossil species would be identical in all these formations, and others would be closely allied. Making all due allowance for differences in species due to local differences in climate and other physical causes, it would still be plain that plants and animals so similar lived at the same period of time, and that the formations in which their remains were embedded were contemporaneous in a broad way. The presence of the bones of whales and other marine mammals would prove that the strata were laid after the appearance of mammals upon Earth, and embedded relics of man would give a still closer approximation to their age. In the same way we correlate the earlier geological formations. For example, in 1902 there were collected the first fossils ever found on the Antarctic continent. Among the dozen specimens obtained were some fossil ammonites, a family of chambered shells, of genera which are found on other continents in certain formations classified as the Cretaceous system, and which occur neither above these formations nor below them. On the basis of these few fossils we may be confident that the strata in which they were found in the Antarctic region were laid in the same period of geologic time as were the Cretaceous rocks of the United States and Canada. The record as a time scale. By means of the law of included organisms and the law of superposition, the formations of different countries and continents are correlated and arranged in their natural order. When the geological record is thus obtained, it may be used as a universal time scale for geological history. Geological time is separated into divisions corresponding to the times during which the successive formations were laid. The largest assemblages of formations are known as groups, while the corresponding divisions of time are known as eras. Groups are subdivided into systems, and systems into series. Series are divided into stages and substages, subdivisions which do not concern us in this brief treatise. The corresponding divisions of time are given in the following table. Strata group equals time era. Strata system equals time period. Strata series equals time epoch. The geologist is now prepared to read the physical history, the geographical development of any country or of any continent by means of its formations, when he has given each formation its true place in the geological record as a time scale. The following chart exhibits the main divisions of the record, the name given to each being given also to the corresponding time division. Thus we speak of the Cambrian system, meaning a certain succession of formations which are classified together because of the broad resemblances in their included organisms, and of the Cambrian period, meaning the time during which these rocks were deposited. Group and era system, and period series and epoch. The Cenozoic era, which includes the Quaternary period, including the recent and Pleistocene epochs, and the Tertiary period, including the Pliocene, Miocene, and Eocene epochs. The Mesozoic era, including the Cretaceous, Jurassic, and Triassic periods. The Paleozoic era, which includes the Carboniferous period, including the Permian, Pennsylvanian, and Mississippian epochs, as well as the Devonian, Silurian, Ordovician, and Cambrian periods. The Algonquian era and the Archean era. Fossils and what they teach. The geological formations contain a record still more important than that of the geographical development of the continents. The fossils embedded in the rocks of each formation tell of the kinds of animals and plants which inhabited the earth at that time, and from these fossils we are therefore able to construct the history of life upon the earth. Fossils. These remains of organisms are found in the strata in all degrees of perfection, from trails and tracks and fragmentary impressions to perfectly preserved shells, wood, bones, and complete skeletons. As a rule, it is only the hard parts of animals and plants which have left any traces in the rocks. Sometimes the original hard substance is preserved, but more often it has been replaced by some less soluble material. Petrifaction, as this process of slow replacement is called, is often carried on in the most exquisite detail. When wood, for example, is undergoing petrifaction, the woody tissue may be replaced, particle by particle, by silica in solution, through the action of underground waters, even the microscopic structures of the wood being perfectly reproduced. In shells originally made of aragonite, a crystalline form of carbonate of lime, that mineral is usually replaced by calcite, a more stable form of the same substance. The most common petrifying materials are calcite, silica, and pyrite. Often the organic substance has neither been preserved nor replaced, but the form has been retained by means of moulds and casts. Permanent impressions or moulds may be made in sediments not only by the hard parts of organisms, but also by such soft and perishable parts as the leaves of plants, and in the rarest instances by the skin of animals and the feathers of birds. In fine-grained limestones, even the imprints of jellyfish have been retained. The different kinds of moulds and casts may be illustrated by means of a clam shell and some moist clay, the latter representing the sediments in which the remains of animals and plants are entombed. Embedding the shell in the clay and allowing the clay to harden, we have a mould of the exterior of the shell, as is seen on cutting the clay matrix in two and removing the shell from it. Filling this mould with clay of different color, we obtain a cast of the exterior, which represents accurately the original form and surface markings of the shell. In nature, shells and other relics of animals or plants are often removed by being dissolved by percolating waters, and the moulds are either filled with sediments or with minerals deposited from solution. Where the fossil is hollow, a cast of the interior is made in the same way. Interior casts of shells reproduce any markings on the inside of the valves, and casts of the interior of the skulls of ancient vertebrates show the form and size of their brains. Imperfection of the life record. At the present time, only the smallest fraction of the life on earth ever gets entombed in rocks now forming. In the forests, great fallen tree trunks, as well as dead leaves, decay, and only add a little to the layer of dark vegetable mold from which they grew. The bones of land animals are, for the most part, left unburied on the surface and are soon destroyed by chemical agencies. Even where, as in the swamps of river, flood plains, and in other bogs, there are preserved the remains of plants, and sometimes insects, together with the bones of some animal drowned or mired, in most cases these swamp and bog deposits are sooner or later destroyed by the shifting channels of the stream or by the general erosion of the land. In the sea, the conditions for preservation are more favorable than on land. Yet even here the proportion of animals and plants whose hard parts are fossilized is very small compared with those which either totally decay before they are buried in slowly accumulating sediments or are ground to powder by waves and currents. We may infer that during each period of the past, as at the present, only a very insignificant fraction of the innumerable organisms of sea and land escaped destruction and left in continental and oceanic deposits permanent records of their existence. Scanty as these original life records must have been, they have been largely destroyed by metamorphism of the rocks in which they were embedded, by solution in underground waters, and by the vast denudation under which the sediments of earlier periods have been eroded to furnish materials for the sedimentary records of later times. Moreover, very much of what has escaped destruction still remains undiscovered. The immense bulk of the stratified rocks is buried and inaccessible, and the records of the past which it contains can never be known. Comparatively few outcrops have been thoroughly searched for fossils. Although new species are constantly being discovered, each discovery may be considered as the outcome of a series of happy accidents. That the remains of individuals of this particular species happen to be embedded and fossilized, that they happen to escape destruction during long ages, and that they happened to be exposed and found. Some inferences from the records of the history of life upon the planet. Meager as are these records, they set forth plainly some important truths which we will now briefly mention. 1. Each series of the stratified rocks, except the very deepest, contains vestiges of life. Hence, the earth was tenanted by living creatures for an uncalculated length of time before human history began. 2. Life on the earth has been ever-changing. The youngest strata hold the remains of existing species of animals and plants, and those of species and varieties closely allied to them. Strata somewhat older contain fewer existing species, and in strata of a still earlier, but by no means an ancient epoch, no existing species are to be found. The species of that epoch and of previous epochs have vanished from the living world. During all geological time since life began on Earth, old species have constantly become extinct, and with them the genera and families to which they belong, and other species, genera and families, have replaced them. The fossils of each formation differ on the whole from those of every other. The assemblage of animals and plants, the fauna-flora of each epoch, differs from that of every other epoch. In many cases the extinction of a type has been gradual, in other instances apparently abrupt. There is no evidence that any organism once become extinct has ever reappeared. The duration of a species in time, or its vertical range through the strata, varies greatly. Some species are limited to a stratum a few feet in thickness. Some may range through an entire formation, and be found but little modified in still higher beds. A formation may thus often be divided into zones, each characterized by its own peculiar species. As a rule, the simpler organisms have a longer duration as species, though not as individuals, than the more complex. 3. The larger zoological and botanical groupings survive longer than the smaller. Species are so short-lived that a single geological epoch may be marked by several more or less complete extinctions of the species of its fauna-flora and their replacement by other species. A genus continues with new species after all the species with which it began have become extinct. Families survive genera, and orders families. Classes are so long-lived that most of those which are known from the earliest formations are represented by living forms, and no subkingdom has ever become extinct. Thus, to take an example from the stony corals, the zoantharia, the particular characters, which constituted a certain species, Phacocytes niagrenensis, of the order are confined to the Niagara series. Its generic characters appeared in other species earlier in the Silurian and continued through the Devonian. Its family characters, represented in different genera and species, range from the Ordovician to the close of the Paleozoic, while the characters which it shares with all its order, the Zoantharia, began in the Cambrian and are found in living species. 4. The change in organisms has been gradual. The fossils of each life zone and of each formation of a conformable series closely resemble, with some explainable exceptions, those of the beds immediately above and below. The animals and plants which tenanted the earth during any geological epoch are so closely related to those of the preceding and the succeeding epochs that we may consider them to be the descendants of the one and the ancestors of the other, thus accounting for the resemblance by heredity. It is therefore believed that the species of animals and plants now living on the earth are the descendants of the species whose remains we find entombed in the rocks, and that the chain of life has been unbroken since its beginning. 5. The change in species has been a gradual differentiation. Tracing the lines of descent of various animals and plants of the present backward through the divisions of geologic time, we find that these lines of descent converge and unite in simpler and still simpler types. The development of life may be represented by a tree whose trunk is found in the earliest ages and whose branches spread and subdivide to the growing twigs of the present species. 6. The change in organisms throughout geologic time has been a progressive change. In the earliest ages, the only animals and plants on the earth were lowly forms, simple and generalized in structure, while succeeding ages have been characterized by the introduction of types more and more specialized and complex, and therefore of higher rank in the scale of being. Thus the Algonquian contains the remains of only the humblest forms of the invertebrates. In the Cambrian, Ordovician, and Silurian, the invertebrates were represented in all their subkingdoms by a varied fauna. In the Devonian, fishes, the lowest of the vertebrates, became abundant. Amphibians made their entry on the stage in the Carboniferous, and reptiles came to rule the world in the Mesozoic. Mammals culminated in the Tertiary in strange forms which became more and more like those of the present as the long ages of that era rolled on, and latest of all appeared the noblest product of the creative process, man. Just as growth is characteristic of the individual life, so gradual progressive change, or evolution, has characterized the history of life upon the planet. The evolution of the organic kingdom from its primitive germinal forms to the complex and highly organized fauna-flora of today may be compared to the growth of some noble oak as it rises from the acorn, spreading loftier and more widely extended branches as it grows. 7. While higher and still higher types have continually been evolved until man, the highest of all, appeared, the lower and earlier types have generally persisted. Some which reached their culmination early in the history of the earth have since changed only in slight adjustments to a changing environment. Thus the brachiopods, a type of shellfish, have made no progress since the Paleozoic, and some of their earliest known genera are represented by living forms hardly to be distinguished from their ancient ancestors. The lowest and earliest branches of the tree of life have risen to no higher levels since they reached their climax of development long ago. 8. A strange parallel has been found to exist between the evolution of organisms and the development of the individual. In the embryonic stages of its growth, the individual passes swiftly through the successive stages through which its ancestors evolved during the millions of years of geologic time. The development of the individual recapitulates the evolution of the race. The frog is a typical amphibian. As a tadpole, it passes through a stage identical in several well-known features with the maturity of fishes, as, for example, its aquatic life, the tail by which it swims, and the gills through which it breathes. It is a fair inference that the tadpole stage in the life history of the frog represents a stage in the evolution of its kind, that the amphibia are derived from fish-like ancestral forms. This inference is amply confirmed in the geological record. Fishes appeared before amphibia, and were connected with them by transitional forms. The great length of geologic time inferred from the slow change of species. Life forms, like land forms, are thus subject to change under the influence of their changing environment and of forces acting from within. How slowly they change may be seen in the apparent stability of existing species. In the lifetime of the observer, and even in the recorded history of man, species seem as stable as the mountain and the river. But life forms and land forms are alike variable, both in nature and still more under the shaping hand of man. As man has modified the face of the earth with his great engineering works, so he has produced widely different varieties of many kinds of domesticated plants and animals, such as the varieties of the dog and the horse, the apple and the rose, which may be regarded in some respects as new species in the making. We have assumed that land forms have changed in the past under the influence of forces now in operation. Assuming also that life forms have always changed as they are changing at present, we come to realize something of the immensity of geologic time required for the evolution of life from its earliest lowly forms up to man. It is because the onward march of life has taken the same general course the world over that we are able to use it as a universal time scale and divide geologic time into ages and minor subdivisions according to the ruling or characteristic organisms then living on the earth. Thus, since vertebrates appeared, we have in succession the age of fishes, the age of amphibians, the age of reptiles, and the age of mammals. The chart given on page 295 is thus based on the law of superposition and the law of the evolution of organisms. The first law gives the succession of the formations in local areas. The fossils which they contain demonstrate the law of the progressive appearance of organisms, and by means of this law the formations of different countries are correlated and set each in its place in a universal time scale and grouped together according to the affinities of their embedded organic remains. Geologic time divisions compared with those of human history. We may compare the division of geologic time into eras, periods, and other divisions according to the dominant life of the time, to the ill-defined ages into which human history is divided, according to the dominance of some nation, ruler, or other characteristic feature. Thus we speak of the Dark Ages, the Age of Elizabeth, and the Age of Electricity. These crude divisions would be of much value if, as in the case of geologic time, we had no exact reckoning of human history by years. And as the course of human history has flowed in an unbroken stream along quiet reaches of slow change and through periods of rapid change and revolution, so with the course of geologic history. Periods of quiescence, in which revolutionary forces are perhaps gathering head, alternate with periods of comparatively rapid change in physical geography and in organisms, when new and higher forms appear which serve to draw the boundary line of new epochs. Nevertheless, geological history is a continuous progress. Its periods and epochs shade into one another by imperceptible gradations, and all our subdivisions must needs be vague and more or less arbitrary. How fossils tell of the geography of the past. Fossils are used not only as a record of the development of life upon the earth, but also in testimony to the physical geography of past epochs. They indicate whether in any region the climate was tropical, temperate, or arctic. Since species spread slowly from some center of dispersion where they originate until some barrier limits their migration farther, the occurrence of the same species in rocks of the same system in different countries implies the absence of such barriers at the period. Thus, in the collection of Antarctic fossils referred to on page 294, there were shallow water marine shells identical in species with Mesozoic shells found in India and in the southern extremity of South America. Since such organisms are not distributed by the currents of the deep sea and cannot migrate along its bottom, we infer a shallow water connection in Mesozoic times between India, South America, and the Antarctic region. Such a shallow water connection would be offered along the marginal shelf of a continent uniting these now widely separated countries. End of section 20.
Section 21 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, July 2010. The Elements of Geology by William Harmon Norton. Chapter 15. The Precambrian Systems. The Earth's Beginnings. The geological record does not tell us of the beginnings of the Earth. The history of the planet, as we have every reason to believe, stretches far back beyond the period of the oldest stratified rocks, and is involved in the history of the solar system and of the nebula, the cloud of glowing gases or of cosmic dust, from which the sun and planets are believed to have been derived. The Nebular Hypothesis. It is possible that the earth began as a vaporous, shining sphere, formed by the gathering together of the material of a gaseous ring, which had been detached from a cooling and shrinking nebula. Such a vaporous sphere would condense to a liquid, fiery globe, whose surface would become cold and solid, while the interior would long remain intensely hot because of the slow conductivity of the crust. Under these conditions, the primeval atmosphere of the earth must have contained in vapor the water now belonging to the earth's crust and surface. It held also all the oxygen, since locked up in rocks by their oxidation, and all the carbon dioxide, which has been since laid away in limestones, besides that corresponding to the carbon of carbonaceous deposits, such as peat, coal, and petroleum. On this hypothesis, the original atmosphere was dense, dark, and noxious, and enormously heavier than the atmosphere at present. The accretion hypothesis. On the other hand, it has been recently suggested that the earth may have grown to its present size by the gradual accretion of meteoric masses. Such cold, stony bodies might have come together at so slow a rate that the heat caused by their impact would not raise sensibly the temperature of the growing planet. Thus the surface of the earth may never have been hot and luminous, but as the loose aggregation of stony masses grew larger, and was more and more compressed by its own gravitation, the heat thus generated raised the interior to high temperatures, while from time to time molten rock was introduced among the loose, cold meteoric masses of the crust and outpoured upon the surface. It is supposed that the meteorites of which the earth was built brought to it, as meteorites do now, various gases shut up within their pores. As the heat of the interior increased, these gases transpired to the surface and formed the primitive atmosphere and hydrosphere. The atmosphere has therefore grown slowly from the smallest beginnings. Gases emitted from the interior in volcanic eruptions and in other ways have ever added to it, and are adding to it now. On the other hand, the atmosphere has constantly suffered loss, as it has been robbed of oxygen by the oxidation of rocks in weathering, and of carbon dioxide in the making of limestones and carbonaceous deposits. While all hypotheses of the earth's beginnings are as yet unproved speculations, they serve to bring to mind one of the chief lessons which geology has to teach, that the duration of the earth in time, like the extension of the universe in space, is vastly beyond the power of the human mind to realize. Beyond the history recorded in the rocks, which stretches back for many million years, lies the long unrecorded history of the beginnings of the planet, and still farther in the abysses of the past are dimly seen the cycles of the evolution of the solar system and of the nebula which gave it birth. We pass now from the dim realm of speculation to the earliest era of the recorded history of the earth, where some certain facts may be observed, and some sure inferences from them may be drawn. The Archean, the oldest known sedimentary strata, wherever they are exposed by uplift and erosion, are found to be involved with a mass of crystalline rocks which possess the same characteristics in all parts of the world. It consists of foliated rocks, gneisses, and schists of various kinds, which have been cut with dikes and other intrusions of molten rock, and have been broken, crumpled, and crushed, and left in interlocking masses, so confused that their true arrangement can usually be made out only with the greatest difficulty, if at all. The condition of this body of crystalline rocks is due to the fact that they have suffered not only from the faultings, foldings, and igneous intrusions of their time, but necessarily also from those of all later geological ages. At present, three leading theories are held as to the origin of these basal crystalline rocks. 1. They are considered by perhaps the majority of the geologists who have studied them most carefully to be igneous rocks, intruded in a molten state among the sedimentary rocks involved with them. In many localities This relation is proved by the phenomena of contact, but for the most part the deformations which the rocks have since suffered again and again have been sufficient to destroy such evidence if it ever existed. 2. An older view regards them as profoundly altered sedimentary strata, the most ancient of the earth. 3. According to a third theory, they represent portions of the earth's original crust, not, indeed, its original surface, but deeper portions uncovered by erosion, and afterwards mantled with sedimentary deposits. All these theories agree that the present foliated condition of these rocks is due to the intense metamorphism which they have suffered. It is to this body of crystalline rocks, and the stratified rocks involved with it, which form a very small proportion of its mass, that the term Archean (Greek arche, beginning) is applied by many geologists. The Algonkian. In some regions there rests uncomfortably on the Archean an immense body of stratified rocks, thousands and in places even scores of thousands of feet thick, known as the Algonkian. Great unconformities divide it into well-defined systems, but as only the scantiest traces of fossils appear here and there among its strata, it is as yet impossible to correlate the formations of different regions and to give them names of more than local application. We will describe the Algonkian rocks of two typical areas. The Grand Canyon of the Colorado. We have already studied a very ancient peneplain whose edge is exposed to view deep on the walls of the Colorado Canyon. The formation of flat-laying sandstone which covers this buried land surface is proved by its fossils to belong to the Cambrian, the earliest period of the Paleozoic era. The tiled rocks on whose upturned edges the Cambrian sandstone rests are far older, for the physical break which separates them from it records a time interval during which they were upheaved to mountainous ridges and worn down to a low plain. They are therefore classified as Algonkian. They comprise two immense series. The upper is more than 5,000 feet thick, and consists of shales and sandstones with some limestones. Separated from it by an unconformity which does not appear in Figure 207, the lower division, 7,000 feet thick, consists chiefly of massive reddish sandstones with 7 or more sheets of lava interbedded. The lowest member is a basal conglomerate composed of pebbles derived from the erosion of the dark crumpled schists beneath, schists which are supposed to be Archean. As shown in Figure 207, a strong unconformity parts the schists and the Algonkian. The floor on which the Algonkian rests is remarkably even, and here again is proved an interval of incalculable length, during which an ancient landmass of Archean rocks was base-leveled before it received the cover of the sediments of the later age. The Lake Superior region. In eastern Canada an area of Precambrian rocks, Archean and Algonkian, estimated at 2,000,000 square miles, stretches from the Great Lakes and the St. Lawrence River northward to the confines of the continent, inclosing Hudson Bay in the arms of a gigantic U. This immense area, which we have already studied as the Laurentian peneplain, extends southward across the Canadian border into northern Minnesota, Wisconsin, and Michigan. The rocks of this area are known to be Precambrian, for the Cambrian strata, wherever found, lie unconformably upon them. The general relations of the formations of that portion of the area which lies about Lake Superior are shown in Figure 262. Great unconformities, UU', separate the Algonkian both from the Archean and from the Cambrian, and divide it into three distinct systems, the Lower Huronian, the Upper Huronian, and the Keweenawen. The Lower and the Upper Huronian consist in the main of old sea muds and sands and limy oozes, now changed to gneisses, schists, marbles, quartzites, slates, and other metamorphic rocks. The Keweenawen is composed of immense piles of lava, such as those of Iceland, overlain by bedded sandstones. What remains of these rock systems after the denudation of all later geologic ages is enormous. The Lower Huronian is more than a mile thick, the Upper Huronian more than 2 miles thick, while the Keweenawen extends 9 miles in thickness. The vast length of Algonkian time is shown by the thickness of its marine deposits and by the cycles of erosion which it includes. In Figure 267 the student may read an outline of the history of the Lake Superior region, the deformations which it suffered, their relative severity, the times when they occurred, and the erosion cycles marked by the successive unconformities. Other Precambrian areas in North America. Precambrian rocks are exposed in various parts of the continent, usually by the erosion of mountain ranges in which their strata were infolded. Large areas occur in the maritime provinces of Canada. The core of the Green Mountains of Vermont is Precambrian, and rocks of these systems occur in scattered patches in western Massachusetts. Here belong also the oldest rocks of the highlands of the Hudson and of New Jersey. The Adirondack region, an outlier of the Laurentian region, exposes Precambrian rocks which have been metamorphosed and tilted by the intrusion of a great boss of igneous rock out of which the central peaks are carved. The core of the Blue Ridge and probably much of the Piedmont belt are of this age. In the Black Hills the eruption of an immense mass of granite has caused or accompanied the upheaval of Precambrian strata and metamorphosed them by heat and pressure into gneisses, schists, quartzites, and slates. In most of these mountainous regions the lowest strata are profoundly changed by metamorphism, and they can be assigned to the Precambrian only when they are clearly overlain unconformably by formations proved to be Cambrian by their fossils. In the Belt Mountains of Montana, however, the Cambrian is underlain by Algonkian sediments 12,000 feet thick, and but little altered. Mineral wealth of the Precambrian rocks. The Precambrian rocks are of very great economic importance, because of their extensive metamorphism and the enormous masses of igneous rock which they involve. In many parts of the country they are the source of supply of granite, gneiss, marble, slate, and other such building materials. Still more valuable are the stores of iron and copper and other metals which they contain. At the present time the Precambrian region about Lake Superior leads the world in the production of iron ore, its output for 1903 being more than 5/7 of the entire output of the whole United States, and exceeding that of any foreign country. The ore bodies consist chiefly of the red oxide of iron, hematite, and occur in troughs of the strata underlain by some impervious rock. A theory held by many refers the ultimate source of the iron to the igneous rocks of the Archean. When these rocks were upheaved and subjected to weathering, their iron compounds were decomposed. Their iron was leached out and carried away to be lain in the Algonkian water bodies in beds of iron carbonate and other iron compounds. During the later ages, after the Algonkian strata had been uplifted to form part of the continent, a second concentration has taken place. Descending underground waters charged with oxygen have decomposed the iron carbonate and deposited the iron, in the form of iron oxide, in troughs of the strata where their downward progress was arrested by impervious floors. The Precambrian rocks of the eastern United States are also rich in iron. In certain districts, as in the highlands of New Jersey, the black oxide of iron, magnetite, is so abundant in beds and disseminated grains that the ordinary surveyor's compass is useless. The Precambrian copper mines of the Lake Superior region are among the richest on the globe. In the igneous rocks copper, next to iron, is the most common of all the useful metals, and it was especially abundant in the Keweenawen lavas. After the Keweenawen was uplifted to form land, percolating waters leached out much of the copper diffused in the lava sheets and deposited it within steam blebs as amygdules of native copper, in cracks and fissures, and especially as a cement, or matrix, in the interbedded gravels which form the chief aquifers of the region. The famous Calumet and Hecla mine follows down the dip of the strata to the depth of nearly a mile, and works such an ancient conglomerate whose matrix is pure copper. The appearance of life. Sometime during the dim ages preceding the Cambrian, whether in the Archean or in the Algonkian we know not, occurred one of the most important events in the history of the earth. Life appeared for the first time upon the planet. Geology has no evidence whatever to offer as to whence or how life came. All analogies lead us to believe that its appearance must have been sudden. Its earliest forms are unknown, but analogy suggests that as every living creature has developed from a single cell, so the earliest organisms upon the globe, the germs from which all later life is supposed to have been evolved, were tiny, unicellular masses of protoplasm, resembling the amoeba of today in the simplicity of their structure. Such lowly forms were destitute of any hard parts, and could leave no evidence of their existence in the record of the rocks, and of their supposed descendants we find so few traces in the Precambrian strata that the first steps in organic evolution must be supplied from such analogies in embryology as the following. The fertilized ovum, the cell with which each animal begins its life, grows and multiplies by cell division, and develops into a hollow globe of cells, called the blastosphere. This stage is succeeded by the stage of the gastrula, an ovoid or cup-shaped body, with a double wall of cells inclosing a body cavity, and with an opening, the primitive mouth. Each of these early embryological stages is represented by living animals, the undivided cell by the protozoa, the blastosphere by some rare forms, and the gastrula in the essential structure of the coelenterates, the subkingdom to which the freshwater hydra and the corals belong. All forms of animal life, from the coelenterates to the mammals, follow the same path in their embryological development as far as the gastrula stage, but here their paths widely diverge, those of each subkingdom going their own separate ways. We may infer, therefore, that during the Precambrian periods, organic evolution followed the lines thus dimly traced. The earliest one-celled protozoa were probably succeeded by many-celled animals of the type of the blastosphere, and these by gastrula-like organisms. From the gastrula type, the higher subdivisions of animal life probably diverged, as separate branches from a common trunk. Much or all of this vast differentiation was accompanied before the opening of the next era, for all the subkingdoms are represented in the Cambrian except the vertebrates. Evidences of Precambrian life. An indirect evidence of life during the Precambrian periods is found in the abundant and varied fauna of the next period, for, if the theory of evolution is correct, the differentiation of the Cambrian fauna was a long process which might well have required for its accomplishment a large part of Precambrian time. Other indirect evidences are the Precambrian limestones, iron ores, and graphite deposits, since such minerals and rocks have been formed in later times by the help of organisms. If the carbonate of lime of the Algonkian limestones and marbles was extracted from sea water by organisms, as is done at present by corals, mollusks, and other humble animals and plants, the life of those ancient seas must have been abundant. Graphite, a soft black mineral composed of carbon, and used in the manufacture of lead pencils and as a lubricant, occurs widely in the metamorphic Precambrian rocks. It is known to be produced in some cases by the metamorphism of coal, which itself is formed of decomposed vegetal tissues. Seams of graphite may therefore represent accumulations of vegetal matter such as seaweed, while limestone, iron ores, and graphite can be produced by chemical processes, and their presence in the Precambrian makes it only probable and not certain that life existed at that time. Precambrian fossils. Very rarely has any clear trace of an organism been found in the most ancient chapters of the geological record. So many of their leaves have been destroyed, and so far have their pages been defaced. Omitting structures whose organic nature has been questioned, there are left to mention a tiny seashell of one of the most lowly types, a Dicina from the Precambrian rocks of the Colorado Canyon, and from the Precambrian rocks of Montana trails of annelid worms and casts of their burrows in ancient beaches, and fragments of the tests of crustaceans. These diverse forms indicate that before the Algonkian had closed, life was abundant and had widely differentiated. We may expect that other forms will be discovered as the rocks are closely searched. Precambrian geography. Our knowledge is far too meager to warrant an attempt to draw the varying outlines of sea and land during the Archean and Algonquian eras. Precambrian time probably was longer than all later geological time down to the present, as we may infer from the vast thicknesses of its rocks and the unconformities which part them. We know that during its long periods land masses again and again rose from the sea, were worn low, and were submerged and covered with the waste of other lands, but the formations of separated regions cannot be correlated because of the absence of fossils, and nothing more can be made out than the detached chapters of local histories, such as the outline given of the district about Lake Superior. The Precambrian rocks show no evidence of any forces then at work upon the earth except the forces which are at work upon it now. The most ancient sediments known are so like the sediments now being laid that we may infer that they were formed under conditions essentially similar to those of the present time. There is no proof that the sands of the Precambrian sandstones were swept by any more powerful waves and currents than our offshore sands today, or that the muds of the Precambrian shales settled to the seafloor in less quiet water than such muds settle in at present. The Precambrian lands were, no doubt, worn by wind and weather, beaten by rain, and furrowed by streams as now, and, as now, they fronted the ocean with beaches on which waves dashed and along which tidal currents ran. Perhaps the chief difference between the Precambrian and the present was the absence of life upon the land. So far as we have any knowledge, no forests covered the mountainsides, no verdure carpeted the plains, and no animals lived on the ground or in the air. It is permitted to think of the most ancient lands as deserts of barren rock and rock waste swept by rains and trenched by powerful streams. We may therefore suppose that the processes of their destruction went on more rapidly than at present. End of section 21. Section 22 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, July 2010. The Elements of Geology by William Harmon Norton. Chapter 16. The Cambrian. The Paleozoic Era. The second volume of the geological record, called the Paleozoic (Greek paleos, ancient, zoe, life), has come down to us far less mutilated and defaced than has the first volume, which contains the traces of the most ancient life of the globe. Fossils are far more abundant in the Paleozoic than in the earlier strata, while the sediments in which they were entombed have suffered far less from metamorphism and other causes, and have been less widely buried from view than the strata of the Precambrian groups. By means of their fossils we can correlate the formations of widely separated regions from the beginning of the Paleozoic on, and can therefore trace some outline of the history of the continents. Paleozoic time Although shorter than the Precambrian as measured by the thickness of the strata, must still be reckoned in millions of years. During this vast reach of time, the changes in organisms were very great. It is according to the successive stages in the advance of life that the Paleozoic formations are arranged in 5 systems: the Cambrian, the Ordovician, the Silurian, the Devonian, and the Carboniferous. On the same basis, the first 3 systems are grouped together as the Older Paleozoic, because they alike are characterized by the dominance of the invertebrates, while the last 2 systems are united in the Later Paleozoic, and are characterized, the one by the dominance of fishes, and the other by the appearance of amphibians and reptiles. Each of these systems is world-wide in its distribution, and may be recognized on any continent by its own peculiar fauna. The names first given them in Great Britain have therefore come into general use, while their subdivisions, which often cannot be correlated in different countries and different regions, are usually given local names. The first 3 systems were named from the fact that their strata are well displayed in Wales. The Cambrian carries the Roman name of Wales, and the Ordovician and Silurian the names of tribes of ancient Britons which inhabited the same country. The Devonian is named from the English country Devon, where its rocks were early studied. The Carboniferous was so called from the large amount of coal which it was found to contain in Great Britain and continental Europe. The Cambrian. Distribution of strata. The Cambrian rocks outcrop in narrow belts about the Precambrian areas of eastern Canada and the Lake Superior region, the Adirondacks and the Green Mountains. Strips of Cambrian formations occupy troughs in the Precambrian rocks of New England and the maritime provinces of Canada. A long belt borders on the west the crystalline rocks of the Blue Ridge, and on the opposite side of the continent the Cambrian reappears in the mountains of the Great Basin and the Canadian Rockies. In the Mississippi Valley it is exposed in small districts where uplift has permitted the stripping off of younger rocks. Although the areas of outcrop are small, we may infer that Cambrian rocks were widely deposited over the continent of North America. Physical geography. The Cambrian system of North America comprises 3 distinct series: the Lower Cambrian, the Middle Cambrian, and the Upper Cambrian, each of which is characterized by its own peculiar fauna. In sketching the outlines of the continent as it was at the beginning of the Paleozoic, it must be remembered that wherever the Lower Cambrian formations now are found was certainly then sea bottom, and wherever the Lower Cambrian are wanting, the next formations rest directly on Precambrian rocks, was probably then land. Early Cambrian geography. In this way we know that at the opening of the Cambrian 2 long, narrow Mediterranean seas stretched from north to south across the continent. The Eastern Sea extended from the Gulf of St. Lawrence down the Champlain-Hudson Valley, and thence along the western base of the Blue Ridge south at least to Alabama. The Western Sea stretched from the Canadian Rockies over the Great Basin, and at least as far south as the Grand Canyon of the Colorado in Arizona. Between these Mediterraneans lay a great central land which included the Precambrian U-shaped area of the Laurentian peneplain, and probably extended southward to the latitude of New Orleans. To the east lay a land which we may designate as Appalachia, whose western shore line was drawn along the site of the present Blue Ridge, but whose other limits are quite unknown. The land of Appalachia must have been large, for it furnished a great amount of waste during the entire Paleozoic era, and its eastern coast may possibly have lain even beyond the edge of the present continental shelf. On the western side of the continent a narrow land occupied the site of the Sierra Nevada mountains. Thus, even at the beginning of the Paleozoic, the continental plateau of North America had already been left by crustal movements in relief above the abysses of the great oceans on either side. The Mediterraneans which lay upon it were shallow, as their sediments prove. They were epicontinental seas, that is, they rested upon (Greek epi) the submerged portion of the continental plateau. We have no proof that the deep ocean ever occupied any part of where North America now is. The middle and upper Cambrian strata are found together with the lower Cambrian over the area of both the eastern and the western Mediterraneans, so that here the sea continued during the entire period. The sediments throughout are those of shoal water. Coarse, cross-bedded sandstones record the action of strong shifting currents which spread coarse waste near shore and winnowed it of finer stuff. Frequent ripple marks on the bedding planes of the strata prove that the loose sands of the sea floor were near enough to the surface to be agitated by waves and tidal currents. Sun cracks show that often the outgoing tide exposed large muddy flats to the drying action of the sun. The fossils also of the strata are of kinds related to those which now live in shallow waters near the shore. The sediments which gathered in the Mediterranean seas were very thick, reaching in places the enormous depth of 10,000 feet. Hence the bottoms of the seas were sinking troughs, ever filling with waste from the adjacent land as fast as they subsided. Late Cambrian geography. The formations of the Middle and Upper Cambrian are found resting unconformably on the Precambrian rocks from New York westward into Minnesota, and at various points in the interior, as in Missouri and in Texas. Hence after earlier Cambrian time the central land subsided, with much the same effect as if the Mississippi Valley were now to lower gradually, and the Gulf of Mexico to spread northward until it entered Lake Superior. The Cambrian seas transgressed the central land and strewed far and wide behind their advancing beaches the sediments of the later Cambrian upon an eroded surface of Precambrian rocks. The succession of the Cambrian formations in North America records many minor oscillations and varying conditions of physical geography, yet on the whole it tells of widening seas and lowering lands. Basal conglomerates and coarse sandstones, which must have been laid near shore, are succeeded by shaly sandstones, sandy shales, and shales. Toward the top of the series, heavy beds of limestone, extending from the Blue Ridge to Missouri, speak of clear water, and either of more distant shores or of neighboring lands, which were worn or sunk so low that for the most part their waste was carried into the sea in solution. In brief, the Cambrian was a period of submergence. It began with the larger part of North America emerged as the great land masses. It closed with most of the interior of the continental plateau covered with a shallow sea. The life of the Cambrian period. It is now for the first time that we find preserved in the offshore deposits of the Cambrian seas enough remains of animal life to be properly called a fauna. Doubtless these remains are only the most fragmentary representation of the life of the time, for the Cambrian rocks are very old and have been widely metamorphosed. Yet the 500 and more species already discovered embrace all the leading types of invertebrate life, and are so varied that we must believe that their lines of descent stretch far back into the Precambrian past. Plants. No remains of plants have been found in Cambrian strata, except some doubtful markings, as of seaweed. Sponges. The sponges, the lowest of the multicellular animals, were represented by several orders. Their fossils are recognized by the siliceous spicules, which, as in modern sponges, either were scattered through a mass of horny fibers or were connected in a flinty framework. Colenterrates. This subkingdom includes two classes of interest to the geologist: the hydrozoa, such as the freshwater hydra and the jellyfish, and the corals. Both classes existed in the Cambrian. The hydrozoa were represented not only by jellyfish, but also by the graptolite, which takes its name from a fancied resemblance of some of its forms to a quill pen. It was a composite animal with a horny framework, the individuals of the colony living in cells strung on one or both sides along a hollow stem, and communicating by means of a common flesh in this central tube. Some graptolites were straight, and some curved or spiral. Some were single-stemmed, and others consisted of several radial stems united. Graptolites occur but rarely in the Upper Cambrian. In the Ordovician and Silurian they are very plentiful, and at the close of the Silurian they pass out of existence never to return. Corals are very rarely found in the Cambrian, and the description of their primitive types is postponed to later chapters treating of periods when they became more numerous. Echinoderms. This subkingdom comprises at present such familiar forms as the crinoid, the starfish, and the sea urchin. The structure of echinoderms is radiate. Their integument is hardened with plates or particles of carbonate of lime. Of the free echinoderms, such as the starfish and the sea urchin, the former has been found in the Cambrian rocks of Europe, but neither have so far been discovered in the strata of this period in North America. The stemmed and lower division of the echinoderms was represented by a primitive type, the cystoid, so called from its sac-like form, a small globular or ovate calyx of calcareous plates, with an aperture at the top for the mouth, enclosed the body of the animal, and was attached to the sea bottom by a short flexible stalk, consisting of discs of carbonate of lime, held together by a central ligament. Arthropods. These segmented animals with jointed feet, as their name suggests, may be divided in a general way into water breathers and air breathers. The first named and lower division comprises the class of the Crustacea. Arthropods, protected by a hard exterior skeleton, or crust, of which crabs, crayfish, and lobsters are familiar examples. The higher division, that of the air breathers, includes the following classes: spiders, scorpions, centipedes, and insects. The trilobite. The aquatic arthropods, the Crustacea, culminated before the air breathers, and while none of the latter are found in the Cambrian, the former were the dominant life of the time in numbers, in size, and in the variety of their forms. The leading crustacean type is the trilobite, which takes its name from the three lobes into which its shell is divided longitudinally. There are also three cross divisions: the head shield, the tail shield, and between the two the thorax, consisting of a number of distinct and unconsolidated segments. The head shield carries a pair of large, crescentic, compound eyes, like those of the insect. The eye varies greatly in the number of its lenses, ranging from 14 in some species to 15,000 in others. Figure 268c is a restoration of the trilobite, and shows the appendages, which are found preserved only in the rarest cases. During the long ages of the Cambrian the trilobite varied greatly. Again and again new species and genera appeared, while the older types became extinct. For this reason, and because of their abundance, trilobites are used in the classification of the Cambrian system. The Lower Cambrian is characterized by the presence of a trilobitic fauna in which the genus Olinellus is prominent. This, the Olinellus zone, is one of the most important formations in the entire geological series, for, the world over, it marks the beginning of Paleozoic time, while all underlying strata are classified as Precambrian. The Middle Cambrian is marked by the genus Paradoxides, and the Upper Cambrian by the genus Olinus. Some of the Cambrian trilobites were giants, measuring as much as 2 feet long, while others were the smallest of their kind, a fraction of an inch in length. Another type of crustacean which lived in the Cambrian, and whose order is still living, is illustrated in Figure 269. Worms. Trails and burrows of worms have been left on the sea beaches and mud flats of all geological times from the Algonkian to the present. Brachiopods. These soft-bodied animals, with bivalve shells and two interior arm-like processes which served for breathing, appeared in the Algonkian, and had now become very abundant. The two valves of the brachiopod shell are unequal in size, and in each valve a line drawn from the beak to the base divides the valve into 2 equal parts. It may thus be told from the pelecypod mollusk, such as the clam, whose two valves are not far from equal in size, each being divided into unequal parts by a line dropped from the beak. Brachiopods include two orders. In the most primitive order, that of the inarticulate brachiopods, the two valves are held together only by muscles of the animal, and the shell is horny or is composed of phosphate of lime. The Dicina, which began in the Algonkian, is of this type, as is also the Lingulella of the Cambrian. Both of these genera have lived on during the millions of years of geological time since their introduction, handing down from generation to generation with hardly any change to their descendants now living off our shores the characters impressed upon them at the beginning. The more highly organized articulate brachiopods have valves of carbonate of lime more securely joined by a hinge with teeth and sockets (Fig. 270). In the Cambrian the inarticulates predominate, though the articulates grow common toward the end of the period. Mollusks. The three chief classes of mollusks, the pelecypods, represented by the oyster and clam of today, the gastropods, represented now by snails, conches, and periwinkles, and the cephalopods, such as the nautilus, cuttlefish, and squids, were all represented in the Cambrian, although very sparingly. Pteropods, a suborder of the gastropods, appeared in this age. Their papery shells of carbonate of lime are found in great numbers from this time on. Cephalopods, the most highly organized of the mollusks, started into existence, so far as the record shows, toward the end of the Cambrian, with the long extinct Orthoceras (straighthorn) and the allied genera of its family. The Orthoceras had a long, straight, and tapering shell, divided by cross partitions into chambers. The animal lived in the body chamber at the larger end, and walled off the other chambers from it in succession during the growth of the shell. A central tube, the siphuncle, passed through from the body chamber to the closed tip of the cone. The seashells, both brachiopods and mollusks, are in some respects the most important to the geologist of all fossils. They have been so numerous, so widely distributed, and so well preserved because of their durable shells and their station in growing sediments, that better than any other group of organisms they can be used to correlate the strata of different regions, and to mark by their slow changes the advance of geological time. Climate. The life of Cambrian times in different countries contains no suggestion of any marked climatic zones, and as in later periods a warm climate probably reached into the polar regions. End of section 22. Section 23 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, July 2010. The Elements of Geology by William Harmon Norton. Chapter 17. The Ordovician and Silurian. Footnote: often known as the Lower Silurian. The Ordovician. In North America, The Ordovician rocks lie conformably on the Cambrian. The two periods, therefore, were not parted by any deformation, either of mountain making or of continental uplift. The general submergence which marked the Cambrian continued into the succeeding period with little interruption. Subdivisions and distribution of strata. The Ordovician series, as they have been made out in New York, are given for reference in the following table, with the rocks of which they are chiefly composed. 5. Hudson shales. 4. Utica shales. 3. Trenton limestones. 2. Chazy limestones. 1. Calciferous sandy limestones. These marine formations of the Ordovician outcrop about the Cambrian and Precambrian areas, and, as borings show, extend far and wide over the interior of the continent beneath more recent strata. The Ordovician Sea stretched from Appalachia across the Mississippi Valley. It seems to have extended to California, although broken probably by several mountainous islands in the west. Physical geography. The physical history of the period is recorded in the succession of its formations. The sandstones of the Upper Cambrian, as we have learned, tell of a transgressing sea which gradually came to occupy the Mississippi Valley and the interior of North America. The limestones of the early and middle Ordovician show that now the shore had become remote and the lands had become more low. The waters now had cleared. Colonies of brachiopods and other lime-secreting animals occupied the sea bottom, and their debris mantled it with sheets of limy ooze. The sandy limestones of the Calciferous record the transition stage from the Cambrian, when some sand was still brought in from shore. The highly fossiliferous limestones of the Trenton tell of clear water and abundant life. We need not regard this epicontinental sea as deep. No abysmal deposits have been found, and the limestones of the period are those which would be laid in clear, warm water of moderate depth, like that of modern coral seas. The shales of the Utica and Hudson show that the waters of the sea now became clouded with mud washed in from land. Either the land was gradually uplifted, or perhaps there had arrived one of those periodic crises which, as we may imagine, have taken place whenever the crust of the shrinking earth has slowly given way over its great depressions, and the ocean has withdrawn its waters into deepening abysses. The land was thus left relatively higher and bordered with new coastal plains. The epicontinental sea was shoaled and narrowed, and muds were washed in from the adjacent lands. The taconic deformation. The Ordovician was closed by a deformation whose extent and severity are not yet known. From the St. Lawrence River to New York Bay, along the northwestern and western border of New England, lies a belt of Cambrian Ordovician rocks more than a mile in total thickness, which accumulated during the long ages of those periods in a gradually subsiding trough between the Adirondacks and a Precambrian ridge lying west of the Connecticut River. But since their deposition these ancient sediments have been crumpled and crushed, broken with great faults, and extensively metamorphosed. The limestones have recrystallized into marbles, among them the famous marbles of Vermont. The Cambrian sandstones have become quartzites, and the Hudson shale has been changed to a schist, exposed on Manhattan Island and northward. In part these changes occurred at the close of the Ordovician, for in several places beds of Silurian age rest unconformably on the upturned Ordovician strata, but recent investigations have made it probable that the crustal movements recurred at later times, and it was perhaps in the Devonian and at the close of the Carboniferous that the greater part of the deformation and metamorphism was accomplished. As a result of these movements, perhaps several times repeated, a great mountain range was upridged, which has been long since leveled by erosion, but whose roots are now visible in the tectonic mountains of western New England. The Cincinnati anticline, over an oval area in Ohio, Indiana, and Kentucky, whose longer axis extends from north to south through Cincinnati, the Ordovician strata rise in a very low, broad swell called the Cincinnati anticline. The Silurian and Devonian strata thin out as they approach this area and seem never to have deposited upon it. We may regard it, therefore, as an island upwarped from the sea at the close of the Ordovician or shortly after. Petroleum and natural gas. These valuable illuminants and fuels are considered here because, although they are found in traces in older strata, it is in the Ordovician that they occur for the first time in large quantities. They range throughout later formations down to the most recent. The oil horizons of California and Texas are Tertiary, those of Colorado, Cretaceous, those of West Virginia, Carboniferous, those of Pennsylvania, Kentucky, and Canada, Devonian, and the large field of Ohio and Indiana belongs to the Ordovician and higher systems. Petroleum and natural gas, wherever found, have probably originated from the decay of organic matter when buried in sedimentary deposits, just as at present in swampy places the hydrogen and carbon of decaying vegetation combine to form marsh gas. The light and heat of these hydrocarbons we may think of, therefore, as a gift to the civilized life of our race from the humble organisms, both animal and vegetable, of the remote past, whose remains were entombed in the sediments of the Ordovician and later geological ages. Petroleum is very widely disseminated throughout the stratified rocks. Certain limestones are visibly greasy with it, and others give off its characteristic fetid odor when struck with a hammer. Many shales are bituminous, and some are so highly charged that small flakes may be lighted like tapers, and several gallons of oil to the ton may be obtained by distillation. But oil and gas are found in paying quantities only when certain conditions meet. 1. A source below, usually a bituminous shale, from whose organic matter they have been derived by slow change. 2. A reservoir above, in which they have gathered. This is either a porous sandstone, or a porous or creviced limestone. 3. Oil and gas are lighter than water, and are usually under pressure owing to artesian water. Hence, in order to hold them from escaping to the surface, the reservoir must have the shape of an anticline, dome, or lens. 4. It must also have an impervious cover, usually a shale. In these reservoirs gas is under a pressure which is often enormous, reaching in extreme cases as high as 1,500 pounds to the square inch. When tapped, it rushes out with deafening roar, sometimes flinging the heavy drill high in the air. In accounting for this pressure, we must remember that the gas has been compressed within the pores of the reservoir rock by artesian water, and in some cases also by its own expansive force. It is not uncommon for artesian water to rise in wells after the exhaustion of gas and oil. Life of the Ordovician. During the ages of the Ordovician, life made great advances. Types already present branched widely into new genera and species, and new and higher types appeared. Sponges continued from the Cambrian. Graptolites now reached their climax. Stromatopora. Colonies of minute hydrozoans allied to corals grew in places on the sea floor, secreting stony masses composed of thin, close, concentric layers, connected by vertical rods. The Stromatopora are among the chief limestone builders of the Silurian and Devonian periods. Corals developed along several distinct lines. Like modern corals, they secreted a calcareous framework in whose outer portions the polyps lived. In the Ordovician, corals were represented chiefly by the family of the Coetites, all species of which are long since extinct. The description of other types of corals will be given under the Silurian, where they first became abundant. Echinoderms. The cystoid reaches its climax, but there appear now two higher types of echinoderms, the crinoid and the starfish. The crinoid, named from its resemblance to the lily, is like the cystoid in many respects, but has a longer stem and supports a crown of plumose arms. Stirring the water with these arms, it creates currents by which particles of food are wafted to its mouth. Crinoids are rare at the present time, but they grew in the greatest profusion in the warm Ordovician seas and for long ages thereafter. In many places the sea floor was beautiful with these graceful flower-like forms, as with fields of long-stemmed lilies. Of the higher, free-moving classes of the echinoderms, starfish are more numerous than in the Cambrian, and sea urchins make their appearance in rare archaic forms. Crustaceans. Trilobites now reach their greatest development, and more than 1,100 species have been described from the rocks of this period. It is interesting to note that in many species the segments of the thorax have now come to be so shaped that they move freely on one another. Unlike their Cambrian ancestors, many of the Ordovician trilobites could roll themselves into balls at the approach of danger. It is in this attitude, taken at the approach of death, that trilobites are often found in the Ordovician and later rocks. The gigantic crustaceans called the Eurypterids were also present in this period. The arthropods had now seized upon the land. Centipedes and insects of a low type, the earliest known land animals, have been discovered in strata of this system. Bryozoans. No fossils are more common in the limestones of the time than the small branching stems and lace-like mats of the bryozoans, the skeletons of colonies of a minute animal allied in structure to the brachiopod. Brachiopods. These multiplied greatly, and in places their shells formed thick beds of coquina. they still greatly surpassed the mollusks in numbers. Cephalopods. Among the mollusks we must note the evolution of the cephalopods. The primitive straight orthoceras has now become abundant, but in addition to this ancestral type, there appears a succession of forms more and more curved and closely coiled, as illustrated in Figure 285. The nautilus, which began its course in this period, crawls on the bottom of our present seas. Vertebrates. The most important record of the Ordovician is that of the appearance of a new and higher type, with possibilities of development lying hidden in its structure that the mollusk and the insect could never hope to reach. Scales and plates of minute fishes found in the Ordovician rocks near Cañon City, Colorado, show that the humblest of the vertebrates had already made its appearance. But it is probable that vertebrates had been on the earth for ages before this in lowly types, which, being destitute of hard parts, would leave no record. The Silurian. The narrowing of the seas and the emergence of the lands which characterized the closing epoch of the Ordovician in eastern North America continue into the succeeding period of the Silurian. New species appear and many old species now become extinct. The Appalachian region. Where the Silurian system is most fully developed, from New York southward along the Appalachian Mountains, it comprises 4 series. 4. Salina, shales, impure limestones, gypsum, salt. 3. Niagara, chiefly limestones. 2. Clinton, sandstones, shales, with some limestones. 1. Medina, conglomerates, sandstones. The rocks of these series are shallow water deposits and reach the total thickness of some 5,000 feet. Evidently they were laid over an area which was on the whole gradually subsiding, although with various gentle oscillations which are recorded in the different formations. The coarse sands of the heavy Medina formations record a period of uplift of the old land of Appalachia, when erosion went on rapidly and coarse waste in abundance was brought down from the hills by swift streams and spread the waves in wide, sandy flats. As the lands were worn lower, the waste became finer, and during an epoch of transition, the Clinton, there were deposited various formations of sandstones, shales, and limestones. The Niagara limestones testify to a long epoch of repose, when low-lying lands sent little waste down to the sea. The gypsum and salt deposits of the Salina show that toward the close of the Silurian period a slight oscillation brought the sea floor nearer to the surface, and at the north cut off extensive tracts from the interior sea. In these wide lagoons, which now and then regained access to the open sea and obtained new supplies of salt water, beds of salt and gypsum were deposited as the briny waters became concentrated by evaporation under a desert climate. Along with these beds there were also laid shales and impure limestones. In New York, the salt pans of the Salina extended over an area 150 miles long from east to west and 60 miles wide, and similar salt marshes occurred as far west as Cleveland, Ohio, and Goderich on Lake Huron. At Ithaca, New York, the series is 1,500 feet thick, and is buried beneath an equal thickness of later strata. It includes 250 feet of solid salt in several distinct beds, each sealed within the shales of the series. Would you expect to find ancient beds of rock salt enclosed in beds of pervious sandstone? The salt beds of the Salina are of great value. They are reached by well borings, and their brines are evaporated by solar heat and by boiling. The rock salt is also mined from deep shafts. Similar deposits of salt, formed under like conditions, occur in the rocks of later systems down to the present. The salt beds of Texas are Permian, those of Kansas are Permian, and those of Louisiana are Tertiary. The Mississippi Valley. The heavy near-shore formations of the Silurian in the Appalachian region thin out towards the west. The Medina and the Clinton sandstones are not found west of Ohio, where the first passes into a shale and the second into a limestone. The Niagara limestone, however, spreads from the Hudson River to beyond the Mississippi, a distance of more than 1,000 miles. During the Silurian period, the Mississippi Valley region was covered with a quiet, shallow, limestone-making sea, which received little waste from the low lands which bordered it. The probable distribution of land and sea in eastern North America and western Europe is shown in Figure 287. The fauna of the interior region and of eastern Canada are closely allied with that of western Europe, and several species are identical. We can hardly account for this except by a shallow water connection between the two ancient epicontinental seas. It was perhaps along the coastal shelves of a northern land connecting America and Europe by way of Greenland and Iceland that the migration took place, so that the same species came to live in Iowa and in Sweden. The western United States. So little is found of the rocks of the system west of the Missouri River that it is quite probable that the western part of the United States had for the most part emerged from the sea at the close of the Ordovician, and remained land during the Silurian. At the same time, the western land was perhaps connected with the eastern land of Appalachia across Arkansas and Mississippi, for toward the south the Silurian sediments indicate an approach to shore. Life of the Silurian. In this brief sketch, it is quite impossible to relate the many changes of species and genera during the Silurian. Corals. Some of the more common types are familiarly known as cup corals, honeycomb corals, and chain corals. In the cup corals, the most important feature is the development of radiating vertical partitions, or septa, in the cell of the polyp. Some of the cup corals grew in hemispherical colonies, Figure 288, while many were separate individuals, Figure 289, building a single conical or horn-shaped cell, which sometimes reached the extreme size of a foot in length and 2 or 3 inches in diameter. Honeycomb corals consist of masses of small, close-set prismatic cells, each crossed by horizontal partitions, or tabulae, while the septa are rudimentary, being represented by faintly projecting ridges or rows of spines. Chain corals are also marked by tabulae. Their cells form elliptical tubes, touching each other at the edges, and appearing in cross-section like the links of a chain. They became extinct at the end of the Silurian. The corals of the Syringopora family are similar in structure to chain corals, but the tubular columns are connected only in places. To the echinoderms there is now added the blastoid, bud-shaped. The blastoid is stemmed and armless, and its globular head or calyx with its 5 petal-like divisions resembles a flower bud. The blastoids became more abundant in the Devonian, culminated in the Carboniferous, and disappeared at the end of the Paleozoic. The great Eutypterids, some of which were 5 or 6 feet in length, and the cephalopods were still masters of the seas. Fishes were as yet few and small. Trilobites and graptolites had now passed their prime and had diminished greatly in numbers. Scorpions are found in this period both in Europe and in America. The limestone-making seas of the Silurian swarmed with corals, crinoids, and brachiopods. With the end of the Silurian period, the age of invertebrates comes to a close, giving place to the Devonian, the age of fishes. End of section 23. Section 24 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, July 2010. The Elements of Geology by William Harmon Norton. Chapter 18. The Devonian. In America, the Silurian is not separated from the Devonian by any mountain-making deformations or continental uplift. The one period passed quietly into the other. Their conformable systems are so closely related, and the change of their faunas is so gradual, that geologists are not agreed as to the precise horizon which divides them. Subdivisions and physical geography. The Devonian is represented in New York and southward by the following 5 series. We add the rocks of which they are chiefly composed. 5. Chemung, sandstones and sandy shales. 4. Hamilton, shales and sandstones. 3. Coroniferous, limestones. 2. Oriskany, sandstones. 1. Helderberg, limestones. The Helderberg is a transition epoch referred by some geologists to the Silurian. The thin sandstones of the Oriskany mark an epoch when waves worked over the deposits of former coastal plains. The limestones of the Coroniferous testify to a warm and clear wide sea, which extended from the Hudson to beyond the Mississippi. Corals throve luxuriantly, and their remains, with those of mollusks and other lime-secreting animals, built up great beds of limestone. The bordering continents, as during the later Silurian, must now have been monotonous lowlands, which sent down little of even the finest waste to the sea. In the Hamilton, the clear seas of the previous epoch became clouded with mud. The immense deposits of coarse sandstones and sandy shales of the Chemung which are found off what was at the time the west coast of Appalachia, prove an uplift of that ancient continent. The Keemung series extends from the Catskill Mountains to northeastern Ohio and south to northeastern Tennessee, covering an area of not less than 100,000 square miles. In eastern New York it attains 3,000 feet in thickness. In Pennsylvania it reaches an enormous thickness of 2 miles, but it rapidly thins to the west. Everywhere the Keemung is made of thin beds of rapidly alternating coarse and fine sands and clays, with an occasional pebble layer, and hence is a shallow water deposit. The fine material has not been thoroughly winnowed from the coarse by the long action of strong waves and tides. The sands and clays have undergone little more sorting than is done by rivers. We must regard the Keemung sandstones as deposits made at the mouths of swift, turbid rivers in such great amount that they could be little sorted and distributed by waves. Over considerable areas the Keemung sandstones bear little or no trace of the action of the sea. The Catskill Mountains, for example, have as their summit layers some 3,000 feet of coarse red sandstones of this series, whose structure is that of river deposits, and whose few fossils are chiefly of freshwater types. The Keemung is therefore composed of delta deposits, more or less worked over by the sea. The bulk of the Keemung equals that of the Sierra Nevada mountains. To furnish this immense volume of sediment a great mountain range, or highland, must have been upheaved where the Appalachian lowland long had been. To what height the Devonian mountains of Appalachia attained cannot be told from the volume of the sediments wasted from them, for they may have risen but little faster than they were worn down by denudation. We may infer from the character of the waste which they furnished to the Keemung shores that they did not reach an alpine height. The grains of the Keemung sandstones are not those which would result from mechanical disintegration as by frost on high mountain peaks, but are rather those which would be left from the long chemical decay of siliceous crystalline rocks, for the more soluble minerals are largely wanting. The red color of much of the deposits points to the same conclusion. Red residual clays accumulated on the mountain sides and upland summits, and were washed as ochreous silt to mingle with the delta sands. The iron-bearing igneous rocks of the oldland also contributed by their decay iron in solution to the rivers, to be deposited in films of iron oxide about the quartz grains of the Keemung sandstones, giving them their reddish tints. Life of the Devonian. Plants. The lands were probably clad with verdure during Silurian times, if not still earlier, for some rare remains of ferns and other lowly types of vegetation have been found in the strata of that system. But it is in the Devonian that we discover for the first time the remains of extensive and luxuriant forests. This rich flora reached its climax in the Carboniferous, and it will be more convenient to describe its varied types in the next chapter. Rhizocarps. In the shales of the Devonian are found microscopic spores of rhizocarps in such countless numbers that their weight must be reckoned in hundreds of millions of tons. It would seem that these aquatic plants culminated in this period, and in widely distant portions of the earth swampy flats and shallow lagoons were filled with vegetation of this humble type, either growing from the bottom or floating free upon the surface. It is to the resinous spores of the rhizocarps that the petroleum and natural gas from Devonian rocks are largely due. The decomposition of the spores has made the shales highly bituminous, and the oil and gas have accumulated in the reservoirs of overlying porous sandstones. Invertebrates. We must pass over the ever-changing groups of the invertebrates with the briefest notice. Chain corals became extinct at the close of the Silurian, but other corals were extremely common in the Devonian seas. At many places corals formed thin reefs, as at Louisville, Kentucky, where the hardness of the reef rock is one of the causes of the falls of the Ohio. Sponges, echinoderms, brachiopods, and mollusks were abundant. The cephalopods take a new departure. So far in all their various forms, whether straight, as the orthoceras, or curved, or close coiled, as in the nautilus, the septum, or partition dividing the chambers, met the inner shell along a simple line like that of the rim of a saucer. There now begins a growth of the septum, by which its edges become sharply corrugated, and the suture, or line of juncture of the septum and the shell, is thus angled. The group in which this growth of the septum takes place is called the goniatite (Greek gonia, angle). Vertebrates. It is with the greatest interest that we now turn to study the backboned animals of the Devonian, for they are believed to be the ancestors of the hosts of vertebrates which have since dominated the earth. Their rudimentary structures foreshadowed what their descendants were to be, and some give clue to the earliest vertebrates from which they sprang. Like those whose remains are found in the lower Paleozoic systems, all of these Devonian vertebrates were aquatic and go under the general designation of fishes. The lowest in grade, and nearest, perhaps, to the ancestral type of vertebrates, was the problematic creature, an inch or so long, of Figure 297. Note the circular mouth not supplied with jaws, the lack of paired fins, and the symmetrical tail fin, with the column of cartilaginous, ring-like vertebrae running through it to the end. The animal is probably to be placed with the jawless lampreys and hags, a group too low to be included among true fishes. Ostracoderms. This archaic group, long since extinct, is also too lowly to rank among the true fishes, for its members have neither jaws nor paired fins. These small, fish-like forms were cased in front with bony plates, developed in the skin, and covered in the rear with scales. The vertebrae were not ossified, for no trace of them has been found. Devonian fishes. The true fishes of the Devonian can best be understood by reference to their descendants now living. Modern fishes are divided into several groups: sharks and their allies, dipnoans, ganoids, such as the sturgeon and gar, and teleosts, most common fishes, such as the perch and cod. Sharks. Of all groups of living fishes, the sharks are the oldest, and still retain most fully the embryonic characters of their Paleozoic ancestors. Such characters are the cartilaginous skeleton, and the separate gill slits with which the throat wall is pierced, and which are arranged in line like the gill openings of the lamprey. The sharks of the Silurian and Devonian are known to us chiefly by their teeth and fin spines, for they were unprotected by scales or plates, and were devoid of a bony skeleton. Figure 299 is a restoration of an archaic shark from a somewhat higher horizon. Note the 7 gill slits and the lappet-like paired fins. These fins seem to be remnants of the continuous fold of skin which, as embryology teaches, passed from fore to aft down each side of the primitive vertebrae. Devonian sharks were comparatively small. They had not evolved into the ferocious monsters which were later to be masters of the seas. Dipnoans, or lungfishes. These are represented today by a few peculiar fishes, and are distinguished by some high structures which ally them with amphibians. An air sac with cellular spaces is connected with the gullet and serves as a rudimentary lung. It corresponds with the swim bladder of most modern fishes, and appears to have had a common origin with it. We may conceive that the primordial fishes not only had gills used in breathing air or dissolved in water, but also developed a sac-like pouch off the gullet. This sac evolved along 2 distinct lines. On the line of the ancestry of most modern fishes, its duct was closed, and it became the swim bladder used in flotation and balancing. On another line of descent it was left open, air was swallowed into it, and it developed into the rudimentary lung of the dipnoans and into the more perfect lungs of the amphibians and other air-breathing vertebrates. One of the ancient dipnoans is illustrated in Fig. 300. Some of the members of this order were, like the ostracoderms, cased in armor, but their higher rank is shown by their powerful jaws and by other structures. Some of these armored fishes reached 25 feet in length and 6 feet across the head. They were the tyrants of the Devonian seas. Ganoids. These take their name from the enameled plates or scales of bone. The few genera now surviving are the descendants of the tribes which swarmed in the Devonian seas. A restoration of one of a leading order, the fringe-finned ganoids, is given in Fig. 301. The side fins, which correspond to the limbs of the higher vertebrates, are quite unlike those of most modern fishes. Their rays, instead of radiating from a common base, fringe a central lobe which contains a cartilaginous axis. The teeth of the Devonian ganoids show a complicated folded structure. General characteristics of Devonian fishes. The notochord is persistent. The notochord is a continuous rod of cartilage or gristle, which in the embryological growth of vertebrate animals supports the spinal nerve cord before the formation of the vertebrae. In most modern fishes and in all higher vertebrates, the notochord is gradually removed as the bodies of the vertebrae are formed about it, but in the Devonian fishes it persists through maturity and the vertebrae remain incomplete. The skeleton is cartilaginous. This also is an embryological characteristic. In the Devonian fishes the vertebrae, as well as other parts of the skeleton, have not ossified or changed to bone, but remain in their primitive cartilaginous condition. The tail fin is vertebrated. The backbone runs through the fin, and is fringed above and below with its vertical rays. In some fishes with vertebrated tail fins the fin is symmetric, and this seems to be the primitive type. In others the tail fin is unsymmetric. The backbone runs into the upper lobe, leaving the two lobes of unequal size. In most modern fishes, the teleosts, the tail fin is not vertebrated. The spinal column ends in a broad plate, to which the diverging fin rays are attached. But along with these embryonic characters, which were common to all Devonian fishes, there were other structures in certain groups which foreshadowed the higher structures of the land vertebrates which were yet to come: air sacs, which were to develop into lungs, and cartilaginous axes in the side fins, which were a prophecy of limbs. The vertebrates had already advanced far enough to prove the superiority of their type of structure to all others. Their internal skeleton afforded the best attachment for muscles and enabled them to become the largest and most powerful creatures of the time. The central nervous system, with the predominance given to the ganglia at the fore end of the nerve cord, the brain, already endowed them with greater energy than the invertebrates, and, still more important, these structures contained the possibility of development into the more highly organized land vertebrates which were to rule the earth. Teleosts. The great group of fishes called the teleosts, or those with complete bony skeletons, to which most modern fishes belong, may be mentioned here, although in the Devonian they had not yet appeared. The teleosts are a highly specialized type, adapted most perfectly to their aquatic environment. Heavy armor has been discarded, and reliance is placed instead on swiftness. The skeleton is completely ossified, and the notochord removed. The vertebrae have been economically withdrawn from the tail, and the cartilaginous access of the side fins has been found unnecessary. The air sac has become a swim bladder. In this complete specialization they have long since lost the possibility of evolving into higher types. It is interesting to note that the modern teleosts in their embryological growth pass through the stages which characterize the maturity of their Devonian ancestors. Their skeleton is cartilaginous, and their tail fin vertebrated. End of section 24.
Section 25 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Elements of Geology by William Harmon Norton. Chapter 19. The Carboniferous. The Carboniferous system is so named from the large amount of coal which it contains. Other systems, from the Devonian on, are coal-bearing also, but none so richly and to so wide an extent. Never before or since have the peculiar conditions been so favorable for the formation of extensive coal deposits. With few exceptions, the Carboniferous strata rest on those of the Devonian without any marked unconformity. The one period passed quietly into the other with no great physical disturbances. The Carboniferous includes three distinct series. The lower is called the Mississippian, from the outcrop of its formations along the Mississippi River in central and southern Illinois and the adjacent portions of Iowa and Missouri. The middle series is called the Pennsylvanian, or coal measures, from its wide occurrence over Pennsylvania. The upper series is named the Permian, from the province of Perm in Russia. The Mississippian series. In the interior the Mississippian is composed chiefly of limestones, with some shales, which tell of a clear, warm, epicontinental sea, swarming with crinoids, corals, and shells, and occasionally clouded with silt from the land. In the eastern region, New York had been added by uplift to the Appalachian land, which now was united to the northern area. From eastern Pennsylvania southward, there were laid in a subsiding trough, first thick sandstones, the Pocono sandstone, and later still heavier shales, the two together reaching the thickness of 4,000 feet and more. We infer a renewed uplift of Appalachia similar to that of the later epochs of the Devonian, but is much less in amount, as the volume of sediments is smaller. The Pennsylvanian series. The Mississippian was brought to an end by a quiet oscillation which lifted large areas slightly above the sea, and the Pennsylvanian began with a movement in the opposite direction. The sea encroached on the new land, and spread far and wide a great basal conglomerate and coarse sandstones. On this ancient beach deposit a group of strata rests, which we must now interpret. They consist of alternating shales and sandstones, with here and there a bed of limestone and an occasional seam of coal. A stratum of fire clay commonly underlies a coal seam, and there occur also beds of iron ore. We give a typical section of a very small portion of the series at a locality in Pennsylvania. Although some of the minor changes are omitted, the section shows the rapid alternation of the strata. In feet: the first layer, fire clay, 3 feet. Second layer, coal, 5 to 12 feet. Third layer, limestone, 10 feet. Fourth layer, sandstone, 40 feet. Fifth layer, shale, 0 to 2 feet. Sixth layer, coal, 1 to 6 feet. Seventh layer, sandstone, 10 feet. Eighth layer, limestone, 18 feet. Ninth layer, sandstone and shale, 25 feet. This section shows more coal than is usual. On the whole, coal seams do not take up more than 1 foot and 50 of the coal measures. They vary also in thickness more than is seen in the section, some exceptional seams reaching the thickness of 50 feet. How coal was made. 1. Coal is of vegetable origin. Examined under the microscope, even anthracite or hard coal is seen to contain carbonized vegetal tissues. There are also all gradations connecting the hardest anthracite through semi-bituminous coal, bituminous or soft coal, lignite, an imperfect coal in which sometimes woody fibers may be seen little changed, with peat and decaying vegetable tissues. Coal is compressed in mineralized vegetal matter. Its varieties depend on the perfection to which the peculiar change called bituminization has been carried, and also, as shown in the table below, on the degree to which the volatile substances and water have escaped, and on the per cent change of carbon remaining. From a sample in Dismal Swamp, Texas, the Pennsylvanian series. Peat, 78.89% moisture, 13.84% volatile matter, 6.49% fixed carbon, 0.78% ash. Lignite, 14.67% moisture, 37.32% volatile matter, 41.7% fixed carbon, 6.69% ash. Bituminous coal, 1.3% moisture, 20.87% volatile matter, 67.2% fixed carbon, 8.8% ash. Anthracite, 2.74% moisture, 4.25% volatile matter, 81.51% fixed carbon, 10.87% ash. 2. The vegetal remains associated with coal are those of land plants. 3. Coal accumulated in the presence of water, for it is only when thus protected from the air that vegetal matter is preserved. The vegetation of coal accumulated for the most part where it grew. It was not generally drifted and deposited by waves and currents. Commonly the fire clay beneath the seam is penetrated with roots, and the shale above is packed with leaves of ferns, and other plants as beautifully pressed as in an herbarium. There often is associated with the seam a fossil forest, with the stumps, which are still standing where they grew, their spreading roots, and the soil beneath all changed to stone. In the Nova Scotia field Out of 76 distinct coal seams, 20 are underlain by old forest grounds. The presence of fire clay beneath a seam points in the same direction. Such underclays withstand intense heat and are used in making fire brick, because their alkalis have been removed by the long continued growth of vegetation. Fuel coal is also too pure to have been accumulated by driftage. In that case we should expect to find it mixed with mud, while in fact it often contains no more ash than the vegetal matter would furnish from which it has been compressed. These conditions are fairly met in the great swamps of river plains and deltas and of coastal plains, such as the Great Dismal Swamp, where thousands of generations of forests with their undergrowths contribute their stems and leaves to form thick beds of peat. A coal seam is a fossil peat bed. Geographical conditions during the Pennsylvanian. The Carboniferous peat swamps were of vast extent. A map of the coal measures shows that the coal marshes stretched, with various interruptions of higher ground and straits of open water, from eastern Pennsylvania into Alabama, Texas, and Kansas. Some individual coal beds may still be traced over 1,000 square miles, despite the erosion which they have suffered. It taxes the imagination to conceive that the varied region included within these limits was for hundreds of thousands of years a marshy plain covered with tropical jungles. On the basis that peat loses 4/5 of its bulk in changing to coal, we may reckon the thickness of these ancient peat beds. Coal seams 6 and 10 feet thick, which are not uncommon, represent peat beds 30 and 50 feet in thickness, while mammoth coal seams 50 feet thick have been compressed from peat beds 250 feet deep. At the same time, the thousands of feet of marine and freshwater sediments, with their repeated alternations of limestones, sandstones, and shales, in which the seams of coal occur, prove a slow subsidence, with many changes in its rate, with halts when the land was at a still stand, and with occasional movements upward. When subsidence was most rapid and long continued, the sea encroached far and wide upon the lowlands and covered the coal swamps with sands and muds and limy oozes. When subsidence slackened or ceased, the land gained on the sea. Bays were barred, and lagoons, as they gradually filled with mud, became marshes. River deltas pushed forward, burying with their silts the sunken peat beds of earlier centuries, and at the surface emerged in broad swampy flats, like those of the deltas of the Mississippi and the Ganges, which soon were covered with luxuriant forests. At times a gentle uplift brought to the sea level great coastal plains, which for ages remained mantled with the jungle, their undeveloped drainage clogged with its debris, and were then again submerged. Physical geography of the several regions. The Acadian region lay on the eastern side of the northern land, where now are New Brunswick and Nova Scotia, and was an immense river delta. Here river deposits rich in coal accumulated to a depth of 16,000 feet. The area of this coal field is estimated at about 36,000 square miles. The Appalachian region skirts the Appalachian Old Land, on the west, from the southern boundary of New York to northern Alabama, extending west into eastern Ohio. The Cincinnati anticline was now a peninsula, and the broad gulf which had lain between it and Appalachia was transformed at the beginning of the Pennsylvanian into wide marshy plains, now sinking beneath the sea and now emerging from it. This area subsided during the Carboniferous period to a depth of nearly 10,000 feet. The central region lay west of the peninsula of the Cincinnati anticline, and extended from Indiana west into eastern Nebraska, and from central Iowa and Illinois southward about the ancient island in Missouri and Arkansas into Oklahoma and Texas. On the north, the subsidence in this area was comparatively slight, for the Carboniferous strata scarcely exceed 2,000 feet in thickness. But in Arkansas and Indian Territory the downward movement amounted to 4 and 5 miles, as is proved by shoal water deposits of that immense thickness. The coal fields of Indiana and Illinois are now separated by erosion from those lying west of the Mississippi River. At the south the Appalachian land seems still to have stretched away to the west across Louisiana and Mississippi into Texas, and this westward extension formed the southern boundary of the coal marshes of the continent. The three regions just mentioned include the chief Carboniferous coal fields of North America, including a field in central Michigan evidently formed in an enclosed basin, and one in Rhode Island. The total area of American coal fields has been reckoned at not less than 200,000 square miles. We can hardly estimate the value of these great stores of fossil fuel to an industrial civilization. The forests of the coal swamps accumulated in their woody tissues the energy which they received from the sun in light and heat, and it is this solar energy long stored in coal seams which now forms the world's chief source of power in manufacturing. The Western Area. On the great plains beyond the Missouri River the Carboniferous strata pass under those of more recent systems. Where they reappear as about dissected mountain axes, or on stripped plateaus, they consist wholly of marine deposits, and are devoid of coal. The rich coal fields of the West are of later date. On the whole, the Carboniferous seems to have been a time of subsidence in the West. Throughout the period a sea covered the Great Basin and the plateaus of the Colorado River. At the time of the greatest depression, the sites of the central chains of the Rockies were probably islands, but early in the period they may have been connected with the broad lands to the south and east. Thousands of feet of Carboniferous sediments were deposited where the Sierra Nevada mountains now stand. The Permian. As the Carboniferous period drew towards its close, the sea gradually withdrew from the eastern part of the continent. Where the sea lingered in the deepest troughs, and where enclosed basins were cut off from it, the strata of the Permian were deposited. Such are found in New Brunswick, in Pennsylvania and West Virginia, in Texas, and in Kansas. In southwestern Kansas, extensive Permian beds of rock salt and gypsum show that here lay great salt lakes, in which these minerals were precipitated as their brines grew dense and dried away. In the southern hemisphere the Permian deposits are so extraordinary that they deserve a brief notice. Although we have so far omitted mention of the great events which characterize the evolution of other continents than our own, the Permian fauna, flora of Australia, India, South Africa, and the southern part of South America are so similar that the inference is a reasonable one, that these widely separated regions were then connected together, probably as extensions of a great Antarctic continent. Interbedded with the Permian strata of the first three countries named are extensive and thick deposits of a peculiar nature, which are clearly ancient ground moraines. Clays and sand, now hardened to firm rock, are inset with unsorted stones of all sizes, which often are faceted and scratched. Moreover, these boulder clays rest on rock pavements which are polished and scored with glacial markings. Hence, towards the close of the Paleozoic, the southern lands of the eastern hemisphere were invaded by great glaciers, or perhaps by ice sheets like that which now shrouds Greenland. These Permian ground moraines are not the first traces of the work of glaciers met with in the geological record. Similar deposits prove glaciation in Norway succeeding the Precambrian stage of elevation, and Cambrian glacial drift has recently been found in China. The Appalachian deformation. We have seen that during Paleozoic times a long narrow trough of the sea lay off the western coast of the ancient land of Appalachia, where now are the Appalachian Mountains. During the long ages of this era the trough gradually subsided, although with many still stands, and with occasional slight oscillations upward. Meanwhile the land lying to the east was gradually uplifted at varying rates and with long pauses. The waste of the rising land was constantly transferred to the sinking marginal sea bottom, and on the whole the trough was filled with sediments as rapidly as it subsided. The sea was thus kept shallow, and at times, especially toward the close of the era, much of the area was upbuilt or raised to low marshy coastal plains. When the Carboniferous was ended, the waste which had been removed from the land and laid along its margin in the successive formations of the Paleozoic had reached a thickness of between 30 and 40,000 feet. Both by sedimentation and by subsidence the trough had now become a belt of weakness in the crust of the earth. Here the crust was now made of layers to the depth of 6 or 7 miles. In comparison with the massive crystalline rocks of Appalachia on the east, the layered rock of the trough was weak to resist lateral pressure, as a ream of sheets of paper is weak when compared with a solid board of the same thickness. It was weaker also than the region to the west, since there the sediments were much thinner. Besides, by the long continued depression the strata of the trough had been bent from the flat lying attitude in which they were laid to one in which they were less able to resist a horizontal thrust. There now occurred one of the critical stages in the history of the planet, when the crust crumples under its own weight and shrinks down upon a nucleus which is diminishing in volume and no longer able to support it. Under slow but resistless pressure the strata of the Appalachian trough were thrust against the rigid land and slowly, steadily bent into long folds where axes ran northeast, southwest parallel to the ancient coastline. It was on the eastern side, next the buttress of the land, that the deformation was the greatest, and the folds most steep and close. In central Pennsylvania and West Virginia the folds were for the most part open. South of these states the folds were more closely oppressed. The strata were much broken, and the great thrust faults were formed which have been described already. In eastern Pennsylvania seams of bituminous coal were altered to anthracite, while outside the region of strong deformation, as in western Pennsylvania, they remained unchanged. An important factor in the deformation was the massive limestones of the Cambrian Ordovician. Because of these thick, resistant beds, the rocks were bent into wide folds and sheared in places with great thrust faults. Had the strata been weak shales, an equal pressure would have crushed and mashed them. Although the great earth folds were slowly raised, and no doubt eroded in their rising, they formed, in all probability, a range of lofty mountains, with a width of from 50 to 125 miles, which stretched from New York to central Alabama. From their bases lowlands extended westward to beyond the Missouri River. At the same time ranges were upridged out of thick Paleozoic sediments both in the Bay of Fundy region and in the Indian Territory. The eastern portion of the North American continent was now well nigh complete. The date of the Appalachian deformation is told in the usual way. The Carboniferous strata, nearly 2 miles thick, are all enfolded in the Appalachian ridges, while the next deposits found in this region, those of the latter portion of the first period, the Trias, of the succeeding era, rest unconformably on the worn edges of the Appalachian folded strata. The deformation, therefore, took place about the close of the Paleozoic. It seems to have begun in the Permian, in eastern Pennsylvania, for here the Permian strata are wanting, and to have continued into the Trias, whose earlier formations are absent over all the area. With this wide uplift the subsidence of the sea floor, which had so long been general in eastern North America, came to an end. Deposition now gave place to erosion. The sedimentary record of the Paleozoic was closed, and after an unknown lapse of time, here unrecorded, the annals of the succeeding era were written under changed conditions. In western North America the closing stages of the Paleozoic were marked by important oscillations. The Great Basin, which had long been a Mediterranean sea, was converted into land over western Utah and eastern Nevada, while the waves of the Pacific rolled across California and western Nevada. The absence of tuffs and lavas among the Carboniferous strata of North America shows that here volcanic action was singularly wanting during the entire period. Even the Appalachian deformation was not accompanied by any volcanic outbursts. Life of the Carboniferous. Plants. The gloomy forests and dense undergrowths of the Carboniferous jungles would appear unfamiliar to us could we see them as they grew, and even a botanist would find many of their forms perplexing and hard to classify. None of our modern trees would meet the eye. Plants with conspicuous flowers of fragrance and beauty were yet to come. Even mosses and grasses were still absent. Tree ferns lifted their crowns of feathery fronds high in air on trunks of woody tissue, and lowly herbaceous ferns, some belonging to existing families, carpeted the ground. Many of the fern-like forms, however, have distinct affinities with the cycads, of which they may be the ancestors, and some bear seeds and must be classed as gymnosperms. Dense thickets, like cane or bamboo brakes, were composed of thick clumps of calamites, whose slender jointed stems shot up to a height of 40 feet, and at the joints bore slender branches set with whorls of leaves. These were close allies of the equiseta, or horsetails, of the present, but they bore characteristics of higher classes in the woody structures of their stems. There was also vast monotonous forests, composed chiefly of trees belonging to the lycopods, and whose nearest relatives to day are the little club mosses of our eastern woods. Two families of lycopods deserve special mention, the lepidodendrons and the sigillaria. The lepidodendron, or scale tree, was a gigantic club moss, 50 and 75 feet high, spreading towards the top into stout branches, at whose ends were borne cone-shaped spore cases. The younger parts of the tree were clothed with stiff needle-shaped leaves, but elsewhere the trunk and branches were marked with scale-like scars left by the fallen leaves and arranged in spiral rows. The sigillaria, or seal tree, was similar to the lepidodendron. but its fluted trunk divided into even fewer branches, and was dotted with vertical rows of leaf scars like the impressions of a seal. Both Lepidodendron and Sigillaria were anchored by means of great cable like underground stems, which ran to long distances through the marshy ground. The trunks of both trees had a thick woody rind, enclosing loose cellular tissue and a pith. Their hollow stumps, filled with sand and mud, are common in the coal measures, and in them one sometimes finds leaves and stems, land shells, and the bones of little reptiles of the time which made their home there. It is important to note that some of these gigantic lycopods, which are classed with the cryptogams, or flowerless plants, had pith and medullary raids dividing their cylinders into woody wedges. These characters connect them with the phanerogams, or flowering plants. Like so many of the organisms of the remote past, they were connecting types from which groups now widely separated have diverged. Gymnosperms akin to the cycads were also present in the Carboniferous forests. Such were the different species of chordates, trees pyramidal in shape, with strap-shaped leaves and nut-like fruit. Other gymnosperms were related to the yews, and it was by these that many of the fossil nuts found in the coal measures were born. It is thought by some that the gymnosperms had their station on the drier plains and higher lands. The Carboniferous jungles extended over parts of Europe and of Asia, as well as eastern North America, and reached from the equator to within 9° of the North Pole. Even in these widely separated regions, the genera and species of coal plants are close akin and often identical. Invertebrates. Among the echinoderms, crinoids are now exceedingly abundant. Sea urchins are more plentiful, and sea cucumbers are found now for the first time. Trilobites are rapidly declining, and pass away forever with the close of the period. Eurypterids are common. Stinging scorpions are abundant, and here occur the first known spiders. We have seen that the arthropods were the first of all animals to conquer the realm of the air, the earliest insects appearing in the Ordovician. Insects had now become exceedingly abundant, and the Carboniferous forest swarmed with the ancestral types of dragonflies, some with a spread of wing of more than 2 feet, mayflies, crickets, and locusts. Cockroaches infested the swamps, and 133 species of this ancient order have been discovered in the Carboniferous of North America. The higher, flower-loving insects are still absent. The reign of the flowering plants has not yet begun. The Paleozoic insects were generalized types connecting the present orders. Their forewings were still membranous and delicately veined and used in flying. They had not yet become thick and useful only as wing covers, as in many of their descendants. Fishes still held to the Devonian types, with the exception that the strange ostracoderms now had perished. Amphibians. The vertebrates had now followed the arthropods and the mollusks upon the land, and had evolved a higher type adapted to the new environment. Amphibians, the class to which frogs and salamanders belong, now appear, with lungs for breathing air, and with limbs for locomotion on the land. Most of the Carboniferous amphibians were shaped like the salamander, with weak limbs adapted more for crawling than for carrying the body well above the ground. Some legless, degenerate forms were snake-like in shape. The earliest amphibians differ from those of to-day in a number of respects. They were connecting types, linking together fishes, from which they were descended, with reptiles, of which they were the ancestors. They retain the evidence of their close relationship with the Devonian fishes in their cold blood, their gills, and the aquatic habit during their larval stage, their teeth with dentine enfolded, like those of the Devonian ganoids, but still more intricately, and their biconcave vertebra, which never completely ossified. These, the highest vertebrates of the time, had not yet advanced beyond the embryonic stage of the more or less cartilaginous skeleton and the persistent notochord. On the other hand, the skull of the Carboniferous amphibians was made of close-set bony plates, like the skull of the reptile rather than like that of the frog, with its open spaces. Unlike modern amphibians with their slimy skin, the Carboniferous amphibians wore an armor of bony scales over the ventral surface and sometimes over the back as well. It is interesting to notice from the footprints and skeletons of these earliest known vertebrates of the land what was the primitive number of digits. The Carboniferous amphibians had 5-toed feet, the primitive type of foot, from which their descendants of higher orders, with a smaller number of digits, have diverged. The Carboniferous was the age of lycopods and amphibians, as the Devonian had been the age of rhizocarps and fishes. Life of the Permian. The close of the Paleozoic was, as we have seen, a time of marked physical changes. The upridging of the Appalachians had begun a wide continental uplift, proved by the absence of Permian deposits over large areas where sedimentation had gone on before, opened new lands for settlement to hordes of air breathing animals. Changes of climate compelled extensive migrations, and the fauna of different regions were thus brought into conflict. The Permian was a time of pronounced changes in plant and animal life, and a transitional period between two great eras. The sombre forests of the earlier Carboniferous, with their gigantic club mosses, were now replaced by forests of cycads, tree ferns, and conifers. Even in the lower Permian, the lepidodendron and the sigillaria were very rare, and before the end of the epoch they and the calamites also had become extinct. Gradually the antique types of the Paleozoic fauna died out, and in the Permian rocks are found the last survivors of the cystoid, the trilobite, and the eurypterid, and of many long-lived families of brachiopods, mollusks, and other invertebrates. The venerable Orthoceras and the Goniatite linger on through the epoch and into the first period of the succeeding era. Forerunners of the great ammonite family of cephalopod mollusks now appear. The antique forms of the earlier Carboniferous amphibians continue, but with many new genera and a marked increase in size. A long forward step had now been taken in the evolution of the vertebrates. A new and higher type, the reptiles, had appeared, and in such numbers and variety are they found in the Permian strata that their advent may well have occurred in a still earlier epoch. It will be most convenient to describe the Permian reptiles along with their descendants of the Mesozoic. End of chapter 19.
Section 26 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Elements of Geology by William Harmon Norton. Chapter 20, Part 2. The Mesozoic. With the close of the Permian, the world of animal and vegetable life had so changed that the line is drawn here which marks the end of the Old Order and the beginning of the New, and separates the Paleozoic from the succeeding era, the Mesozoic, the middle age of geological history. Although the Mesozoic era is shorter than the Paleozoic, as measured by the thickness of their strata, yet its duration must be reckoned in millions of years. Its predominant life features are the culmination and beginning of the decline of reptiles, amphibians, cephalopod mollusks, and cycads, and the advent of marsupial mammals, birds, teleost fishes, and angiospermous plants. The leading events of the long ages of the era we can sketch only in the most summary way. The Mesozoic comprises three systems: the Triassic, named from its threefold division in Germany; the Jurassic, which is well displayed in the Jura Mountains; and the Cretaceous, which contains the extensive chalk, Latin Creta, deposits of Europe. In eastern North America, the Mesozoic rocks are much less important than the Paleozoic, for much of this portion of the continent was land during the Mesozoic era, and the area of the Mesozoic rocks is small. In western North America, on the other hand, the strata of the Mesozoic and of the Cenozoic are also widely spread. The Paleozoic rocks are buried quite generally from view, except where the mountain makings and continental uplifts of the Mesozoic and Cenozoic have allowed profound erosion to bring them to light, as in deep canyons and about mountain axes. The record of most of the important events in the development of the continent during the Mesozoic and Cenozoic eras is found in the rocks of our western states. The Triassic and Jurassic, eastern North America. The sedimentary record interrupted by the Appalachian deformation was not renewed in eastern North America until late in the Triassic. Hence, during this long interval, the land stood high, the coast was farther out than now, and over our Atlantic states, geological time was recorded chiefly in erosion forms of hill and plain, which have long since vanished. The area of the later Triassic rocks of this region, which take up again the geological record, is seen in the map of Figure 260. They lie on the upturned and eroded edges of older rocks and occupy long troughs running for the most part parallel to the Atlantic coast. Evidently subsidence was in progress where these rocks were deposited. The eastern border of Appalachia was now depressed. The old land was warping, and long belts of country lying parallel to the shore subsided, forming troughs in which thousands of feet of sediment now gathered. These Triassic rocks, which are chiefly sandstones, hold no marine fossils, and hence were not laid in open arms of the sea. But their layers are often ripple-marked and contain many tracks of reptiles, imprints of raindrops, and some fossil wood, while an occasional bed of shale is filled with the remains of fishes. We may conceive, then, of the Connecticut Valley and the larger trough to the southwest as basins, gradually sinking at a rate perhaps no faster than that of the Jersey coast today, and as gradually aggraded by streams from the neighboring uplands. Their broad, sandy flats were overflowed by wandering streams, and with subsidence gained on depositions, shallow lakes overspread the alluvial plains. Perhaps now and then the basins became long, brackish estuaries, whose low shores were swept by the incoming tide and were in turn left bare at its retreat to receive the rain prints of passing showers and the tracks of the troops of reptiles which inhabited these valleys. The Triassic rocks are mainly red sandstones, often feldspathic or arkose, with some conglomerates and shales. Considering the large amount of feldspathic material in these rocks, do you infer that they were derived from the adjacent crystalline and metamorphic rocks of the old land of Appalachia, or from the sedimentary Paleozoic rocks which had been folded into mountains during the Appalachian deformation? If from the former, was the drainage of the northern Appalachian mountain region then, as now, eastward and southward toward the Atlantic? The Triassic sandstones are voluminous, measuring at least a mile in thickness, and are largely of coarse waste. What do you infer as to the height of the lands from which the waste was shed, or to the direction of the oscillation which they were then undergoing? In the southern basins, as about Richmond, Virginia, are valuable beds of coal. What was the physical geography of these areas when the coal was being formed? Interbedded with the Triassic sandstones are contemporaneous lava beds which were fed from dikes. Volcanic action, which had been remarkably absent in eastern North America during Paleozoic times, was well marked in connection with the warping now in progress. Thick, intrusive sheets have also been driven in among the strata, as, for example, the sheet of the Palisades of the Hudson, described on page 269. The present condition of the Triassic sandstones of the Connecticut Valley is seen in Figure 315. Were the beds laid in their present attitude? What was the nature of the deformation which they have suffered? When did the intrusion of the lava sheets take place relative to the deformation? What effect have these sheets on the present topography, and why? Assuming that the Triassic deformation went on more rapidly than denudation, what was its effect on the topography of the time? Are there any of its results remaining in the topography of today? Do the Triassic areas now stand higher or lower than the surrounding country? And why? How do the Triassic sandstones and shales compare in hardness with the igneous and metamorphic rocks about them? The Jurassic strata are wanting over the Triassic areas and over all of eastern North America. Was this region land or sea, an area of erosion or sedimentation during the Jurassic period? In New Jersey, Pennsylvania, and farther southwest, the lowest strata of the next period, the Cretaceous, rest on the eroded edges of the earlier rocks. The surface on which they lie is worn so even that we must believe that at the opening of the Cretaceous, the old land of Appalachia, including the Triassic areas, had been base-leveled at least near the coast. When, therefore, did the deformation of the Triassic rocks occur? Western North America. Triassic strata enfolded in the Sierra Nevada mountains carry marine fossils and reach a thickness of nearly 5,000 feet. California was then underwater, and the site of the Sierra was a subsiding trough, slowly filling with waste from the Great Basin land to the east. Over a long belt which reaches from Wyoming across Colorado into New Mexico, no Triassic sediments are found, nor is there any evidence that they were ever present. Hence, this area was highland suffering erosion during the Triassic. On each side of it, in eastern Colorado and about the Black Hills, in western Texas, in Utah, over the side of the Wasatch Mountains, and southward into Arizona over the plateaus trenched by the Colorado River, are large areas of Triassic rocks, sandstones chiefly, with some rock salt and gypsum. Fossils are very rare, and none of them are marine. Here, then, lay broad, shallow lakes, often salt, and warped basins in which the waste of the adjacent uplands gathered. To this system belong the sandstones of the Garden of the Gods in Colorado, which later earth movements have upturned with the uplifted mountain flanks. The Jurassic was marked with varied oscillations and wide changes in the outline of sea and land. Jurassic shales of immense thickness, now metamorphosed into slates, are found infolded into the Sierra Nevada mountains. Hence, during Jurassic times, the Sierra Trough continued to subside, and enormous deposits of mud were washed into it from the land lying to the east. Contemporaneous lava flows interbedded with the strata show that volcanic action accompanied the downwarp, and that molten rock was driven upward through fissures in the crust and outspread over the seafloor in sheets of lava. The Sierra Deformation. Ever since the middle of the Silurian, the Sierra Trough had been sinking, though no doubt with halts and interruptions, until it contained nearly 25,000 feet of sediment. At the close of the Jurassic, it yielded to lateral pressure, and the vast pile of strata was crumpled and upheaved into towering mountains. The Mesozoic muds were hardened and squeezed into slates. The rocks were wrenched and broken, and underground waters began the work of filling their fissures with gold-bearing quartz, which was yet to wait millions of years before the arrival of man to mine it. Immense bodies of molten rock were intruded into the crust as it suffered deformation, and these appear in large areas of granite which the latter denudation of the range has brought to light. The same movements probably uplifted the rocks of the Coast Range in a chain of islands. The whole western part of the continent was raised, and its seas and lakes were for the most part drained away. The British Isles. The Triassic strata of the British Isles are continental, and include breccia beds of cemented talus, deposits of salt and gypsum, and sandstones whose rounded and polished grains are those of the wind-blown sands of deserts. In Triassic times, the British Isles were part of a desert extending over much of northwestern Europe, the Cretaceous. The third great system of the Mesozoic includes many formations, marine and continental, which record a long and complicated history marked by great oscillations of the crust and wide changes in the outlines of sea and land. Early Cretaceous. In eastern North America, the lowest Cretaceous series comprises freshwater formations which are traced from Nantucket across Martha's Vineyard and Long Island, and through New Jersey southward into Georgia. They rest uncomfortably on the Triassic sandstones and the older rocks of the region. The Atlantic shoreline was still farther out than now in the northern states. Again, as during the Triassic, a warping of the crust formed a long trough parallel to the coast and to the Appalachian ridges, but cut off from the sea. And here the continental deposits of the early Cretaceous were laid. Along the Gulf of Mexico, the same series was deposited under like conditions over the area known as the Mississippi Embayment, reaching from Georgia northwestward into Tennessee and thence across into Arkansas and southward into Texas. In the southwest, the subsidence continued until the transgressing sea covered most of Mexico and Texas and extended a gulf northward into Kansas. In its warm and quiet waters, limestones accumulated to a depth of from 1,000 to 5,000 feet in Texas, and of more than 10,000 feet in Mexico. Meanwhile, the lowlands, where the Great Plains are now, received continental deposits. Coal swamps stretched from western Montana into British Columbia. The Middle Cretaceous. This was a land epoch. The early Cretaceous sea retired from Texas and Mexico, for its sediments are overlain uncomfortably by formations of the Upper Cretaceous. So long was the time gap between the two series that no species found in the one occurs in the other. The Upper Cretaceous. There now began one of the most remarkable events in all geological history, the Great Cretaceous subsidence. Its earlier warpings were recorded in continental deposits, wide sheets of sandstone, shale, and some coal, which were spread from Texas to British Columbia. These continental deposits are overlain by a succession of marine formations whose vast area is shown on the map, figure 260. We may infer that as the depression of the continent continued, the sea came in far and wide over the coastlands and the plains worn low during the previous epochs. Upper Cretaceous formations show that south of New England, the waters of the Atlantic somewhat overlapped the crystalline rocks of the Piedmont Belt and spread their waste over the submerged coastal plain. The Gulf of Mexico again covered the Mississippi Embayment, reaching as far north as southern Illinois and extended over Texas. A Mediterranean Sea now stretched from the Gulf to the Arctic regions and from central Iowa to the eastern shore of the Great Basin land, at about the longitude of Salt Lake City, the Colorado Mountains rising from it in a chain of islands. Along with minor oscillations, there were laid in the interior sea various formations of sandstones, shales, and limestones, and from Kansas to South Dakota, beds of white chalk show that the clear, warm waters swarmed at times with foraminiferal life whose disintegrating microscopic shells accumulated in this rare deposit. At this epoch, a wide sea interrupted by various islands stretched across Eurasia from Wales and western Spain to China, and spread southward over much of the Sahara. To the west its waters were clear, and on its floor the crumbled remains of foraminifers gathered in the heavy accumulations of calcareous ooze, the white chalk of France and England. Sea urchins were also abundant, and sponges contributed their spicules to form nodules of flint, the Laramie. The closing stage of the Cretaceous was marked in North America by a slow uplift of the land. As the interior sea gradually withdrew, the warping basins of its floor were filled with waste from the rising lands about them, and over this wide area there were spread continental deposits in freshwater lakes like the Great Lakes of the present, in brackish estuaries, and in river plains, while occasional oscillations now and again let in the sea. There were vast marshes in which there accumulated the larger part of the valuable coal seams of the West. The Laramie is the coal-bearing series of the West, as the Pennsylvanian is of the eastern part of our country, the Rocky Mountain Deformation. At the close of the Cretaceous, we enter upon an epoch of mountain-making far more extensive than any which the continent had witnessed. The long belt lying west of the ancient axes of the Colorado Islands and east of the Great Basin land had been an area of deposition for many ages, and in its subsiding troughs Paleozoic and Mesozoic sediments had gathered to the depth of many thousand feet, and now from Mexico well nigh to the Arctic Ocean this belt yielded to lateral pressure. The Cretaceous limestones of Mexico were folded into lofty mountains. A massive range was upfolded where the Wasatch Mountains now are, and various ranges of the Rockies in Colorado and other states were upridged. However slowly these deformations were effected, they were no doubt accompanied by world-shaking earthquakes, and it is known that volcanic eruptions took place on a magnificent scale. Outflows of lava occurred along the Wasatch. The laccoliths of the Henry Mountains were formed, while the great masses of igneous rock which constitute the cores of the Spanish Peaks and other western mountains were thrust up amid the strata. The high plateaus from which many of these ranges rise had not yet been uplifted, and the bases of the mountains probably stood near the level of the sea. North America was now well nigh completed. The Mediterranean seas, which so often had occupied the heart of the land, were done away with, and the continent stretched unbroken from the foot of the Sierras on the west to the fall line of the Atlantic coastal plain on the east. The Mesozoic peneplain. The immense thickness of the Mesozoic formations conveys to our minds some idea of the vast length of the time involved in the slow progress of its successive ages. The same lesson is taught as plainly by the amount of denudation that the land suffered during the era. The beginning of the Mesozoic saw a system of lofty mountain ranges stretching from New York into central Alabama. The end of this long era found here a wide peneplain, crossed by sluggish wandering rivers and overlooked by detached hills as yet unreduced to the general level. The Mesozoic era was long enough for the Appalachian Mountains, upridged at its beginning, to have been weathered and worn away and carried grain by grain to the sea. The same plain extended over southern New England. The Taconic Range, uplifted partially at least at the close of the Ordovician, and the block mountains of the Triassic, together with the Precambrian mountains of ancient Appalachia, had now all been worn to a common level with the Allegheny Ranges. The Mesozoic peneplain has been upwarped by later crustal movements and has suffered profound erosion. But the remnants of it, which remain on the upland of southern New England and the even summits of the Allegheny Ridges, suffice to prove that it once existed. The age of the Mesozoic peneplain is determined from the fact that the lower tertiary sediments were deposited on its even surface, when at the close of the era the peneplain was depressed along its edges beneath the sea. End of section 26, recorded by Andrew Nelson, Atlanta, Georgia. Section 27 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Elements of Geology by William Harmon Norton. Chapter 20, Section 2. Life of the Mesozoic. Plant life of the Triassic and Jurassic. The carboniferous forests of lepidodendrons and cegalophyds had now vanished from the earth. The uplands were clothed with conifers, like the Araucarian pines of South America and Australia. Dense forests of tree ferns throve in moist regions, and canebrakes of horsetails of modern type, but with stems reaching 4 inches in thickness, bordered the lagoons and marshes. Cycads were exceedingly abundant. These gymnosperms, related to the pines and spruces in structure and fruiting, but palm-like in their foliage, and uncoiling their long leaves after the manner of ferns, culminated in the Jurassic. From the viewpoint of the botanist, the Mesozoic is the age of cycads, and after this era they gradually declined to the small number of species now existing in tropical latitudes. Plant life of the Cretaceous. In the lower Cretaceous, the woodlands continued of much the same type as during the Jurassic. The forerunners now appeared of the modern dicotyls, plants with 2 seed leaves, and in the middle Cretaceous the monocotyledonous group of palms came in. Palms are so much like cycads that we may regard them as descendants of some cycad type. In the upper Cretaceous, cycads became rare. The highest types of flowering plants gain a complete ascendancy, and forests of modern aspect cover the continent from the Gulf of Mexico to the Arctic Ocean. Among the kinds of forest trees whose remains are found in the continental deposits of the Cretaceous are the magnolia, the myrtle, the laurel, the fig, the tulip tree, the chestnut, the oak, beech, elm, poplar, willow, birch, and maple. Forests of eucalyptus grew along the coasts of New England, and palms on the Pacific shores of British Columbia. Sequoias of many varieties ranged far into northern Canada. In northern Greenland there were luxuriant forests of magnolias, figs, and cycads, and a similar flora has been disinterred from the Cretaceous rocks of Alaska and Spitsbergen. Evidently the lands within the Arctic Circle enjoyed a warm and genial climate, as they had done during the Paleozoic. Greenland had the temperature of Cuba and southern Florida, and the time was yet far distant when it was to be wrapped in glacier ice. Invertebrates. During the long succession of the ages of the Mesozoic, with their vast geographical changes, there were many great changes in organisms. Species were replaced again and again by others better fitted to the changing environment. During the lower Cretaceous alone, there were no less than 6 successive changes in the faunas which inhabited the limestone-making sea which then covered Texas. We shall disregard these changes for the most part in describing the life of the era, and shall confine our view to some of the most important advances made in the leading types. Stromatopora have disappeared. Protozoans and sponges are exceedingly abundant, and all contribute to the making of Mesozoic strata. Corals have assumed a more modern type. Sea urchins have become plentiful. Crinoids abound until the Cretaceous, where they begin their decline to their present humble station. Trilobites and eurypterids are gone. 10-footed crustaceans abound of the primitive long-tailed type, represented by the lobster and crayfish, and in the Jurassic there appears the modern short-tailed type, represented by the crabs. The latter type is higher in organization and now far more common. In its embryological development it passes through the long-tailed stage. Connecting links in the Mesozoic also indicate that the younger type is the offshoot of the older. Insects evolve along diverse lines, giving rise to beetles, ants, bees, and flies. Brachiopods have dwindled greatly in the number of their species, while mollusks have correspondingly increased. The great oyster family dates from here. Cephalopods are now to have their day. The archaic Orthoceras lingers onto the Triassic and becomes extinct. But a remarkable development is now at hand for the more highly organized descendants of this ancient line. We have noticed that in the Devonian the sutures of some of the chambered shells became angled, evolving the goniatite type. The sutures now became lobed and corrugated in ceratites. The process was carried still farther, and the sutures were elaborately frilled in the great order of the ammonites. It was in the Jurassic that the ammonites reached their height. No fossils are more abundant or characteristic of their age. Great banks of their shells formed beds of limestone in warm seas the world over. The ammonite stem branched into a most luxuriant variety of forms. The typical form was closely coiled like a nautilus. In others, the coil was more or less open, or even erected into a spiral. Some were hook-shaped, and there were members of the order in which the shell was straight and yet retained all the internal structures of its kind. At the end of the Mesozoic, the entire tribe of ammonites became extinct. The belemnite, Greek belemnon, a dart, is a distinctly higher type of cephalopod which appeared in the Triassic, became numerous and varied in the Jurassic and Cretaceous, and died out early in the Tertiary. Like the squids and cuttlefish, of which it was the prototype, it had an internal calcareous shell. This consisted of a chambered and siphunculed cone, whose point was sheathed in a long solid guard somewhat like a dart. The animal carried an ink sac, and no doubt used it as that of the modern cuttlefish is used, to darken the water and make an easy escape from foes. Belemnites have sometimes been sketched with fossil sepia or India ink from their own ink sacs. In the belemnites and their descendants, the squids and cuttlefish, the cephalopods made the radical change from external to the internal shell. They abandoned the defensive mechanism of warfare and boldly took up the offensive. No doubt, like their descendants, the belemnites were exceedingly active and voracious creatures. Fishes and amphibians. In the Triassic and Jurassic, little progress was made among the fishes, and the ganoid was still the leading type. In the Cretaceous, the teleosts, or bony fishes, made their appearance, while ganoids declined towards their present subordinate place. The amphibians culminated in the Triassic, some being formidable creatures as large as alligators. They were still of the primitive Paleozoic types. Their pygmy descendants of more modern types are not found until later, salamanders appearing first in the Cretaceous and frogs at the beginning of the Cenozoic. No remains of amphibians have been discovered in the Jurassic. Do you infer from this that there were none in existence at that time? Reptiles of the Mesozoic. The great order of reptiles made its advent in the Permian, culminated in the Triassic and Jurassic, and began to decline in the Cretaceous. The advance from the amphibian to the reptile was a long forward step in the evolution of the vertebrates. In the reptile, the vertebrate skeleton now became completely ossified. Gills were abandoned, and breathing was by lungs alone. The development of the individual from the egg to maturity was uninterrupted by any metamorphosis, such as that of the frog when it passes from the tadpole stage. Yet, in advancing from the amphibian to the reptile, the evolution of the vertebrate was far from finished. The cold-blooded, clumsy and sluggish, small-brained and unintelligent reptile is as far inferior to the higher mammals, whose day was still to come, as it is superior to the amphibian and fish. The reptiles of the Permian, the earliest known, were much like lizards in form of body, constituting a transition type between the amphibians on the one hand and both the higher reptiles and mammals on the other. They retain the archanic biconcave vertebra of the fish, and in some cases the persistent notochord, while some of them, the theromorphs, possessed characters allying them with mammals. In these, the skull was remarkably similar to that of the carnivores, or flesh-eating mammals, and the teeth, unlike the teeth of any other reptiles, were divisible into incisors, canines, and molars, as are the teeth of mammals. At the opening of the Mesozoic era, reptiles were the most highly organized and powerful of any animals on Earth. New ranges of continental extent were open to them, food was abundant, and the climate was congenial. And they now branched into very many diverse types which occupied and ruled all fields, the land, the air, and the sea. The Mesozoic was the age of reptiles. The ancestry of surviving reptilian types. We will consider first the evolution of the few reptilian types which have survived to the present. Crocodiles, the highest of existing reptiles, are a very ancient order dating back to the lower Jurassic, and traceable to earlier ancestral generalized forms, from which sprang several other orders also. Turtles and tortoises are not found until the early Jurassic, when they already possess the peculiar characteristics which set them off so sharply from other reptiles. They seem to have lived at first in shallow water and in swamps, and it is not until after the end of the Mesozoic that some of the order became adapted to life on the land. The largest of all known turtles, Archelon, whose home was the great interior Cretaceous Sea, was fully a dozen feet in length and must have weighed at least 2 tons. The skull alone is a yard long. Lizards and snakes do not appear until after the close of the Mesozoic, although their ancestral lines may be followed back into the Cretaceous. We will now describe some of the highly specialized orders peculiar to the Mesozoic. Land reptiles. The dinosaurs, terrible reptiles, are an extremely varied order which were masters of the land from the late Triassic until the close of the Mesozoic era. Some were far larger than elephants, some were as small as cats. Some walked on all fours, some were bipedal. Some fed on the luxuriant tropical foliage, and others on the flesh of weaker reptiles. They may be classed in 3 divisions: the flesh-eating dinosaurs, the reptile-footed dinosaurs, and the beaked dinosaurs, the latter 2 divisions being herbivorous. The flesh-eating dinosaurs are the oldest known division of the order, and their characteristics are shown in Figure 329. As a class, reptiles are egg layers, oviparous, but some of the flesh-eating dinosaurs are known to have been viviparous, i.e., to have brought forth their young alive. This group was the longest lived of any of the 3, beginning in the Triassic and continuing to the close of the Mesozoic era. Contrast the small forelimbs, used only for grasping, with the powerful hind limbs on which the animal stalked about. Some of the species of this group seem to have been able to progress by leaping in kangaroo fashion. Notice the sharp claws, the ponderous tail, and the skull set at right angles with the spinal column. The limb bones are hollow. The ceratosaurs reached a length of some 15 feet, and were not uncommon in Colorado and the western lands in Jurassic times. The reptile-footed dinosaurs, Sauropoda, include some of the biggest brutes which ever trod the ground. One of the largest, whose remains are found entombed in the Jurassic rocks of Wyoming and Colorado, is shown in Figure 330. Note the 5 digits on the hind feet, the quadrupedal gait, the enormous stretch of neck and tail, the small head aligned with the vertebral column. Diplodocus was fully 65 feet long and must have weighed about 20 tons. The thigh bones of the Sauropoda are the largest bones which ever grew. That of a genus allied to the Diplodocus measures 6 feet and 8 inches, and the total length of the animal must not have been far from 80 feet, the largest land animal known. The Sauropoda became extinct when their haunts along the rivers and lakes of the western plains of Jurassic times were invaded by the Cretaceous interior sea. The beaked dinosaurs, Predentata, were distinguished by a beak sheathed with horn carried in front of the tooth-set jaw, and used, we may imagine, in stripping the leaves and twigs of trees and shrubs. We may notice only 2 of the most interesting types. Stegosaurus, plated reptile, takes its name from the double row of bony plates arranged along its back. The powerful tail was armed with long spines, and the thick skin was defended with irregular bits of bone implanted in it. The brain of the stegosaur was smaller than that of any land vertebrate, while in the sacrum the nerve canal was enlarged to 10 times the capacity of the brain cavity of the skull. Despite their feeble wits, this well-armored family lived on through millions of years which intervened between their appearance at the opening of the Jurassic and the close of the Cretaceous, when they became extinct. A less stupid brute than the stegosaur was Triceratops, the dinosaur of the 3 horns, 1 horn carried on the nose, and a massive pair set over the eyes. Note the enormous wedge-shaped skull, with its sharp beak, and the hood behind, resembling a fireman's helmet. Triceratops was fully 25 feet long, and twice the bulk of an elephant. The family appeared in the Upper Cretaceous and became extinct at its close. Their bones are found buried in the freshwater deposits of the time, from Colorado to Montana and eastward to the Dakotas. Marine reptiles. In the ocean, reptiles occupy the place now held by the aquatic mammals, such as whales and dolphins, and their form and structure were similarly modified to suit their environment. In the ichthyosaurus, fish reptile, for example, The body was fish-like in form, with short neck and large, pointed head, figure 333. A powerful tail, whose flukes were set vertical, and the lower one of which was vertebrated, served as propeller, while a large dorsal fin was developed as a cutwater. The primitive bioconcave vertebrae of the fish and of the early land vertebrates were retained, and the limbs degenerated into short paddles. The skin of the ichthyosaur was smooth like that of a whale, and its food was largely fish and cephalopods, as the fossil contents of its stomach prove. These sea monsters disported along the Pacific shore over northern California in Triassic times, and the bones of immense members of the family occur in the Jurassic strata of Wyoming. Like whales and seals, the ichthyosaurs were descended from land vertebrates which had become adapted to a marine habitat. Pliosaurs were another order which ranged throughout the Mesozoic. Descended from small amphibious animals, they later included great marine reptiles, characterized in the typical genus by long neck, snake-like head, and immense paddles. They swam in the Cretaceous interior sea of western North America. Mosasaurs belong to the same order as do snakes and lizards, and are an offshoot of the same ancestral line of land reptiles. These snake-like creatures, which measured as much as 45 feet in length, abounded in the Cretaceous seas. They had large conical teeth, and their limbs had become stout paddles. The lower jaw of the mosasaur was jointed. The quadrate bone, which in all reptiles connects the bone of the lower jaw with the skull, was movable, and as in snakes, the lower jaw could be used in thrusting prey down the throat. The family became extinct at the end of the Mesozoic and left no descendants. One may imitate the movement of the lower jaw of the mosasaur by extending the arms, clasping the hands, and bending the elbows. Flying reptiles. The atmosphere, which had hitherto been tenanted only by insects, was first conquered by the vertebrates in the Mesozoic. Pterosaurs, winged reptiles, whose whole organism was adapted for flight through the air, appeared in the Jurassic and passed off the stage of existence before the end of the Cretaceous. The bones were hollow, as are those of birds. The sternum, or breastbone, was given a keel for the attachment of the wing muscles. The fifth finger, prodigiously lengthened, was turned backward to support a membrane which was attached to the body and extended to the base of the tail. The other fingers were free, and armed with sharp and delicate claws, as shown in figures 336 and 337. These dragons of the air varied greatly in size. Some were as small as sparrows, while others surpassed in stretch of wing the largest birds of the present day. They may be divided into two groups. The earliest group comprises genera with jaws set with teeth, and with long tails, sometimes provided with a rudder-like expansion at the end. In their successors of the later group, the tail had become short, and in some of the genera the teeth had disappeared. Among the latest of the flying reptiles was the ornithostoma, birdbeak, the largest creature which ever flew, and whose remains are embedded in the offshore deposits of the Cretaceous Sea, which held sway over our western plains. Ornithostoma's spread of wings was 20 feet. Its bones were a marvel of lightness, the entire skeleton, even in its petrified condition, not weighing more than 5 or 6 pounds. The sharp beak, a yard long, was toothless and bird-like, as its name suggests. The earliest known birds are found in the Jurassic, and during the remainder of the Mesozoic they contended with the flying reptiles for the empire of the air. The first feathered creatures were very different from the birds of today. Their characteristics prove them an offshoot of the dinosaur line of reptiles. Archaeopteryx, ancient bird, figure 338, exhibits a strange mingling of bird and reptile. Like birds, it was fledged with perfect feathers, at least on wings and tail, but it retained the teeth of the reptile, and its long tail was vertebrated, a pair of feathers springing from each joint. Throughout the Jurassic and Cretaceous, the remains of birds are far less common than those of flying reptiles, and strata representing hundreds of thousands of years intervene between Archaeopteryx and the next birds of which we know, whose skeletons occur in the Cretaceous beds of western Kansas. Mammals. So far as the entries upon the geological record show, Mammals made their advent in a very humble way during the Trias. These earliest of vertebrates which suckle their young were no bigger than young kittens, and their strong affinities with the theromorphs suggest that their ancestors are to be found among some generalized types of that order of reptiles. During the long ages of the Mesozoic, mammals continued small and few, and were completely dominated by the reptiles. Their remains are exceedingly rare and consist of minute scattered teeth, with an occasional detached jaw, which prove them to have been flesh or insect eaters. In the same way, their affinities are to be seen with the lowest of mammals, the monotremes and marsupials. The monotremes, such as the duckbill mole and the spiny anteater of Australia, reproduce by means of eggs resembling those of reptiles. The marsupials, such as the possum and the kangaroo, bring forth their young alive, but in a very immature condition, and carry them for some time after birth in the marsupium, a pouch on the ventral side of the body. End of section 27, recorded by Andrew Nelson, Atlanta, Georgia.
Section 28 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Anne Boulay. The Elements of Geology by William Harmon Norton. Chapter 21. The Tertiary. The Cenozoic Era. The last stages of the Cretaceous are marked by a decadence of the reptiles. By the end of that period, the reptilian forms characteristic of the time had become extinct one after another, leaving to represent the class only the types of reptiles which continue to modern times. The day of the Ammonite and the Belemnite also now drew to a close, and only a few of these cephalopods were left to survive the period. It is therefore at the close of the Cretaceous that the line is drawn which marks the end of the Middle Age of geology and the beginning of the Cenozoic era, the era of modern life, the age of mammals. In place of the giant reptiles, mammals now became masters of the land, appearing first in generalized types which, during the long ages of the era, gradually evolved to higher forms, more specialized and ever more closely resembling the mammals of the present. In the atmosphere, the flying dragons of the Mesozoic give place to birds and bats. In the sea, whales, sharks, and teleost fishes of modern types rule in the stead of huge swimming reptiles. The lower vertebrates, the invertebrates of land and sea, and the plants of field and forest take on a modern aspect, and differ little more than those of today than the plants and animals of different countries now differ from one another. From the beginning of the Cenozoic era until now, there is a steadily increasing number of species of animals and plants which have continued to exist to the present time. The Cenozoic era comprises two divisions, the Tertiary period and the Quaternary period. In the early days of geology, the formations of the entire geologic record, as far as it was then known, were divided into three groups: the primary, the secondary, now known as a Mesozoic, and the tertiary. When the third group was subdivided into two systems, the term tertiary was retained for the first system of the two, while the term quaternary was used to designate the second. Divisions of the tertiary. The formations of the tertiary are grouped in three divisions: the Pliocene, more recent; the Miocene, less recent; and Eocene, the dawn of the recent. Each of these epochs is long and complex. Their various subdivisions are distinguished each by its own peculiar organisms, and the changes of physical geology recorded in their strata. In the rapid view which we are compelled to take, we can note only a few of the most conspicuous events of the period. Physical geology of the Tertiary in eastern North America. The Tertiary rocks of eastern North America are marine deposits and occupy the coastal lowlands of the Atlantic and Gulf states. In New England, the Tertiary beds occur on the island of Martha's Vineyard, but not on the mainland. Hence the shoreline here stood somewhat farther out than now. From New Jersey southward, the earliest tertiary sands and clays, still unconsolidated, leave only a narrow strip of the edge of the Cretaceous between them and the Triassic and crystalline rocks of the Piedmont Oldland. Hence the Atlantic shore here stood further in than now, and at the beginning of the period, the present coastal plain was continental delta. A broad belt of tertiary sea-laid limestones, sandstones, and shales surrounds the Gulf of Mexico and extends northward up the Mississippi embayment to the mouth of the Ohio River. Hence the Gulf was then larger than at present, and its waters reached in a broad bay far up the Mississippi Valley. Along the Atlantic coast, the Mesozoic peneplain may be traced shoreward to where it disappears from view beneath an unconformable cover of early tertiary marine strata. The beginning of the tertiary was therefore marked by a subsidence. The wide erosion surface which at the close of the Mesozoic lay near sea level where the Appalachian Mountains and their neighboring plateaus and uplands now stand, was lowered gently along its seaward edge beneath the tertiary Atlantic to receive a cover of its sediments. As the period progressed, slight oscillations occurred from time to time. Strips of coastal plain were added to the land, and as early as the close of the Miocene, the shore lines of the Atlantic and Gulf states had reached well nigh their present place. Louisiana and Florida were the last areas to emerge wholly from the sea, Florida being formed by a broad transverse upwarp of the continental delta at the opening of the Miocene, forming first an island, which afterwards was joined to the mainland. The Pacific Coast. Tertiary deposits with marine fossils occur along the western foothills of the Sierra Nevadas and are crumpled among the mountain masses of the coast ranges. It is hence inferred that the Great Valley of California was then a border sea, separated from the ocean by a chain of mountainous islands which were upridged into the coast ranges at a still later time. Tertiary marine strata are spread over the lower Columbia Valley and that of Puget Sound, showing that the Pacific came in broadly there. The interior of the western United States. The closing stages of the Mesozoic were marked, as we have seen, by the upheaval of the Rocky Mountains and other western ranges. The bases of the mountains are now skirted by widespread tertiary deposits, which form the highest strata of the lofty plateaus, from the level of whose summits the mountains rise. Like the recent alluvium of the Great Valley of California, these deposits imply low-lying lands when they were laid, and therefore at that time the mountains rose from near sea level. But the height at which the tertiary strata now stand, 5,000 feet above the sea at Denver and twice that height in the plateaus of southern Utah, proves that the plateaus of which the tertiary strata form a part have been uplifted during the Cenozoic. During their uplift, warping formed extensive basins both east and west of the Rockies, and in these basins, streams swept and lake-laid waste gathered to depths of hundreds and thousands of feet, as it is accumulating at present in the Great Valley of California and on the river plains of Turkestan. The tertiary river deposits of the high plains have already been described. How widespread are these ancient river plains and beds of freshwater lakes may be seen in the map of Figure 260. The Badlands. In several of the western states, large areas of tertiary freshwater deposits have been dissected to a maze of hills whose steep sides are cut with innumerable ravines. The deposits of these ancient river plains and lake beds are little cemented, and because of the dryness of the climate, are unprotected by vegetation. Hence they are easily carved by the wet weather rills of scanty and infrequent rains. These waterless, rugged surfaces were named by the early French explorers the Badlands, because they were found so difficult to traverse. The strata of the Badlands contain vast numbers of the remains of the animals of tertiary times, and the large amount of barren surface exposed to view makes search for fossils easy and fruitful. These desolate tracts are therefore frequently visited by scientific collecting expeditions. Mountain making in the Tertiary. The Tertiary period included epochs when the earth's crust was singularly unquiet. From time to time, on all the continents, subterranean forces gathered head, and the crust was bent and broken and upridged in lofty mountains. The Sierra Nevada range was formed, as we have seen, by strata crumpling at the end of the Jurassic. But since that remote time the upfolded mountains have been worn to plains and hilly uplands, the remnants of whose uplifted erosion surfaces may now be traced along the western mountain slopes. Beginning late in the Tertiary, the region was again affected by mountain-making movements. A series of displacements along a profound fault on the eastern side tilted the enormous earth block of the Sierras to the west, lifting its eastern edge to form the lofty crest and giving to the range a steep eastern front and a gentle descent toward the Pacific. The Coast Ranges also have a complex history with many vicissitudes. The earliest foldings of their strata belong to the close of the Jurassic, but it was not until the end of the Miocene that the line of mountainous islands and the heavy sediments which had been deposited on their submerged flanks were crushed into a continuous mountain chain. The thick Pliocene beds upon their sides prove that they were depressed to near sea level during the latter Tertiary. At the close of the Pliocene, the Coast Ranges rose along with the upheaval of the Sierra, and their gradual uplift has continued to the present time. The numerous north-south ranges of the Great Basin and the Mount St. Elias range of Alaska were also uptilted during the Tertiary. During the Tertiary period, many of the loftiest mountains of the earth, the Alps, the Apennines, the Pyrenees, the Atlas, the Caucasus, and the Himalayas, received the uplift to which they owe most of their colossal bulk and height, as portions of the Tertiary seabeds now found high upon their flanks attest. In the Himalayas, Tertiary marine limestones occur 16,500 feet above sea level. Volcanic activity in the Tertiary. The vast deformations of the Tertiary were accompanied on a corresponding scale by outpourings of lava, the outbursts of volcanoes, and the intrusion of molten masses within the crust. In the Sierra Nevadas, the Miocene river gravels of the valleys of the western slope, with their placer deposits of gold, were buried beneath streams of lava and beds of tuff. Volcanoes broke forth along the Rocky Mountains and on the plateaus of Utah, New Mexico, and Arizona. Mount Shasta and the immense volcanic piles of the Cascades date from this period. The mountain basin of the Yellowstone Park was filled to a depth of several thousand feet with tuffs and lavas, the oldest dating as far back as the beginning of the Tertiary. Crandall volcano was reared in the Miocene, and the latest eruptions of the park are far more recent. The Columbia and Snake River lavas. Still more important is the plateau of lava, more than 200,000 square miles in area, extending from the Yellowstone Park to the Cascade Mountains, which has been built from Miocene times to the present. Over this plateau, which occupies large portions of Idaho, Washington, and Oregon, and extends into northern California and Nevada, the country rock is basaltic lava. For thousands of square miles, the surface is a lava plain which meets the boundary mountains as a lake or sea meets a rugged and deeply indented coast. The floods of molten rock spread up the mountain valleys for a score of miles and more, the intervening spurs rising above the lava like long peninsulas, while here and there an isolated peak was left to tower above the inundation like an island off a submerged coast. The rivers which drain the plateau, the Snake, the Columbia, and their tributaries, have deeply trenched it, yet their canyons, which reach the depth of several thousand feet, have not been worn to the base of the lava, except near the margin and where they cut the summits of mountains drowned beneath the flood. Here and there the plateau has been deformed. It has been upbent into great folds and broken into immense blocks of bedded lava, forming mountain ranges, which run parallel with the Pacific coast line. On the edges of these tilted blocks, the thickness of the lava is seen to be fully 5,000 feet. The plateau has been built, like that of Iceland, of innumerable overlapping sheets of lava. On the canyon walls they weather back in horizontal terraces and long talus slopes. One may distinguish each successive flow by its dense central portion, often jointed with large vertical columns, and the upper portion with its mass of confused irregular columns and scoriaceous surface. The average thickness of the flows seems to be about 75 feet. The plateau was long in building. Between the layers are found in places old soil beds and forest grounds and the sediments of lakes. Hence the interval between the flows in any locality was sometimes long enough for clays to gather in the lakes which filled depressions in the surface. Again and again the surface of the black basalt was reddened by oxidation and decayed to soil, and forests had time to grow upon it before the succeeding inundation sealed the sediments and soils away beneath a sheet of stone. Near the edges of the lava plain, rivers from the surrounding mountains spread sheets of sand and gravel on the surface of one flow after another. These impervious sands, interbedded with the lava, become the aquifers of artesian wells. In places, the lavas rest on extensive lake deposits, 1,000 feet deep, and Miocene in age as their fossils prove. It is to the Middle Tertiary, then, that the earliest flows and the largest bulk of the great inundation belong. So ancient are the latest floods in the Columbia Basin that they have weathered to a residual yellow clay from 30 to 60 feet in depth, and marvelously rich in the mineral substances on which plants feed. In the Snake River Valley, the latest lavas are much younger. Their surfaces are so fresh and undecayed that here the effusive eruptions may well have continued to within the period of human history. Low lava domes like those of Iceland marked where the last basalt outwelled and spread far and wide before it chilled. In places, small mounds of scoria show that the eruptions were accompanied to a slight degree by explosions of steam. So fluid was this superheated lava that recent flows have been traced for more than 50 miles. The rocks underlying the Columbia lavas, where exposed to view, are seen to be cut by numerous great dikes of dense basalt, which mark the fissures through which the molten rock rose to the surface. The Tertiary included times of widespread and intense volcanic action in other continents as well as in North America. In Europe, Vesuvius and Etna began their career as submarine volcanoes in connection with earth movements which finally lifted Pliocene deposits in Sicily to their present height, 4,000 feet above the sea. Volcanoes broke forth in central France and southern Germany, in Hungary and the Carpathians. Innumerable fissures open in the crust from the north of Ireland and the western islands of Scotland to the Faroes, Iceland, and even to Arctic Greenland. And here great plateaus were built of flows of basalt similar to that of the Columbia River. In India, at the opening of the Tertiary, there had been an outwelling of basalt, flooding to a depth of thousands of feet 200,000 square miles of the northwestern part of the peninsula, and similar inundations of lava occurred where are now the tablelands of Byssinia. From the Middle Tertiary on, Asia Minor, Arabia, and Persia were the scenes of volcanic action. In Palestine, the rise of the uplands of Judea at the close of the Eocene and the downfaulting of the Jordan Valley were followed by volcanic outbursts. In comparison with the Middle Tertiary, the present is a time of volcanic inactivity and repose. Erosion of Tertiary mountains and plateaus. The mountains and plateaus, built at various times during the Tertiary and at its commencement, have been profoundly carved by erosive agents. The Sierra Nevada mountains have been dissected on the western slope by such canyons as those of Kings River and the Yosemite. 6 miles of strata have been denuded from parts of the Wasatch Mountains since their rise at the beginning of the era. From the Colorado plateaus, whose uplift dates from the same time, there have been stripped off 10,000 feet of strata over thousands of square miles, and the colossal canyon of the Colorado has been cut after this great denudation had been mostly accomplished. On the eastern side of the continent, as we have seen, a broad peneplain had been developed by the close of the Cretaceous. The remnants of this old erosion surface are now found upwarped to various heights in different portions of its area. In southern New England, it now stands 1,500 feet above the sea in western Massachusetts, declining thence southward and eastward to sea level at the coast. In southwest Virginia, it has been lifted to 4,000 feet above the sea. Manifestly, this upwarp occurred since the peneplain was formed. It is later than the Mesozoic, and the vast dissection which the peneplain has suffered since its uplift must belong to the successive cycles of Cenozoic time. Revived by the uplift, the streams of the area trenched it as deeply as its elevation permitted, and reaching grade, opened up wide valleys and new peneplains in the softer rocks. The Connecticut Valley is Tertiary in age, and in the weak Triassic sandstones has been widened in places to 15 miles. Dating from the same time are the valleys of the Hudson, the Susquehanna, the Delaware, the Potomac, and the Shenandoah. In Pennsylvania and the states lying to the south, the Mesozoic peneplain lies along the summits of the mountain ridges. On the surface of this ancient plain, Tertiary erosion etched out the beautifully irregular pattern of the Allegheny mountain ridges and their intervening valleys. The weaker strata of the long regular folds were eroded into longitudinal valleys, while the hard Paleozoic sandstones, such as the Medina and the Pocono, were left in relief as bold mountain walls whose even crests rise to the common level of the ancient plain. From Virginia far into Alabama, the great Appalachian Valley was open to a width in places of 50 miles and more, along a belt of intensely folded and faulted strata where once was the heart of the Appalachian Mountains. In Figure 70, the summit of the Cumberland Plateau marks the level of the Mesozoic peneplain, while the lower erosion levels are Tertiary and Quaternary in age. Life of the Tertiary period. Vegetation and climate. The highest plants in structure, the dicotyls, such as our deciduous forest trees, and the monocotyls, represented by the palms, were introduced during the Cretaceous. The vegetable kingdom reached its culmination before the animal kingdom, and if the dividing line between the Mesozoic and the Cenozoic were drawn according to the progress of plant life, the Cretaceous instead of the Tertiary would be made the opening period of the modern era. The plants of the Tertiary belonged, for the most part, to genera now living, but their distribution was very different from that of the flora of today. In the earlier Tertiary, palms flourished over northern Europe, and in the northwestern United States grew the magnolia and laurel, along with the walnut, oak, and elm. Even in northern Greenland and in Spitzenberg there were lakes covered with water lilies and surrounded by forests of maples, poplars, limes, the cypress of our southern states, and noble sequoias similar to the big trees and redwoods of California. A warm climate like that of the Mesozoic, therefore, prevailed over North America and Europe, extending far toward the pole. In the later Tertiary, the climate gradually became cooler. Palms disappeared from Europe, and everywhere the aspect of forests and open lands became more like that of today. Grasses became abundant, furnishing a new food for herbivorous animals. Animal life of the Tertiary. Little needs to be said of the Tertiary invertebrates, so nearly were they like the invertebrates of the present. Even in the Eocene, about 5% of marine shells were of species still living, and in the Pliocene the portion had risen to more than one-half. Fishes were of modern types. Teleosts were now abundant. The ocean teemed with sharks, some of them being voracious monsters 75 feet and even more in length, with a gape of jaw of 6 feet, as estimated by the size of their enormous sharp-edged teeth. Snakes are found for the first time in the early Tertiary. These limbless reptiles, evolved by degeneration from lizard-like ancestors, appeared in non-poisonous types scarcely to be distinguished from those of the present day. Mammals of the early Tertiary. The fossils of continental deposits of the earliest Eocene show that a marked advance had been made in the evolution of the Mammalia. The higher mammals had appeared, and henceforth the lower mammals, the monotremes and the marsupials, are reduced to a subordinate place. These first true mammals are archaic and generalized in structure. Their feet were of the primitive type, with 5 toes of about equal length. They were also plantigrades, that is, they touched the ground with the sole of the entire foot from toe to heel. No foot had yet become adapted to swift running by a decrease in the number of digits and by lifting the heel and sole so that only the toes touched the ground. a tread called digitigrade. Nor was there yet any foot like that of the cats, with sharp retractile claws adapted to seizing and tearing the prey. The forearm and lower leg each had still two separate bones, ulna and radius, fibula and tibia, neither pair having been replaced by a single strong bone, as in the leg of the horse. The teeth were also primitive in type and of full number. The complex heavy grinders of the horse and elephant, the sharp cutting teeth of the carnivores, and the cropping teeth of the grass eaters were all still to come. Phenacodus is a characteristic genus of the early Eocene, whose species varied in size from that of a bulldog to that of an animal a little larger than a sheep. Its feet were primitive, and their 5 toes bore nails intermediate in form between a claw and a hoof. The archaic type of teeth indicates that the animal was omnivorous in diet. A cast of the brain cavity shows that, like its associates of the time, its brain was extremely small and nearly smooth, having little more than traces of convolutions. The long ages of the Eocene and the following epochs of the Tertiary were times of comparatively rapid evolution among the mammalia. The earliest forms evolved along diverging lines towards the various specialized types of hoofed mammals, rodents, carnivores, proboscideans, the primates, and the other mammalian orders as we know them now. We must describe the tertiary mammals very briefly, tracing the lines of descent of only a few of the more familiar mammals of the present. The horse. The pedigree of the horse runs back to the early Eocene, through many genera and species to a 5-toed footnote, or more accurately, with 4 perfect toes and a rudimentary 5th corresponding to the thumb. End footnote. A short-legged ancestor little bigger than a cat. Its descendants gradually increased in stature and became better and better adapted to swift running to escape their foes. The leg became longer, and only the tip of the toes struck the ground. The middle toe, digit number 3, originally the longest of the 5, steadily enlarged, while the remaining digits dwindled and disappeared. The inner digit, corresponding to the great toe and thumb, was the first to go. Next, number 5, the little finger, was also dropped. By the end of the Eocene, a 3-toed genus of the horse family had appeared, as large as a sheep. The hoof of digit number 3 now supported most of the weight, but the slender hoofs of digits 2 and 4 were still serviceable. In the Miocene, the stature of the ancestors of the horse increased to that of a pony. The feet were still 3-toed, but the side hoofs were now mere dewclaws and scarcely touched the ground. The evolution of the family was completed in the Pliocene. The middle toe was enlarged still more, the side toes were dropped, and the palm and foot bones which supported them were reduced to splints. While these changes were in progress, the radius and ulna of the forelimb became consolidated to a single bone, and in the hind limb the fibula dwindled to a splint, while the tibia was correspondingly enlarged. The molars also gradually lengthened, and became more and more complex on their grinding surface. The neck became longer, the brain steadily increased in size, and its convolutions became more abundant. The evolution of the horse has made for greater fleetness and intelligence. The rhinoceros and tapir. These animals, which are grouped with the horse among the odd-toed perissodactyl mammals, are now verging towards extinction. In the rhinoceros, evolution seems to have taken the opposite course from that of the horse. As the animal increased in size, it became more clumsy. Its limbs became shorter and more massive, and perhaps, because of its great weight, the number of digits were not reduced below the number 3. Like other large herbivores, the rhinoceros, too slow to escape its enemies by flight, learned to withstand them. It developed as its means of defense a nasal horn. Peculiar offshoots of the line appeared at various times in the Tertiary. A rhinoceros, semi-aquatic in habits, with curved tusks, resembling in aspect the hippopotamus, lived along the watercourses of the plains east of the Rockies, and its bones are now found by the thousands in the Miocene of Kansas. Another developed along a line parallel to that of the horse, and herds of these light-limbed and swift-footed running rhinoceroses range the plains from the Dakotas southwards. The tapirs are an ancient family which has changed but little since it separated from the other perissodactyl stocks in the early Tertiary. At present tapirs are found only in South America and southern Asia, a remarkable distribution which we could not explain, were it not that the geological record shows that during Tertiary times tapirs ranged throughout the northern hemisphere, making their way to South America late in that period. During the Pleistocene they became extinct over all the intervening lands between the widely separated regions where now they live. The geographic distribution of animals, as well as their relationships and origins, can be understood only through a study of their geological history. The Proboscideans. This unique order of hoofed mammals, of which the elephant is the sole survivor, began, so far as known, in the Eocene in Egypt, with a pig-like ancestor the size of a small horse, with cheek teeth like the mastodons, but wanting both trunk and tusks. The Proboscidean came next, with 4 short tusks, and in the Miocene there followed a mastodon, armed with 2 pairs of long, straight tusks on which rested a flexible proboscis. The Dinotheria was a curious offshoot of the line, which developed in the Miocene in Europe. In this immense Proboscidean, whose skull was 3 feet long, the upper pair of tusks had disappeared, and those of the lower jaw were bent down with a backward curve in walrus fashion. In the true elephants, which do not appear until near the close of the Tertiary, the lower jaw loses its tusks and the grinding teeth become exceedingly complex in structure. The grinding teeth of the mastodon had long roots and low crowns crossed by 4 or 5 peaked enamel ridges. In the teeth of the true elephants the crown has become deep, and the ridges of enamel have changed to numerous upright, plate-like folds, their interspaces filled with cement. The 2 genera, mastodon and elephant, are connected by species whose teeth are intermediate in pattern. The Proboscideans culminated in the Pliocene, when some of the giant elephants reached a height of 14 feet. The artiodactyls comprise the hoofed mammalia which have an even number of toes, such as cattle, sheep, and swine. Like the perissodactyls, they are descended from the primitive 5-toed plantigrade mammals of the lowest Eocene. In their evolution, digit number 1 was first dropped, and the middle pair became larger and more massive, while the side digits, number 2 and 5, became shorter, weaker, and less serviceable. The 4-toed artiodactyls culminated in the Tertiary. At present they are represented only by the hippopotamus and the hog. Along the main line of the evolution of the artiodactyls, the side toes, digits 2 and 5, disappeared, leaving as proof that they once existed the corresponding bones of palm and sole as splints. The 2-toed artiodactyls, such as the camels, deer, cattle, and sheep, are now the leading types of the herbivores. Swine and peccaries are 2 branches of a common stock, the first developing in the Old World and the second in the New. In the Miocene, a noticeable offshoot of the line was a gigantic pig-like brute, a root-eater, with a skull a yard in length, whose remains are now found in Colorado and South Dakota. Camels and llamas. The line of camels and llamas developed in North America, where the successive changes from an early Eocene ancestor, no larger than a rabbit, are traced step by step to the present forms, as clearly as the evolution of the horse. In the late Miocene, some of the ancestral forms migrated to the Old World by way of a land connection where the Bering Strait now is, and there gave rise to the camels and dromedaries. Others migrated into South America, which had been now connected with our own continent, and these developed into the llamas and guanacos, while those of the race which remained in North America became extinct during the Pleistocene. Some peculiar branches of the camel stem appeared in North America. In the Pliocene arose a llama with the long neck and limbs of a giraffe, whose food was cropped from the leaves and branches of trees. Far more generalized in structure was the Oreodon, an animal related to the camels, but with distinct affinities also with other lines, such as those of the hog and deer. These curious creatures were much like the peccary in appearance, except for their long tails. In the Middle Eocene, they roamed in vast herds from Oregon to Kansas and Nebraska. The ruminants. This division of the artiodactyls includes antelopes, deer, oxen, bison, sheep, and goats, all of which belong to a common stock which took its rise in Europe in the Upper Eocene from ancestral forms akin to those of the camels. In the Miocene, the evolution of the two-toed artiodactyl foot was well nigh completed. Bone-like growths appeared on the head, and the two groups of the ruminants became specialized. The deer with bony antlers, shed and renewed each year, and the ruminants with hollow horns, whose two bony knobs upon the skull are covered with permanent, pointed, horny sheaths. The ruminants evolved in the Old World, and it was not until the later Miocene that the ancestors of the antelope and some deer found their way to North America. Mountain sheep and goats, the bison, and most of the deer did not arrive until after the close of the Tertiary, and sheep and oxen were introduced by man. The hoofed mammals of the Tertiary included many offshoots from the main line which we have traced. Among them were a number of genera of clumsy, ponderous brutes, some almost elephantine in their bulk. The carnivores. The ancestral lines of the families of the flesh eaters, such as the cats, lions, tigers, etc., the bears, the hyenas, and the dogs, including wolves and foxes, converge in the creodonts of the early Eocene, an order so generalized that it had affinities not only with the carnivores, but also with the insect eaters, the marsupials, and the hoofed mammals as well. From these primitive flesh eaters, with small and simple brains, numerous small teeth, and plantigrade tread, the different families of the carnivores of the present have slowly evolved. Dogs and bears. The dog family diverged from the creodonts late in the Eocene and divided into two branches, one of which evolved the wolves and the other the foxes. An offshoot gave rise to the family of the bears, and so closely do these two families, now wide apart, approach as we trace them back in Tertiary times, that the Amphicyon, a genus dog-like in its teeth and bear-like in other structures, is referred by some to the dog and by others to the bear family. The well-known plantigrade tread of bears is a primitive characteristic which has survived from their creodont ancestry. Cats. The family of the cats, the most highly specialized of all the carnivores, divided in the Tertiary into two main branches. One, the saber-toothed tigers, which takes its name from their long saber-like sharp-edged upper canine teeth, evolved a succession of genera and species, among them some of the most destructive beasts of prey which ever scourged the earth. They were masters of the entire northern hemisphere during the Middle Tertiary, but in Europe during the Pliocene they declined, from unknown causes, and gave place to the other branches of cats, which include the lions, tigers, and leopards. In the Americas, the saber-toothed tigers long survived the epoch. Marine mammals. The carnivorous mammals of the sea, whales, seals, walruses, etc., seem to have been derived from some of the creodonts of the early Tertiary by adaptation to aquatic life. Whales evolved from some land ancestry at a very early date in the Tertiary. In the marine deposits of the Eocene are found the bones of the zeuglodont, a whale-like structure 70 feet in length. Primates. This order, which includes lemurs, monkeys, apes, and man, seems to have sprung from a creodont or insectivorous ancestry in the lower Eocene. Lemur-like types, with small smooth brains, were abundant in the United States in the early Tertiary, but no primates have been found here in the Middle Tertiary and later strata. In Europe, true monkeys were introduced in the Miocene and were abundant until the close of the Tertiary, when they were driven from the continent by the increasing cold. Advance of the Mammalia during the Tertiary. During the several millions of years comprised in Tertiary time, the mammals evolved from the lowly simple types which tenanted the earth at the beginning of the period into the many kinds of highly specialized mammals of the Pleistocene and the present, each with the various structures of the body adapted to its own peculiar mode of life. The swift feet of the horse, the horns of cattle and the antlers of the deer, the lion's claws and teeth, the long incisors of the beaver, the proboscis of the elephant, were all developed in tertiary times. In especial, the brain of the tertiary mammals constantly grew larger relatively to the size of the body, and the higher portion of the brain, the cerebral lobes, increased in size in comparison with the cerebellum. Some of the hoofed mammals now have a brain 8 or 10 times the size of that of their early tertiary predecessors of equal bulk. Nor can we doubt that along with the increasing size of the brain went a corresponding increase in the keenness of the senses, in activity and vigor, and in intelligence. End of section 28. Section 29 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Anne Boulay. The Elements of Geology by William Harmon Norton. Chapter 22, The Quaternary, Part 1. The last period of geological history, the Quaternary, may be said to have begun when all, or nearly all, living species of mollusks and most of the existing mammals had appeared. It is divided into two great epochs. The first, the Pleistocene or glacial epoch, is marked off from the Tertiary by the occupation of the northern parts of North America and Europe by vast ice sheets. The second, the recent epoch, began with the disappearance of the ice sheets from these continents and merges into the present time. The Pleistocene epoch. We now come to an episode of unusual interest, so different was it from most of the preceding epochs and from the present, and so largely has it influenced the conditions of man's life. The records of the glacial epoch are so plain and full, we are compelled to believe what otherwise would seem almost incredible, that following the mild climate of the Tertiary came a succession of ages when ice fields, like that of Greenland, shrouded the northern parts of North America and Europe, and extended far into temperate latitudes. The drift. Our studies of glaciers have prepared us to decipher and interpret the history of the glacial epoch, as it is recorded in the surface deposits known as the drift. Over most of Canada and the northern states, this familiar formation is exposed to view in nearly all cuttings which pass below the surface soil. The drift includes two distinct classes of deposits: the unstratified drift, laid down by glacier ice, and the stratified drift, spread by glacial waters. The materials of the drift are in any given place, in part unlike the rock on which it rests. They cannot be derived from the underlying rock by weathering, but have been brought from elsewhere. Thus where a region is underlain by sedimentary rocks, as is the drift-covered area from the Hudson River to the Missouri, the drift contains not only fragments of limestone, sandstone, and shale of local derivation, but also pebbles of many igneous and metamorphic rocks, such as granites, gneisses, schists, dike rocks, quartzites, and the quartz of mineral veins, whose nearest source is the Archean area of Canada and the states of our northern border. The drift received its name when it was supposed that the formation had been drifted by floods and icebergs from outside sources, a theory long since abandoned. The distribution also of the drift points clearly to its peculiar origin. Within the limits of the glaciated area, it covers the country without regard to the relief, mantling with its debris not only lowlands and valleys, but also highlands and mountain slopes. The boundary of the drift is equally independent of the relief of the land, crossing hills and plains impartially, unlike water-laid deposits, whose margins, unless subsequently deformed, are horizontal. The boundary of the drift is strikingly lobate also, bending outward in broad convex curves, where there are no natural boundaries in the topography of the country to set it such a limit. Under these conditions, such a low bait margin cannot belong to the deposits of rivers, lakes, or ocean, but is precisely that which would mark the edge of a continental glacier, which deployed in long tongues of ice. The rock surface underlying the drift. Over much of its area, the drift rests on firm, fresh rock, showing that both the preglacial mantle of residual waste and the partially decomposed and broken rock beneath it have been swept away. The underlying rock, especially if massive, hard, and of fine grain, has often been ground down to a smooth surface and rubbed to a polish as perfect as that seen on the rock beside an alpine glacier where the ice has recently melted back. Frequently it has been worn down to the smooth rounded hummocks known as rauches moutonnes, and even rocky hills have been thus smoothed to flowing outlines like rauches moutonnes on a gigantic scale. The rock pavement beneath the drift is also marked by long straight parallel scorings, varying in size from deep grooves to fine stria, as delicate as the hairlines cut by an engraver's needle. Where the rock is soft or closely jointed, it is often shattered to a depth of several feet beneath the drift, while stony clay has been thrust in among the fragments into which the rock is broken. In the presence of these glaciated surfaces, we cannot doubt that the area of the drift has been overridden by vast sheets of ice which, in their steady flow, rasped and scored the rock bed beneath by means of the stones with which their basal layers were inset, and in places plucked and shattered it. Till. The unstratified portion of the drift consists chiefly of sheets of dense, stony clay called till, which clearly are the ground moraines of the ancient continental glaciers. Till is an unsorted mixture of materials of all sizes, from fine clay and sand, gravel, pebbles, and cobblestones, to large boulders. The stones of the till are of many kinds, some having been plucked from the bedrock of the locality where they are found, and others having been brought from outside and often distant places. Land ice is the only agent known which can spread unstratified material in such extensive sheets. The fine material of the till comes from two different sources. In part it is derived from old residual clays, which in the making had been leached of the lime and other soluble ingredients of the rock from which they weathered. In part it consists of sound rock ground fine. A drop of acid on fresh clayey till often proves by brisk effervescence that the till contains much undecayed limestone flour. The ice sheet, therefore, both scraped up the mantle of long weathered waste which covered the country before its coming, and also ground heavily upon the sound rock beneath, and crushed and wore to rock flour the fragments which it carried. The color of unweathered till depends on that of the materials of which it is composed. Where red sandstones have contributed largely to its making, as over the Triassic sandstones of the eastern states and the Algonquian sandstones about Lake Superior, the drift is reddish. When derived in part from coaly shales, as over many outcrops of the Pennsylvanian, it may, when moist, be almost black. Fresh till is normally a dull gray or bluish, so largely is it made up of the grindings of unoxidized rocks of these common colors. Except where composed chiefly of sand or coarser stuff, unweathered till is often exceedingly dense. Can you suggest by what means it has been thus compacted? Did the ice fields of the glacial epoch bear heavy surface moraines like the medial and lateral moraines of valley glaciers? Where was the greater part of the load of these ice fields carried, judging from what you know of the glaciers of Greenland? Boulders of the drift. The pebbles and boulders of the drift are in part stream gravels, boulders of weathering, and other coarse rock waste picked up from the surface of the country by the advancing ice, and in part are fragments plucked from ledges of solid rock after the mantle of waste had been removed. Many of the stones of the till are dressed as only glacier ice can do. Their sharp edges have been blunted and their sides faceted and scored. We may easily find all stages of this process represented among the pebbles of the till. Some are little worn, even on their edges. Some are planed and scored on one side only, while some in their long journey have been ground down to many facets and have lost much of their original bulk. Evidently the ice played fast and loose with the stone carried in its basal layers, now holding it fast and rubbing it against the rock beneath, now loosening its grasp and allowing the stone to turn. Boulders of the drift are sometimes found on higher ground than their parent ledges. Thus boulders have been left on the sides of Mount Katahdin, Maine, which were plucked from limestone ledges 12 miles distant and 3,000 feet lower than their resting place. In other cases, stones have been carried over mountain ranges, as in Vermont, where pebbles of Burlington red sandstone were dragged over the Green Mountains, 3,000 feet in height, and left in the Connecticut Valley 60 miles away. No other geological agent than glacier ice could do this work. The boulders of the drift are often large. Boulders 10 and 20 feet in diameter are not uncommon, and some are known whose diameter exceeds 50 feet. As a rule, the average size of boulders decreases with increasing distance from their sources. Why? Till plains. The surface of the drift, where left in its initial state, also displays clear proof of glacial origin. Over large areas it is spread in level plains of till, perhaps boulder-dotted, similar to the plains of stony clay left in Spitzenberg by the recent retreat of some of the glaciers of that island. In places, the unstratified drift is heaped in hills of various kinds, which we will now describe. Drumlins. Drumlins are smooth, rounded hills composed of till, elliptical in base, and having their longer axes parallel to the movement of the ice, as shown by glacial scorings. They crowd certain districts in central New York and in southern Wisconsin, where they may be counted by the thousands. Among the numerous drumlins about Boston is historic Bunker Hill. Drumlins are made of ground moraine. They were accumulated and given shape beneath the overriding ice, much as are sandbars in a river, or in some instances were carved, like Roche's Moutones, by a sheet of ice out of the till left by an earlier ice invasion. Terminal moraines. The glaciated area is crossed by belts of thickened drift, often a mile or two, and sometimes even 10 miles or more, in breadth, which lie transverse to the movement of the ice and clearly are the terminal moraines of ancient ice sheets, marking either the limit of their farthest advance or pauses in their general retreat. The surface of these moraines is a jumble of elevations and depressions, which vary from low gentle swells and shallow sags to sharp hills, 100 feet or so in height, and deep steep-sided hollows. Such tumultuous hills and hummocks, set with depressions of all shapes, which usually are without outlet and are often occupied by marshes, ponds, and lakes, surely cannot be the work of running water. The hills are heaps of drift, lodged beneath the ice edge or piled along its front. The basins were left among the tangle of morainic knolls and ridges as the margin of the ice moved back and forth. Some bowl-shaped basins were made by the melting of a mass of ice left behind by the retreating glacier and buried in its debris. The stratified drift. Like modern glaciers, the ice sheets of the Pleistocene were ever being converted into water about their margins. Their limits on the land were the lines where their onward flow was just balanced by melting and evaporation. On the surface of the ice along the marginal zone, rivulets no doubt flowed in summer, and found their way through crevasses to the interior of the glacier or to the ground. Subglacial streams, like those of the Malaspina Glacier, issued from tunnels in the ice, and water ran along the melting ice front, as it is seen to do about the glacier tongues of Greenland. All these glacier waters flow down the chief drainage channels in swollen rivers loaded with glacial waste. It is not unexpected, therefore, that there are found, over all the country where the melting ice retreated, deposits made of the same materials as the till, but sorted and stratified by running water. Some of these were deposited behind the ice front in ice-walled channels, some at the edge of the glaciers by issuing streams, and others were spread to long distances in front of the ice edge by glacial waters as they flowed away. Eskers are narrow, winding ridges of stratified sand and gravel whose general course lies parallel with the movement of the glacier. These ridges, though evidently laid by running water, do not follow lines of continuous descent, but may be found to cross river valleys and ascend their sides. Hence the streams by which eskers were laid did not flow unconfined upon the surface of the ground. We may infer that eskers were deposited in the tunnels and ice-wall gorges of glacial streams before they issued from the ice front. Kames are sand and gravel knolls, associated for the most part with terminal moraines, and heaped by glacial waters along the margin of the ice. Kame terraces are hummocky embankments of stratified drift, sometimes found in rugged regions along the sides of valleys. In these valleys, long tongues of glacier ice lay slowly melting. Glacial waters took their way between the edges of the glaciers and the hillside, and here deposited sand and gravel in rude terraces. Outwash plains are plains of sand and gravel which frequently border terminal moraines on their outward face, and were spread evidently by outwash from the melting ice. Outwash plains are sometimes pitted by bowl-shaped basins, where ice blocks were left buried in the sand by the retreating glacier. Valley trains are deposits of stratified drift, with which river valleys have been aggraded. Valleys leading outward from the ice front were flooded by glacial waters and were filled often to great depths with trains of stream-swept drift. Since the disappearance of the ice, these glacial floodplains have been dissected by the shrunken rivers of recent times and left on either side of the valley in high terraces. Valley trains head in morainic plains, and their material grows finer down valley and coarser toward their sources. Their gradient is commonly greater than that of the present rivers. The extent of the drift. The extent of the drift of North America and its southern limits are best seen in Figure 359. Its area is reckoned at about 4,000,000 square miles. The ice fields which once covered so much of our continent were altogether 10 times as large as the inland ice of Greenland, and about equal to the enormous ice cap which now covers the Antarctic regions. The ice field of Europe was much smaller, measuring about 770,000 square miles. Centers of dispersion. The direction of the movement of the ice is recorded plainly in the scorings of the rock's surface, in the shapes of glaciated hills, in the axes of drumlins and eskers, and in trains of boulders, when the ledges from which they were plucked can be discovered. In these ways it has been proved that in North America there were 3 centers where ice gathered in the greatest depth, and from which it flowed in all directions outward. There were thus 3 vast ice fields: one the Cordilleran, which lay upon the Cordilleras of British America; one the Keewatin, which flowed out from the province of Keewatin west of Hudson Bay; and one the Labrador ice field, whose center of dispersion was the highlands of the peninsula of Labrador. As shown in Figure 359, the western ice field extended but a short way beyond the eastern foothills of the Rocky Mountains, where perhaps it met the far-traveled ice from the central field. The Keewatin and Labrador ice fields flowed farthest toward the south, and in the Mississippi Valley the one reached the mouth of the Missouri and the other nearly to the mouth of the Ohio. In Minnesota and Wisconsin and northward they merged in one vast field. The thickness of the ice was so great that it buried the highest mountains of eastern North America, as is proved by the transported boulders which have been found upon their summits. If the land then stood at its present height above sea level, and if the average slope of the ice was no more than 10 feet to the mile, a slope so gentle that the eye could not detect it, and less than half the slope of the interior of the inland ice of Greenland, the ice plateaus about Hudson Bay must have reached a thickness of at least 10,000 feet. In Europe the Scandinavian plateau was the chief center of dispersion. At the time of greatest glaciation, a continuous field of ice extended from the Ural Mountains to the Atlantic, where, off the coasts of Norway and the British Isles, it met the sea in an unbroken ice wall. On the south it reached to southern England, Belgium, and central Germany, and deployed on the eastern plains in wide lobes over Poland and central Russia. At the same time, the Alps supported giant glaciers many times the size of the surviving glaciers of today, and a Piedmont glacier covered the plains of northern Switzerland. The thickness of the drift. The drift is far from uniform in thickness. It is comparatively thin and scanty over the Laurentian highlands and the rugged regions of New England, while from southern New York and Ontario westward over the Mississippi Valley and on the great western plains of Canada it exceeds an average of 100 feet over wide areas, and in places has 5 and 6 times that thickness. It was to this marginal belt that the ice sheets brought their loads, while northwards, nearer the centers of dispersion, erosion was excessive and deposition slight. Successive ice invasions and their drift sheets. Recent studies of the drift prove that it does not consist of one indivisible formation, but includes a number of distinct drift sheets, each with its own peculiar features. The Pleistocene epoch consisted, therefore, of several glacial stages, during each of which the ice advanced far southward, together with the intervening interglacial stages when, under a milder climate, the ice melted back towards its source or wholly disappeared. The evidences of such interglacial stages, and the means by which the different drift sheets are told apart, are illustrated in Figure 361. Here the country from N to S is wholly covered by drift, but the drift from N to M is so unlike that from M to S that we may believe it the product of a distinct ice invasion and deposited during another and far later glacial stage. The former drift is very young, for its drainage is yet immature, and there are many lakes and marshes upon its surface. The latter is far older, for its surface has been thoroughly dissected by its streams. The former is but slightly weathered, while the latter is so old that it is deeply reddened by oxidation, and is leached of its soluble ingredients such as lime. The younger drift is bordered by a distinct terminal moraine, while the margin of the older drift is not thus marked. Moreover, the two drift sheets are somewhat unlike in composition, and the different proportion of pebbles of the various kinds of rocks which they contain shows that their respective glaciers followed different tracks and gathered their loads from different regions. Again, in places beneath the younger drift, there is found the buried land surface of an older drift with old soils, forest grounds, and vegetable deposits, containing the remains of animals and plants, which tell of the climate of the interglacial stage in which they lived. By such differences as these, the following drift sheets have been made out in America, and similar subdivisions have been recognized in Europe. 5. The Wisconsin Formation. 4. The Iowan Formation. 3. The Illinoisan Formation. 2. The Kansan Formation. 1. The Pre-Kansan or Jerseyan Formation. In New Jersey and Pennsylvania, the edge of a deeply weathered and eroded drift sheet, the Jerseyan, extends beyond the limits of a much younger overlying drift. It may be the equivalent of a deep buried basal drift sheet found in the Mississippi Valley beneath the Kansan, and parted from it by peat, old soil, and gravel beds. The two succeeding stages mark the greatest snowfall of the glacial epoch. In Kansan times, the Keewatin ice field slowly grew southward until it reached 1,500 miles from its center of dispersion and extended from the Arctic Ocean to northeastern Kansas. In the Iowan stage, the Labrador ice field stretched from Hudson Straits nearly to the Ohio River in Illinois. In the Iowan and the Wisconsin, the closing stages of the glacial epoch, the re-advancing ice fields fell far short of their former limits in the Mississippi Valley. But in the eastern states, the Labrador ice field during Wisconsin times overrode for the most part all earlier deposits, and, covering New England, probably met the ocean in a continuous wall of ice which set its bergs afloat from Massachusetts to northern Labrador. We select for detailed description the Kansan and the Wisconsin formations as representatives, the one of the older and the other of the younger drift sheets. The Kansan Formation. The Kansan drift consists for the most part of a sheet of clayey till carrying smaller boulders than the later drift. Few traces of drumlins, kames, or terminal moraines are found upon the Kansan drift, and where thick enough to mask the pre-existing surface, it seems to have been spread originally in level plains of till. The initial Kansan plain has been worn by running water till there are now left only isolated patches and the narrow strips and crests of the divides, which still rise to the ancient level. The valleys of the larger streams have been opened wide. Their well-developed tributaries have carved nearly the entire plain to valley slopes. The lakes and marshes which once marked the infancy of the region have long since been effaced. The drift is also deeply weathered. The till, originally blue in color, has been yellowed by oxidation to a depth of 10 and 20 feet and even more, and its surface is sometimes rusted to terracotta red. To a somewhat less depth it has been leached of its lime and other soluble ingredients. In the weathered zone its pebbles, especially where the till is loose in texture, are sometimes so rotted that granites may be crumbled with the fingers. The Kansan drift is therefore old. The Wisconsin Formation. The Wisconsin drift sheet is but little weathered and eroded, and therefore is extremely young. Oxidation has affected it but slightly, and lime and other soluble plant foods remain undissolved even at the grass roots. Its river systems are still in their infancy. Swamps and peat bogs are abundant in its undrained surface, and to this drift sheet belong the lakelands of our northern states and of the Laurentian peneplain of Canada. The lake basins of the Wisconsin drift are of several different classes. Many are shallow sags in the ground moraine. Still more numerous are the lakes set in hollows among the hills of the terminal moraines, such as the thousands of lakelets of eastern Massachusetts. Indeed, the terminal moraines of the Wisconsin drift may often be roughly traced on maps by means of belts of lakes and ponds. Some lakes are due to the blockage of ancient valleys by morainic delms, and this class includes many of the lakes of the Adirondacks, the mountain regions of New England, and the Laurentian area. Still other lakes rest in rock basins scooped out by glaciers. In many cases, lakes are due to more than one cause, as where pre-glacial valleys have both been basined by the ice and blockaded by its moraines. The Finger Lakes of New York, for example, occupy such glacial troughs. Massive terminal moraines, which mark the farthest limits to which the Wisconsin ice advanced, have been traced from Cape Cod and the islands south of New England, across the Appalachians and the Mississippi Valley, through the Dakotas, and far to the north over the plains of British America. Where the ice halted for a time in its general retreat, it left recessional moraines, as this variety of the terminal moraine is called. The moraines of the Wisconsin drift lie upon the country like great festoons, each series of concentric loops marking the utmost advance of the broad lobes of the ice margin and the various pauses in their recession. Behind the terminal moraines lie wide till plains, in places studded thickly with drumlins, or ridged with an occasional esker. Great outwashed plains of sand and gravel lie in front of the moraine belts, and long valley trains of coarse gravels tell of the swift and powerful rivers of the time. The loess of the Mississippi Valley. A yellow earth, quite like the loess of China, is laid broadly as a surface deposit over the Mississippi Valley from eastern Nebraska to Ohio, outside the boundaries of the Iowan and the Wisconsin drift. Much of the loess was deposited in Iowan times. It is younger than the earlier drift sheets, for it overlies their weathered and eroded surfaces. It thickens to the Iowan drift border, but is not found upon that drift. It is older than the Wisconsin, for in many places it passes underneath the Wisconsin terminal moraines. In part, the loess seems to have been washed from glacial waste and spread in sluggish glacial waters, and in part to have been distributed by the wind from plains of aggrading glacial streams. The effects of the ice invasions on rivers. The repeated ice invasions of the Pleistocene profoundly disarranged the drainage systems of our northern states. In some regions the ancient valleys were completely filled with drift. On the withdrawal of the ice, the streams were compelled to find their way, as best they could, over a fresh land surface, where we now find them flowing on the drift in young narrow channels. But hundreds of feet below the ground, the well driller and the prospector for coal and oil discovered deep wide buried valleys cut in rock, the channels of pre-glacial and interglacial streams. In places, the ancient valleys were filled with drift to a depth of 100 feet, and sometimes even to a depth of 400 and 500 feet. In such valleys, Rivers now flow high above their ancient beds of rock on floors of valley drift. Many of the valleys of our present rivers are but patchworks of pre-glacial, interglacial, and postglacial courses. Here the river winds along an ancient valley with gently sloping sides and a wide alluvial floor perhaps a mile or so in width, and there it enters a young rock-walled gorge, whose rocky bed may be crossed by ledges over which the river plunges in waterfalls and rapids. In such cases it is possible that the river was pushed to one side of its former valley by a lobe of ice, and compelled to cut a new channel in the adjacent uplands. A section of the valley may have been blockaded by morainic waste, and the lake formed behind the barrier may have found outlet over the country to one side of the ancient drift-filled valley. In some instances, it would seem that during the waning of the ice sheets, glacial streams, while confined within walls of stagnant ice, cut down through the ice and incised their channels on the underlying country, in some cases being let down on old river courses, and in other cases excavating gorges in adjacent uplands. End of section 29. Section 30 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Anne Boulay. The Elements of Geology by William Harmon Norton. Chapter 22, The Quaternary, Part 2. Pleistocene Lakes. Temporary lakes were formed wherever the ice front dammed the natural drainage of the region. Some, held in the minor valleys crossed by ice lobes, were small, and no doubt many were too short-lived to leave lasting records. Others, long held against the northward sloping country by the retreating ice edge, left in their beaches their clayey beds, and their outlet channels permanent evidences of their area and depth. Some of these glacial lakes are thus known to have been larger than any present lake. Lake Agassiz, named in honor of the author of the theory of continental glaciation, is supposed to have been held by the united front of the Keewatin and Labrador ice fields as they finally retreated down the valley of the Red River of the North and the drainage basin of Lake Winnipeg. From first to last, Lake Agassiz covered 110,000 square miles in Manitoba and the adjacent parts of Minnesota and North Dakota, an area larger than all the Great Lakes combined. It discharged its waters across the divide which held it on the south, and thus excavated the valley of the Minnesota River. The lake bed, a plain of till, was spread smooth and level as a floor with lacustrine silts. Since Lake Agassiz vanished with the melting back of the ice, beyond the outlet by the Nelson River into Hudson Bay, there has gathered on its floor a deep humus, rich in the nitrogenous elements so needful for the growth of plants, and it is to this soil that the region owes its well-known fertility. The Great Lakes. The basins of the Great Lakes are broad pre-glacial river valleys, warped by movements of the crust still in progress, enlarged by the erosive action of lobes of the continental ice sheets, and blockaded by their drift. The complicated glacial and postglacial history of the lakes is recorded in old strand lines, which have been traced at various heights about them, showing their areas and the levels at which their water stood at different times. With the retreat of the lobate Wisconsin ice sheet toward the north and east, the southern and western ends of the basins of the Great Lakes were uncovered first, and here, between the receding ice fronts and the slopes of land which faced it, lakes gathered which increased constantly in size. The lake which thus came to occupy the western end of the Lake Superior Basin discharged over the divide at Duluth down the St. Croix River, as an old outlet channel proves. That which held the southern end of the basin of Lake Michigan sent its overflow across the divide at Chicago via the Illinois River to the Mississippi. The lake which covered the lowlands about the western end of Lake Erie discharged its waters at Fort Wayne into the Wabash River. The ice still blocked the Mohawk and St. Lawrence valleys on the east, while on the west it had retreated far to the north. The lakes became confluent in wide expanses of water, whose depths and margins, as shown by their old lake beaches, varied at different times with the position of the confining ice and with warpings of the land. These vast water bodies, which at one or more periods were greater than all the Great Lakes combined, discharged at various times across the divide at Chicago, near Syracuse, New York, down the Mohawk Valley, and by a channel from the Georgian Bay into the Ottawa River. Last of all, the present outlet by the St. Lawrence was established. The beaches of the glacial lakes just mentioned are now far from horizontal. That of the lake which occupied the Ontario basin has an elevation of 362 feet above tide at the west, and of 675 feet at the northeast, proving here a differential movement of the land since glacial times amounting to more than 300 feet. The beaches which mark the successive heights of these glacial lakes are not parallel. Hence the warping began before the glacial epoch closed. We have already seen that the canting of the region is still in progress. The Champlain subsidence. As the glacial epoch approached its end, and the Labrador ice field melted back for the last time to near its source, the land on which the ice had lain in eastern North America was so depressed that the sea now spread far and wide up the St. Lawrence Valley. It joined with Lake Ontario, and extending down the Champlain and Hudson valleys, made an island of New England and the maritime provinces of Canada. The proofs of this subsidence are found in old sea beaches and sea-laid clays resting on Wisconsin till. At Montreal, such terraces are found 620 feet above sea level, and along Lake Champlain, where the skeleton of a whale was once found among them, at from 500 to 400 feet. The heavy delta which the Mohawk River built at its mouth, in this arm of the sea, now stands something more than 300 feet above sea level. The clays of the Champlain subsidence pass under water near the mouth of the Hudson, and in northern New Jersey they occur 200 feet below tide. In these elevations we have measures of the warping of the region since glacial times. The western United States in glacial times. The western United States was not covered during the Pleistocene by any general ice sheet, but all the high ranges were capped with permanent snow and nourished valley glaciers, often many times the size of existing glaciers of the Alps. In almost every valley of the Sierras and the Rockies, the records of these vanished ice streams may be found in cirques, glacial troughs, roches moutonnes, and morainic deposits. It was during the glacial epoch that Lakes Bonneville and Lahontan were established in the Great Basin, whose climate must have been much more moist than now. The driftless area. In the upper Mississippi Valley there is an area of about 10,000 square miles in southern Wisconsin and the adjacent parts of Iowa and Minnesota, which escaped the ice invasions. The rocks are covered with residual clays, the product of long pre-glacial weathering. The region is an ancient peneplain, uplifted and dissected in late tertiary times, with mature valleys whose gentle gradients are unbroken by waterfalls and rapids. Thus the driftless area is in strong contrast with the immature drift topography about it, where lakes and waterfalls are common. It is a bit of pre-glacial landscape, showing the condition of the entire region before the glacial epoch. The driftless area lay to one side of the main track of both the Keewatin and the Labrador ice fields, and at the north it was protected by the upland south of Lake Superior, which weakened and retarded the movement of ice. South of the driftless area, the Mississippi Valley was invaded at different times by ice sheets from the west, the Kansan and the Iowan, and again by the Illinoisan ice sheet from the east. Again and again the Mississippi River was pushed to one side or the other of its path. The ancient channel which it held along the Iowan ice front has been traced through southeastern Iowa for many miles. Benefits of glaciation. Like the driftless area, the pre-glacial surface over which the ice advanced seems to have been well dissected after the late Tertiary uplifts, and to have been carved in many places to steep valley slopes and rugged hills. The retreating ice sheets, which left smooth plains and gently rolling country over the wide belt where glacial deposition exceeded glacial erosion, have made travel and transportation easier than they otherwise would have been. The pre-glacial subsoils were residual clays and sands, composed of the insoluble elements of the country rock of the locality, with some minglings of its soluble parts still undissolved. The glacial subsoils are made of rocks of many kinds, still undecayed and largely ground to powder. They thus contain an inexhaustible store of the mineral foods of plants, and in a form made easily ready for plant use. On the pre-glacial hillsides, the humus layer must have been comparatively thin, while broad glacial plains have gathered deep black soils, rich in carbon and nitrogen taken from the atmosphere. To these soils and subsoils, a large part of the wealth and prosperity of the glaciated regions of our country must be attributed. The ice invasions have also added very largely to the water power of the country. The rivers, which in pre-glacial times were flowing over graded courses for the most part, were pushed from their old valleys and set to flow on higher levels, where they have developed waterfalls and rapids. This power will probably be fully utilized long before the coal beds of the country are exhausted, and will become one of the chief sources of the national wealth. The recent epoch. The deposits laid since glacial times graduate into those now forming along the ocean shores, on lake beds, and in river valleys. Slow and comparatively slight changes, such as the warpings of the region of the Great Lakes, have brought about the geographical conditions of the present. The physical history of the recent epoch needs here no special mention. The life of the Quaternary. During the entire Quaternary, invertebrates and plants suffered little change in species. So slowly are these ancient and comparatively simple organisms modified. The mammalia, on the other hand, have changed much since the beginning of Quaternary time. The various species of the present have been evolved, and some lines have become extinct. These highly organized vertebrates are evidently less stable than our lower types of animals, and respond more rapidly to changes in the environment. Pleistocene mammals. In the Pleistocene, the mammalia reached their culmination both in size and in variety of forms, and were superior in both these respects to the mammals of today. In Pleistocene times in North America, there were several species of bison, one whose wide-spreading horns were 10 feet from tip to tip, a gigantic moose elk, a giant rodent, Castro roides, 5 feet long, several species of musk oxen, several species of horses, more akin, however, to zebras than to modern horse, a huge lion, several saber-toothed tigers, immense edentates of several genera, and largest of all, the mastodon and mammoth. The largest of the edentates was the megatherium, a clumsy ground sloth bigger than a rhinoceros. The bones of the megatherium are extraordinarily massive, the thigh bone being thrice as thick as that of an elephant, and the animal seems to have been well able to get its living by overthrowing trees and stripping off their leaves. The glyptodon was a mailed edentate, 8 feet long, resembling the little armadillo. These edentates survived from Tertiary times, and in the warmer stages of the Pleistocene ranged north as far as Ohio and Oregon. The great proboscideans of the glacial epoch were about the size of modern elephants, and somewhat smaller than their ancestral species of the Pliocene. The mastodon ranged over all North America south of Hudson Bay, but had become extinct in the Old World at the end of the Tertiary. The elephants were represented by the mammoth, which roamed in immense herds from our Middle States to Alaska, and from Arctic Asia to the Mediterranean and Atlantic. It is an oft-told story how about a century ago, near the Lena River in Siberia, there was found the body of a mammoth which had been safely preserved in ice for thousands of years, how the flesh was eaten by dogs and bears, and how the eyes and hooves and portions of the hide were taken with the skeleton to St. Petersburg. Since then, several other carcasses of the mammoth, similarly preserved in ice, have been found in the same region, one as recently as 1901. We know from these remains that the animal was clothed in a coat of long coarse hair with thick brown fur beneath. The distribution of animals and plants. The distribution of species in the glacial epoch was far different from that of the present. In the glacial stages, Arctic species ranged south into what are now temperate latitudes. The walrus throve along the shores of Virginia, and the musk ox grazed in Iowa and Kentucky. In Europe, the reindeer and Arctic fox reached the Pyrenees. During the Champlain Depression, Arctic shells lived along the shore of the arm of the sea which covered the St. Lawrence Valley. In interglacial times of milder climate, the Arctic fauna-flora retreated, and their places were taken by plants and animals from the south. Peccaries, now found in Texas, ranged into Michigan and New York, while great sloths from South America reached the Middle States. Interglacial beds at Toronto, Canada, contains remains of forests of maple, elm, and pawpaw, with mollusks now living in the Mississippi Basin. What changes in the forest of your region would be brought about, and in what way, if the climate should very gradually grow colder? What changes if it should grow warmer? On the Alps and the highest summits of the White Mountains of New England are found colonies of Arctic species of plants and insects. How did they come to be thus separated from their home beyond the Arctic Circle, by 1,000 miles and more of temperate climate impossible to cross? Man. Along with the remains of the characteristic animals of the time, which are now extinct, there have been found in deposits of glacial epoch in the Old World relics of Pleistocene man, his bones and articles of his manufacture. In Europe, where they have best been studied, human relics occur chiefly in peat bogs, in loess, in caverns where man made his home, and in high river terraces sometimes 80 and 100 feet above the present floodplains of the streams. In order to understand the development of early man, we should know that prehistoric peoples are ranked according to the materials of which their tools were made and the skill shown in their manufacture. There are thus 4 well-marked stages of human culture preceding the written annals of history. 4. The Iron Stage. 3. The Bronze Stage. 2. The Neolithic (recent stone) stage. 1. The Paleolithic (ancient stone) stage. In the Neolithic stage, the use of the metals had not yet been learned, but tools of stone were carefully shaped and polished. To this stage the North American Indian belonged at the time of the discovery of the continent. In the Paleolithic stage, stone implements were chipped to crude shapes and left unpolished. This, the lowest state of human culture, has been outgrown by nearly every savage tribe now on earth. A still earlier stage may once have existed, when man had not learned so much as to shape his weapons to his needs, but used chance pebbles and rock splinters in their natural forms. Of such a stage, however, we have no evidence. Paleolithic man in Europe. It was to the Paleolithic stage that the earliest man belonged, whose relics are found in Europe. They had learned to knock off 2-edged flakes from flint pebbles, and to work them into simple weapons. The great discovery had been made that fire could be kindled and made use of, as the charcoal and stones discolored by heat of their ancient hearths attest. Caves and shelters beneath overhanging cliffs were their homes or camping places. Paleolithic man was a savage of the lowest type, who lived by hunting the wild beasts of the time. Skeletons found in certain caves in Belgium and France represent perhaps the earliest race yet found in Europe. These short, broad-shouldered men, muscular, with bent knees and stooped gait, low-browed and small of brain, were of little intelligence and yet truly human. The remains of Pleistocene man are naturally found either in caverns, where they escaped destruction by the ice sheets, or in deposits outside the glaciated area. In both cases, it is extremely difficult, or quite impossible, to assign the remains to definite glacial or interglacial times. Their relative age is best told by the fauna with which they are associated. Thus the oldest relics of man are found with the animals of the late Tertiary or early Quaternary, such as a species of hippopotamus and an elephant more ancient than the mammoth. Later in age are the remains found along with the mammoth, cave bear, and cave hyena, and other animals of glacier time which are now extinct, while more recent still are those associated with the reindeer, which in the last ice invasion roamed widely with the mammoth over Central Europe. The caves of southern France. These contain the fullest records of the race, much like the Eskimos in bodily frame, which lived in western Europe at the time of the mammoth and the reindeer. The floors of these caves are covered with a layer of bone fragments, the remains of many meals, and here are found also various articles of handicraft. In this way we know that the savages who made these caves their homes fished with harpoons of bone and hunted with spears and darts tipped with flint and horn. The larger bones are split for the extraction of the marrow. Among such fragments no split human bones are found. This people, therefore, were not cannibals. Bone needles imply the art of sewing, and therefore the use of clothing made no doubt of skins, while various ornaments, such as necklaces of shells, show how ancient is the love of personal adornment. Pottery was not yet invented. There is no sign of agriculture. No animals had yet been domesticated, not even man's earliest friend, the dog. Certain implements, perhaps used as the insignia of office, suggest a rude tribal organization and the beginnings of the state. The remains of funeral feasts in front of caverns used as tombs point to a religion and the belief in a life beyond the grave. In the caverns of southern France are found also the beginnings of the arts of painting and of sculpture. With surprising skill, these Paleolithic men sketched on bits of ivory the mammoth with his long hair and huge curved tusks, frescoed their cavern walls with pictures of the bison and other animals, and carved reindeer on their dagger heads. Early man on other continents. Paleolithic flints curiously like those of Western Europe are found also in many regions of the Old World, in India, Egypt, and Asia Minor, beneath the earliest vestiges of the civilization of these ancient seats, and sometimes associated with the fauna of the glacial epoch. In Java there was found in 1891, in strata early Quaternary or late Pliocene in age, parts of a skeleton of lower grade, if not of greater antiquity, than any human remains now known. Pithecanthropus erectus, as the creature has been named, walked erect, as its thigh bone shows, but the skeleton and teeth indicate a close affinity with the ape. In North America there have been reported many finds of human relics in valley trains, loess, old river gravels buried beneath lava flows, and other deposits of supposed glacial age, but in the opinion of some geologists, sufficient proof of the existence of man in America in glacial times has not as yet been found. These finds in North America have been discredited for various reasons. Some were not made by scientific men accustomed to the closest scrutiny of every detail. Some were reported after a number of years, when the circumstances might not be accurately remembered, while in a number of instances it seems possible that the relics might have been worked into glacial deposits by natural causes from the surface. Man, we may believe, witnessed the great ice fields of Europe, if not of America, and perhaps appeared on earth under the genial climate of pre-glacial times. Nothing has yet been found of the line of man's supposed descent from the primates of the early Tertiary, with the possible exception of the Java remains just mentioned. The structures of man's body show that he is not descended from any of the existing genera of apes. And although he may not have been exempt from the law of evolution, that method of creation which has made all life on earth akin, yet his appearance was an event which in importance ranks with the advent of life upon the planet, and marks a new manifestation of creative energy upon a higher plane. There now appear intelligence, reason, a moral nature, and a capacity for self-directed progress such as had never been before on earth. The recent epoch. The glacial epoch ends with the melting of the ice sheets of North America and Europe, and the replacement of the Pleistocene mammalian fauna by present species. How gradually the one epoch shades into the other is seen in the fact that the glaciers which still linger in Norway and Alaska are the lineal descendants or the renewed appearances of the ice fields of glacial times. Our science cannot foretell whether all traces of the great ice age are to disappear, and the earth is to enjoy again the genial climate of the Tertiary, or whether the present is an interglacial epoch, and the northern lands are comparatively soon again to be wrapped in ice. Neolithic man. The wild Paleolithic men vanished from Europe with the wild beasts which they hunted, and their place was taken by tribes, perhaps from Asia, of a higher culture. The remains of Neolithic man are found, much as are those of the North American Indians, upon or near the surface, in burial mounds, in shell heaps, the refuse heap of their settlements, in peat bogs, caves, recent floodplain deposits, and in the beds of lakes near shore where they sometimes built their dwellings upon piles. The successive stages in European culture are well displayed in the peat bogs of Denmark. The lowest layers contain the polished stone implements of Neolithic man, along with the remains of the Scotch fir. Above are oak trunks with implements of bronze, while the higher layers hold iron weapons and the remains of a beech forest. Neolithic man in Europe had learned to make pottery, to spin and weave linen, to hew timbers and build boats, and to grow wheat and barley. The dog, horse, ox, sheep, goat, and hog had been domesticated, and as these species are not known to have existed before in Europe, it is a fair inference that they were brought by man from another continent of the Old World. Neolithic man knew nothing of the art of extracting the metals from their ores, nor had he a written language. The Neolithic stage of culture passes by insensible gradations into the Age of Bronze, and thus into the recent epoch. In the recent epoch, the progress of man in language, in social organization, in the arts of life, in morals and religion, has left ample records which are for other sciences than ours to read. Here, therefore, geology gives place to archaeology and history. Our brief study of the outlines of geology has given us, it is hoped, some great and lasting good. To conceive a past so different from the present has stimulated the imagination, and to follow the inferences by which the conclusions of our science have been reached has exercised one of the noblest faculties of the mind, the reason. We have learned to look on nature in new ways. Every landscape, every pebble now has a meaning and tells something of its origin and history, while plants and animals have a closer interest since we have traced the long lines of their descent. The narrow horizons of human life have been broken through, and we have caught glimpses of the immeasurable reach of time in which nebulae and suns and planets run their courses. Moreover, we have learned something of that orderly and world-embracing progress by which the once uninhabitable globe has come to be man's well-appointed home, and life appearing in the lowliest forms has steadily developed higher and still higher types. Seeing this progress enter human history and lift our race continually to loftier levels, we find reason to believe that the onward, upward movement of the geological past is the manifestation of the same wise power which makes for righteousness and good, and that this unceasing purpose will still lead on to nobler ends. End of section 30. End of The Elements of Geology, by William Harmon Norton.